Hey guys, good morning, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, if I'm perfectly audible, visible to everyone, just let me know quickly in the chats. Just let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. I know I was a bit late. Sorry for that, sorry for the inconvenience. There were some issues, so I was fixing them up. So now we are good to go. Yeah? So let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone. So what is the duration of the today's session? It's going to be 10-12 hours. Yeah? Be ready to sit with me for 10-12 hours. Quickly, people, quickly let me know in the chats. All right. Okay, got it. So guys, without wasting a lot of time, let's get going. But before starting the session, I just want to know one thing. I keep on asking you in every session. What is that? Which state you guys are watching me from right now? I just want to know that. Which state you guys are watching me from right now? I just want to know that first. I just want to know that first. Let me know quickly in the chats. Till then, I'm going to fix certain things here. All right, people. All right. So I can see a lot of students are from Andhra Pradesh, Kerala. Okay. Amazing. Okay, are you guys done with the class 12th marathon of physical chemistry, which I took like, I think some 7 to 8 days before, or I think some 10 days before? Are you guys done with that? Are you guys done with that? Yeah? Okay, got it. Whatever things I'll be teaching in the today's marathon, every single thing will be from the scratch, from the basics. You don't need to worry about it. Every single thing will be from the scratch, will be from the basics. Okay, and today it's going to be your class 11th physical chemistry marathon. I'll be doing all the theory, all the important types of the problem patterns that can be asked in your upcoming NEET examination, right? So I would want you guys to watch this marathon carefully, okay? And try to make the notes with me. Try to make the handwritten notes. Anyways, I'm going to share the PDF of this particular session as well. I'll be sharing on my Telegram. If you are not the part of the Telegram channel yet, you can be the part of the Telegram channel, which is Wassim Chemistry Official, right? That is the name of the Telegram channel. All right, should we start then? So today is going to be the time for your class 11th physical chemistry, my dear students. Class 11th physical chemistry it's going to be. And as I promised you, I'll be starting exactly from the basics. I'll be starting exactly from the scratch. Okay, I'll imagine as if you guys have never studied your physical chemistry before. Okay, so right from the scratch, from the basics, I'll be starting. All right. So the first chapter with which we shall be starting this particular marathon today, the first chapter in your class 11th physical chemistry, that is your epic mole concept. Yeah, the most phobic chapter of the students. But I'll make sure after watching this particular session, you should be in a position to solve each and every question from your mole concept, from your redox, from your atomic structure, from your equilibrium, right? I'll make sure of that. But please and please do watch this particular session till the end and be with me till the end. Be with me till the end. Okay? So let's get going then. Let's get started with the first chapter of the today's session. And my dear students, the first chapter of the today's session is going to be what? It's going to be your mole concept. It is going to be your mole concept. So let's cover this mole concept right from the basics, right from the scratch. This is our chapter number 1. This is our chapter number 1. So first of all, the first and the basic terminology with which I shall be starting this particular chapter. What is that? All of you must be familiar with that. That is your atomic mass. My dear students, how do we exactly define the term atomic mass? If I ask you, atomic mass is nothing but it is the mass of one atom of an element. Atomic mass is nothing but it is defined as the mass of one atom of an element. For example, if I'm asking you what is the atomic mass of sodium, so technically I'm asking you what is the mass of one atom of sodium. If I ask you what is the atomic mass of fluorine, so technically I'm asking you what is the mass of one atom of fluorine. Atomic mass of magnesium, I'm asking you the mass of one atom of magnesium. So atomic mass is nothing but it is defined as the mass of one atom of an element. The mass of one atom of an element. Okay. So my dear students, the standard, the reference with which we compare the masses of different atoms. The standard or reference with which we compare the masses of different atoms. What is that standard? What is that reference? That reference is taken as 1 AMU. And let me tell you, this 1 AMU is also called as 1U, which is also called as 1D. And this AMU stands for the atomic mass unit. This U over here, it stands for the unified mass. And let me tell you, this D over here, it stands for the Dalton. So first of all, the standard, the reference with which we are going to compare the masses of different atoms, right? That standard is 1 AMU. You call it as 1U. You call it as 1D as well. Now the point is, how do we define this 1 AMU? In simple words, it is defined as 1/12 of the mass of carbon-12 atom. 1/12 of the mass of carbon-12 atom. And let me tell you, my dear students, this mass of carbon-12 atom, the mass of carbon-12 atom, if I talk about, mass of carbon-12 atom is how much? That is 1.99 into 10 raised power minus 23 grams. Now, if you know the mass of carbon-12 atom, just divide this mass of carbon-12 atom with this 12, the value comes out to be like this. 1.99 into 10 raised power minus 23 grams. When you divide it with 12, the value exactly comes out to be 1.66 into 10 raised power minus 24 grams. And let me tell you, in terms of Avogadro's number, you are going to write it as 1 divided by Na grams. So first of all, what is atomic mass? Atomic mass is nothing but it is defined as the mass of one atom of an element. Mass of one atom of an element. The standard, the reference with which we are going to compare the masses of different atoms, that standard, that reference is your 1 AMU. You call it as 1U, you can call it as 1D as well. How do we define it? It is defined as 1/12 of mass of carbon-12 atom. Its value in grams is nothing but 1.66 into 10 raised power minus 23 minus 24 grams. In terms of Avogadro's number, you are going to write it as 1 divided by Na. Now, my dear students, try to understand what exactly I'm going to say. For example, I'm writing a term here. Let's say I'm writing a term, atomic mass of nitrogen. For example, I'm writing a term here, atomic mass of nitrogen. All of you must be familiar with the fact that the atomic mass of nitrogen is nothing but it is 14 AMU. It is 14 AMU, right? My dear students, this 14 AMU, you can write it as 14 multiplied by 1 AMU. Absolutely, you can do that. 14 I can write as such, and instead of 1 AMU, I can write 1 by 12th of mass of carbon to an atom. Again, 14 I can write as such, instead of 1 AMU, I can write 1.66 into 10 raised power minus 24 grams. Again, 14 I can write as such, instead of 1 AMU, I can write 1 divided by Na grams. So basically, what is the meaning of all these terms? What is the meaning of all these terms? I'm writing the term atomic mass of nitrogen. That means I'm talking about the mass of one atom of nitrogen. And my dear students, the mass of one atom of nitrogen is how much? 14 AMU. It means that one atom of nitrogen is 14 times heavier than 1 AMU. One atom of nitrogen is 14 times heavier than 1/12 of mass of carbon to an atom. If you would ask me, what is the mass of one nitrogen atom in grams? I'll say this term, it is the mass of one nitrogen atom in grams. Even this is the mass of one nitrogen atom in grams. Even this is the mass of one nitrogen atom, but in AMU. This is the mass of one nitrogen atom in AMU. This is the mass of one nitrogen atom in grams. Even this is the mass of one nitrogen atom in grams. Okay? I believe this is clear. Let me write one more statement to make things more clear to you. For example, if I write atomic mass of oxygen. Atomic mass of oxygen, what does that mean? In short, I would say it means that we are talking about the mass of one atom of oxygen. It means that we are talking about the mass of one atom of oxygen. And you must be familiar with the fact it is nothing but 16 AMU. 16 AMU you can break as 16 multiplied by 1 AMU. And my dear students, in place of 1 AMU, you can write 1 by 12 of mass of carbon to an atom. And in place of 1 AMU, you can again write 1.66 into 10 raised power minus 24 grams. And in place of the same 1 AMU, you can write 1 divided by Na grams. I believe this is super clear to you, right? Perfect. Now, my dear students, if you ask me what kind of information this atomic mass gives me, I would say atomic mass gives an idea. Atomic mass gives an idea about how many times an atom of an element is heavier than 1 AMU. Right? As you saw here, one atom of oxygen is 16 times heavier than 1 AMU. One atom of nitrogen is 14 times heavier than 1 AMU. Similarly, one atom of sodium is 23 times heavier than 1 AMU. So atomic mass just tells you about one thing. How many times an atom of an element is heavier than 1 AMU. In short. Okay. Now, my dear students, there are few important things which I want you guys to take a note of, which I want you guys to remember. For example, if I talk about sodium, what is the atomic mass of sodium? You should know it. It is 23 AMU. So the first term which I have mentioned over here, that is 23 AMU. Now, the second term that I'm going to mention, that is just going to be 23. I'm not going to write any unit with it, just 23. No unit with it. The third term, my dear students, which I'm going to write, instead of 23 AMU, I can write 23 into 1 AMU. And instead of that 1 AMU, I can write 1.66 into 10 raised power minus 24 grams. So for sodium, how many terms I've mentioned? I've mentioned 3 terms. My dear students, this first term is what I'll be simply calling as atomic mass of sodium. This particular term, without the units, I'll be calling it as the relative atomic mass of sodium. The relative atomic mass of sodium. And this particular term, my dear students, this I would be calling as the actual mass of sodium. This I'll be calling as the actual mass of sodium. Perfect. I want you guys to remember these three terminologies. First, 23 AMU. Second, just 23. Third, 23 multiplied by 1.66 into 10 raised power minus 24 grams. Similarly, you can take any other element. For example, let me take magnesium into consideration. The first term about magnesium I can write as 24 AMU. Second term is just going to be 24. Third term is going to be 24 into 1.66 into 10 raised power minus 24 grams. Right? My dear students, this is the atomic mass of magnesium. This is the relative atomic mass of magnesium. This is what I'll be calling as the actual mass of magnesium. Perfect. Done. Done, people. Is this particular terminology clear? One more important statement which I want you guys to take a note of. One more important statement. Remember that directly. What is that? My dear students, on changing the scale, actual mass of the substance does not change. Actual mass of the substance, it does not change. What does that mean? You'll get the idea in some time when I'll be solving the questions, right? So first of all, what is my scale? My scale is, I've told you that let's define 1 AMU as 1 by 12th of mass of carbon-12 atom. That's my scale. I'm defining 1 AMU as 1 by 12th of mass of carbon-12 atom. Now, what if 1 AMU is defined as 1/6 of mass of carbon-12 atom? What if 1 AMU is defined as 1/24th of the mass of carbon-12 atom? What will happen to the actual mass of the element? I would say actual mass, nothing happens to that. Remember, on changing the scale, actual mass of the substance remains unchanged. It does not change at all. Okay. Now, the second terminology which we have here, what is that? That's what you call as molecular mass. That's what you call as the molecular mass. Now, my dear students, how do we exactly define the term molecular mass? How do we exactly define the term molecular mass? Molecular mass is nothing but it is defined as, in short, I'm writing it, the mass of one molecule of the substance. The mass of one molecule of the substance, or you can say it is the sum of atomic masses. It is the sum of atomic masses of all the atoms. Of all the atoms. Of all the atoms. In case of your molecule. For example, take the case of water. Take the case of water. I want you to calculate the molecular mass of water. I want you to calculate the molecular mass of water. That means technically, I'm asking you to calculate the mass of one molecule of water. Molecular mass of water means mass of one molecule of water. Molecular mass of glucose means mass of one molecule of glucose. Molecular mass of ammonia means mass of one molecule of ammonia. So in short, molecular mass is nothing but mass of one molecule of a substance. Right? The point is, how do we calculate it? Simple, one thing. In case of water, how many elements do you see? I can see two elements, hydrogen and oxygen. What is the atomic mass of hydrogen? 1 AMU. How many hydrogen atoms we have? 2. Plus, what is the atomic mass of oxygen? 16 AMU. How many oxygen atoms we have? 1. The value comes out to be 18. Now you can write either AMU or U or D. But let me tell you, in case of molecules, preferably we write U. In case of molecules, preferably we write U. Okay. Similarly, my dear students, this 18U I can break as 18 multiplied by 1U. And instead of 1U, I can write 1 by 12th of mass of carbon-12 atom. And instead of the same 1U, I can write 1.66 into 10 raised power minus 24 grams. And instead of same 1U, I can write 1 divided by Na grams as well. I can write 1 divided by Na grams as well. So, I would say molecular mass of water. The mass of one molecule of water is nothing but 18U. So, one molecule of water is 18 times heavier than 1U. It is 18 times heavier than 1/12th of mass of carbon-12 atom. This is the mass of one water molecule in grams. Even this is the mass of one water molecule in grams. Right? My dear students, take the case of glucose. Take the case of glucose. Take the case of glucose. I am asking you to calculate the molecular mass of glucose. I'm asking you to calculate the molecular mass of glucose. So technically, I'm asking you to calculate the mass of one molecule of glucose. Right? How do we do it? Just do one thing. Sum of the atomic masses. Nothing else. Sum of the atomic masses. Carbon. What is the atomic mass? 12. How many carbon atoms? 6. Plus. Hydrogen, what is the atomic mass? 1. How many hydrogen atoms? 12. Oxygen, what is the atomic mass? 16. How many oxygen atoms? 6. When you solve it, the value comes out to be 180U. Or you can write it as 180 multiplied by 1U. And instead of that 1U, you can write 1 by 12th of mass of carbon 12 atom. Again, instead of 1U, you can write 1.66 into 10 raised power minus 24 grams. Again, instead of 1U, you can write 1 divided by Avogadro's number in grams. Perfect. So, you should just remember one thing. This is the molecular mass of water. Sorry, this is the molecular mass of glucose. So, it is the mass of one molecule of glucose. Or you can say, one molecule of glucose is 180 times heavier than 1U. 180 times heavier than 1/12 of mass of carbon 12 atom. Even I would say this is the mass of one glucose molecule in grams. Even this is the mass of one glucose molecule in grams. Right? Now, let me summarize few things which you must know. Let me summarize few things which you must know. My dear students, for example, I'm writing N here. Here I'm writing N2. On one side, I wrote N. On another side, I wrote N2. What is the difference? See, this is nitrogen. Even this is nitrogen. But this is the atomic form of nitrogen. This is the atomic form of nitrogen. And let me tell you, this is nothing but it is the molecular form of nitrogen. It is the molecular form of nitrogen. Now, let me tell you a few things. The first term about nitrogen is your 14 AMU. The second term is just 14. The third term is 14 multiplied by 1.66 into 10 raised power minus 24 grams. For N2, 14 into 2 comes out to be 28U. The second term is just going to be 28. The third term is going to be 28 into 1.66 into 10 raised power minus 24 grams. Now, if I ask you, what is the meaning of all this? What are the names given to all these terminologies? You will say this is nothing but it is the atomic mass of nitrogen. This is the relative atomic mass of nitrogen. This is the actual mass of nitrogen. Actual mass of N, right? Actual mass of N. This is what I call as molecular mass of nitrogen. Molecular mass of nitrogen. This is what I call as relative molecular mass of nitrogen. Relative molecular mass. This is what I'll be calling as actual mass. But is it the actual mass of N or N2? This is the actual mass of N2. Got it? Got it, people? Now. The first question that's on your screen. If 1U is defined as 1 by 24th of the mass of carbon 12 atom, calculate the molecular mass of carbon dioxide on new scale. Also calculate the actual mass of carbon dioxide. See guys, understand. First of all, how do we define 1U? We define 1U as 1 by 12th of the mass of carbon 12 atom. We define 1U as 1 by 12th of the mass of carbon 12 atom. In the question, how they have defined 1U, I'll be calling that as 1U dash. In the question, they have defined 1U as 1 by 24th of the mass of carbon 12 atom. Right? Now, my dear students, let me call this as equation number 1. Let me call this as equation number 2. The first thing which I'll be doing here, what is that? I'll be dividing the two equations. I just have to divide the two equations. Either 1 by 2 or 2 by 1. Choice is yours. For example, I'm dividing equation 1 with equation 2. When I divide equation 1 with equation 2, this term gets cancelled out. I will get something like this. 1U divided by 1U dash. So I can write U divided by U dash is equal to. In the numerator, you have got 1 by 12. In the denominator, you have got 1 by 24. The value comes out to be 2. 24 goes out. Value comes out to be 2. So I can say U divided by U dash is equal to 2, which tells you that U is equal to 2 times U dash. So my first point is clear. I got the relation between U and U dash. I got the relation between U and U dash. Now, my dear students, what am I supposed to calculate? I need to calculate the molecular mass of carbon dioxide. First of all, what is the molecular mass of carbon dioxide as per our scale? Our scale means U. Our scale is this one. This is the scale which is given in the question. This is our scale. This is the scale as per question. What is the molecular mass of carbon dioxide as per our scale? It is going to be simply carbon is 12 into 1. Oxygen means 16 multiplied by 2. The value comes out to be 44U. This is the molecular mass of carbon dioxide as per our scale. As per our scale. But I'm not supposed to calculate the molecular mass of carbon dioxide in terms of U. I want to calculate the molecular mass of carbon dioxide in terms of U dash. So what am I supposed to do? 44. Instead of U, I've already got the relation. U is equal to 2 times U dash. So instead of U, I can write 2 times U dash. The value comes out to be 88 U dash. So this is the new molecular mass of carbon dioxide. This is the new molecular mass of carbon dioxide. So I can say just one thing. Since I changed the scale, so molecular mass automatically changed, right? But on changing the scale, does anything happen to actual mass? No. I'll say actual mass of the carbon dioxide will remain unchanged. Actual mass of carbon dioxide will remain unchanged. That's always going to be 44 into 1.66 into 10 raised power minus 24 grams. This is always going to be the actual mass of carbon dioxide, irrespective of the fact what is the scale. I believe this is clear to everyone. Yes? Am I clear, people? Everyone in the chats once? Everyone in the chats quick? I believe I'm clear with all these things. This is a similar type of the question. This can be, you can take this as the homework, right? Similar type of question. You can take this as the homework. Make 2 equations, divide the 2 equations, get the relation between U and U dash, and then do it. Right? This is the homework question which I'm giving you. Now, my dear students, there is one more term that's again important. What is that? That is molar mass. How do we define the molar mass of the substance? Let me tell you, molar mass is nothing but, it is defined as the mass of 1 mole of the substance. The mass of 1 mole of the substance. Or I can say it like this. Molar mass is defined as the mass of 6.022 into 10 raised power 23. 6.022 into 10 raised power 23 particles of the substance. (6.022 into 10 raised power 23 particles of the substance. So technically, for example, I want to calculate molar mass of this marker. That means I want to know the mass of 1 mole of marker, which means that I want to know the mass of 6.022 into 10 raised power 23 markers. Do you understand? For example, I wanted to know the molar mass of carbon. That means I want to know the mass of 1 mole of carbon. That means I want to know the mass of 6.022 into 10 raised power 23 carbon atoms. Right? So whatever is going to be the mass of 1 mole of substance, whatever is going to be the mass of 6.022 into 10 raised power 23 particles of the substance, that is what you call as molar mass. Now, my dear students, let me just tell you one thing without wasting a lot of time. For example, talk about nitrogen again. If I ask you, what is the atomic mass of nitrogen? You will say 14 AMU. Now, if I ask you, what is the molar mass of nitrogen? You just have to do one thing. Remove AMU and instead of AMU, just write grams. Remove AMU and instead of AMU, just write grams. This is your atomic mass of nitrogen. This is the mass of 1 atom of nitrogen. And this is what you will be calling as the molar mass of nitrogen. Right? This is the mass of 1 mole of nitrogen. This is the mass of 6.022 into 10 raised power 23 nitrogen atoms. Understood? Understood, people? Am I clear with this? One more thing. Nitrogen here, I took in atomic form. Nitrogen here, I took in atomic form. You'll be calling molar mass as one more name. That is going to be the gram atomic mass. Either you call it as the molar mass of nitrogen, or you can call it as the gram atomic mass of nitrogen as well. Okay? For example, one more thing. Let's say I'm taking water. Okay? I'm taking water. What is the molecular mass of water? You know it already, 18U. Now, if I ask you what will be the molar mass of water, just replace U with grams. 18 grams is the molar mass of water. Right? This is the molecular mass of water. This is the molecular mass of water. But this is what I'll be calling as the molar mass of water. Or, just write it as such. Molar mass of water. For example, I'm writing O2. I have taken oxygen in molecular form. The first term which I'm writing 32U. And then I'm writing 32 grams. What is 32U? It is the molecular mass of oxygen. It is the molecular mass of oxygen. This is what you'll be calling as molar mass of oxygen. Molar mass of oxygen. Or one more thing, my dear students. O2. Oxygen here is in molecular form. If oxygen is in molecular form, then let me tell you, in place of molar mass, you can write gram molecular mass as well. This is the gram molecular mass of oxygen as well. I believe all these things are super clear to you, right? Yes? I believe all these things are super clear to you. Perfect? Perfect, people. Let me know once in the chats quick. Everyone. Everyone in the chats quickly. I hope you got to know the meaning of all these terminologies. Yeah? Now, my dear students, one more thing. One more thing. Remember this particular thing. Can I say molar mass of the substance? Or leave the substance aside. Let me write molar mass of X. X can be anything. Let's say X is some element. Let's say X is some element. Let's say X is some element. Molar mass of X. Molar mass of element X. That means we are talking about the mass of 1 mole of X. That means we are talking about the mass of 6.022 into 10 raised power 23 atoms of X. We are talking about the mass of 6.022 into 10 raised power 23 atoms of X. Now, how can I write it? I'll be just writing it like this. I'll write it is nothing but it is mass of 1 atom of X. Mass of 1 atom of X in grams. Mass of 1 atom of X in grams. Multiply that with Avogadro's number. Mass of 1 atom of X. Mass of 1 atom of X multiplied by Avogadro's number. That gives me the mass of 6.022 into 10 raised power 23 atoms of X, which is what I'll be calling as molar mass of X. Right? Am I clear, people? Am I clear? Am I clear? Let me know once in the chats. Everyone. Everyone, people. Quickly. Quickly, let me know in the chats. Everyone. Okay? So remember, molar mass of X is nothing but it is the mass of 1 atom of element X multiplied by Avogadro's number. That's going to give me the molar mass of element X. For example, one simple question I'm giving you here. My dear students, the mass of 1 atom, the mass of 1 atom of element X is 4 into 10 raised power minus 23 grams. I'm asking you to identify the element. I'm asking you to identify the element. Can you do that? I'm asking you to identify the element. The mass of 1 atom of an element, I'm giving you. I'm giving you the mass of 1 atom of element. I'm asking you, identify the element. Which element this is? What do we have to do? What do we have to do? My dear students, pretty much simple. If you know the mass of 1 atom of element, then that means you can calculate the molar mass of element. I can say molar mass of X is nothing but mass of 1 atom of X multiplied by Avogadro's number. Multiplied by Avogadro's number. So the value comes out to be 24 grams. So if the molar mass of element is 24 grams, if the molar mass of element is 24 grams, that means atomic mass of element is 24 AMU. And 24 AMU. Which element is there which has got atomic mass of 24 AMU? That is magnesium. So element is magnesium. As simple as that. Right? For example, I'm asking you a question. What is the molar mass of electron? Calculate the molar mass of electron. Let's say this is something I'm asking you. Molar mass of electron. That means if I want to know the molar mass of electron will be nothing but it will be mass of 1 electron in grams. Mass of 1 electron in grams. Multiply it with Avogadro's number. You'll be getting the molar mass of electron. Right? Now, what is the mass of 1 electron? It is 9.1 into 10 raised power minus 28 grams multiplied by Avogadro's number is 6 into 10 raised power 23. Just a bit of calculation is needed and you are done. You are sorted. How much will it be? It will be 54.6 into 10 raised power minus 5 grams. Okay, this is the molar mass of electron. That means this is the mass of 1 mole of electron. This is the mass of 6.022 into 10 raised power 23 electrons. As simple as that. Got it? Now, my dear students, then one more terminology which we have. What is that? That is average atomic mass of an isotopic mixture. Average atomic mass of an isotopic mixture. First of all, you should know what are isotopes. You should know, first of all, what are isotopes. My dear students, if I particularly talk about isotopes, isotopes are nothing but, these are the atoms. These are the atoms of same element. These are the atoms of same element, having same atomic number. Having same atomic number, but different atomic masses. Isotopes are nothing but, these are the atoms of same element, having same atomic number, but different atomic masses. For example, talk about your hydrogen. If you know about hydrogen, hydrogen has got 3 atoms having same atomic number. But their mass numbers are different. 1, 2, 3. Can I say these are the atoms of same element, having same atomic number, but different atomic masses? So I'll be calling them directly as isotopes. So these are the isotopes of hydrogen. Talk about your chlorine. You must be knowing chlorine has got 2 atoms, which have got same atomic number, but their atomic masses are different, 35, 37. So can I say these are the atoms of chlorine, having same atomic number, but different atomic masses? So again, I'll be calling them as the isotopes of chlorine. Again, I'll be calling them as the isotopes of chlorine, right? Again, I'll be calling them as isotopes of chlorine. Now, my dear students, let's try to understand. Let's try to understand few things. See, guys. For example, imagine that you are taking an element X. Imagine that you are taking an element X. My dear students, for example, this X has got, just a second, let me write it somewhere here. For example, I'm taking an element X. I'm assuming that this X has got 2 isotopes. This X has got 2 isotopes. That means this X has 2 atoms with same atomic number but different mass numbers, M1 and M2. Now, people, let me tell you one thing. Whenever you see an element having isotopes, for that particular element, we define a new term called as average atomic mass. So first of all, average atomic mass, it is defined for that element which has isotopes. So I have taken the element X. It has got 2 atoms which have got same atomic number but different mass numbers. So these are the isotopes of this X. Whenever the element has isotopes, at that point of time, we define average atomic mass of an element. Right? And average atomic mass we represent with MAV. Now the point is, in order to calculate the average atomic mass, what do we need? Let me tell you, in order to calculate the average atomic mass, you need percentage abundances of these isotopes. And you can call the percentage abundances as mole percent as well. Let me tell you, my dear students, in order to calculate the average atomic mass of an element, what do we need? We need the percentage abundances of the isotopes. And let me tell you, percentage abundances of the isotopes are represented by A% and B%. What is meant by percentage abundance? You'll get the idea in some time. Yeah? Right? Right, people? Okay. So what is meant by percentage abundance? I'll let you know about that in some time. So first of all, I've got an element X. This element has got 2 isotopes. Whenever the element has isotopes, we calculate average atomic mass for that element. In order to calculate average atomic mass, we need percentage abundance of the isotopes. And if you have percentage abundance of the isotopes, then you have got one direct formula. That is M1A multiplied by M2B divided by A plus B. This is the formula with the help of which you can calculate the average atomic mass of an element. This is the formula by means of which you can calculate the average atomic mass of an element. Okay. And my dear students, let me tell you one more thing. Remember one more thing. The sum of percentage abundances of all the isotopes. The sum of percentage abundances of all the isotopes of a particular element. it is always equal to 100. So remember, this A plus B value will be always equal to 100. Now let me make you understand what all of this means. Let me make you understand what all of this means. Have a look, guys, what I'm trying to do. Understand properly. For example, you've got the element chlorine. I'm assuming this chlorine has got two isotopes. If chlorine has two isotopes, that means their atomic number will be same, but their atomic masses will be different, 35, 37. Now, my dear students, I am telling you that the percentage abundances of these two isotopes are 75% and 25% respectively. And I am asking you to calculate the average atomic mass of chlorine. This is my question. This is my question. We have got the element chlorine. It has got two isotopes. The percentage abundances of these isotopes are given to me. And I want you to calculate the average atomic mass of chlorine. First of all, what is meant by this 75%, 25%? It means that out of all the chlorine existing in nature, out of all the chlorine which we have, 75% of the chlorine will be existing in the form of Cl35 and 25% of the chlorine will be existing in the form of Cl37. What does that mean again? For example, imagine in this particular room there are total 100 chlorine atoms. Imagine in this particular room, right now there are some 100 chlorine atoms. Out of those 100 chlorine atoms, some chlorine atoms will be Cl35 and some chlorine atoms will be Cl37, right? Now let me tell you, this data is telling me that 75 chlorine atoms in this room will be Cl35 ones. And remaining 25 chlorine atoms will be which ones? They'll be Cl37. Do you understand? Now, my dear students, what do I need to calculate? Average atomic mass. Now, in order to calculate average atomic mass, I got all the data. This is the value of A. This is the value of B. This is the value of M1. This is the value of M2. You can just use the formula. M1 multiplied by A plus M2 multiplied by B divided by A plus B. So what is the value of M1? M1 is 35. What is the value of A? A value is 75. What is the value of M2? That is 37. What is the value of B? That is 25. Divided by A plus B will directly come out to be 100. When you solve this, the value is going to be 35.5 AMU. So this is the average atomic mass of chlorine. This is the average atomic mass of chlorine, my dear students. Yeah? Let's try to solve one more question. For example, I'm giving you the question. Let's say you've got the element boron. You've got the element boron, for example. For example, you've got the element boron. Boron has two isotopes, B10 and B11. B10 and B11. I am giving you the percentage abundance of B10. Let that be 19%. Let that be 19%. I want you to calculate average atomic mass of boron. Now, my dear students, how do I calculate average atomic mass of boron? Understand properly. See, boron has two isotopes. Boron has two isotopes. I told you a few minutes back, the sum of percentage abundances, of all the isotopes of a particular element, that's always 100, right? Now, if the percentage abundance of the first isotope is 19%, that means the percentage abundance of the second isotope will be 100 minus 19. 100 minus 19 means 81%, right? So technically, this is the value of A here. This is the value of B. This is the value of your M1. This is the value of your M2. So M average is nothing but it is M1A plus M2B divided by A plus B value is always 100. So what is M1? 10 into 19. 10 into 19 plus what is the value of M2? 11 into 81. 11 into 81 divided by A plus B is always 100. When you solve this, the value comes out to be 10.81 AMU. So this is the average atomic mass of boron here. This is the average atomic mass of boron. I hope you got to know how do we calculate the average atomic masses. Now, my dear students, there is one conclusion which you can make over here. Understand. What is the average atomic mass of chlorine here? Average atomic mass of chlorine came out to be 35.5. Average atomic mass of chlorine came out to be 35.5. Now, if I ask you, is 35.5 closer to this value or this value? 35.5. Is it closer to 35 or is it closer to 37? I would say this 35.5, it is closer to this value, 35. And look at this isotope. Its abundance is minimum or maximum? Its abundance is maximum. Look here. What is the average atomic mass of boron? 10.81. 10.81 is closer to 10 or 11. 10.81 is closer to 11. And look at its abundance. Is it minimum or maximum? It is maximum. So remember one simple thing. The average atomic mass will be closer to the atomic mass of that isotope whose abundance is maximum. Correct? I believe it's done. For example, I'm giving you one more question. My dear students, for example, you have got an element magnesium. And I am telling you that this magnesium has got 3 isotopes. One is your Mg24, one is your Mg25, and one is your Mg26. Magnesium has got 3 isotopes, Mg24, Mg25, Mg26. Now people, for example, the percentage abundance of Mg24 is, for example, 79%. And the average atomic mass of magnesium is nothing but it is 24.31 AMU. It is 24.31 AMU. I am asking you to calculate the percentage abundance of these 2 isotopes. I am asking you the percentage abundance of these 2 isotopes. How do we do it? Tell me just one thing. Magnesium has how many isotopes? 3. The sum of percentage abundances of all these 3 isotopes will be 100. That will be 100. Out of 100, the abundance of the first isotope is how much? 79. Out of total 100, the abundance of this isotope is 79. So how much is remaining? 100 minus 79. That is 21. That is 21, right? That's 21. So 21, is that 21 the percentage abundance of this, or the percentage abundance of both? That 21% is the abundance of these 2 combinedly. So let's assume out of 21, the abundance of this isotope is X. So abundance of this isotope has to be 21 minus X. I hope this particular point is clear. Yeah? So if the percentage abundance of first isotope is 79, so remaining is 21. Out of that 21, let the abundance of this isotope is X. Therefore, the abundance of this isotope will be 21 minus X. Correct? Now, this is the value of your M1, this is the value of your M2, this is the value of your M3. This is A, this is B, this is C. So I can use the formula. I can say M1A plus M2B plus M3C divided by A plus B plus C is always 100. And this value as per the question is nothing but 24.3 here. What is M1? M1 is 24. What is the value of A? A value is 79. M2 value 25. B value is X. M3 value 26. C value 21 minus X divided by A plus B plus C is 100. As per the question, the value is 24.31. When you do the cross multiplication here, you will be getting the value of X as 11%. And what was this X? X was the percentage abundance of Mg25. So it came out to be 11%. So this automatically is going to be 21 minus X. 21 minus 11. That comes out to be 10%. So these were the 2 things which I was supposed to calculate. I believe all of this is super clear to everyone. If yes, let me know once in the chats. Yeah? Right, people? Are we clear with this? Quickly in the chats, everyone. Everyone. Quick. Are we clear with all of this? Perfect, guys. Now the point is, how do we do the calculation of moles? Sir, can you teach faster? I'm already teaching very fast. You have no idea. Whatever things I've taught you till then, in the normal classes, I take like, surely some 2 hours to complete all this. More than that. Okay, is it clear? You don't worry, I'm going on a good pace. Don't worry about it. All right, people. So how do we do the calculation of moles? Let me tell you, in order to calculate the moles of any substance, number of moles of the substance, which we represent with N. Let me tell you, number of moles of the substance, the first formula is given mass of the substance in grams divided by the molar mass of the substance. Divided by the molar mass of the substance. Given mass of the substance divided by the molar mass of the substance. You can write grams per mole here also. Okay, this is the first formula which is valid for solids, liquids as well as gases. First formula which is valid for solids, liquids as well as gases. So my dear students, number of moles of the substance which we represent with N is equal to given mass of the substance divided by molar mass of the substance. There is one more formula, that is number of moles of the substance is equal to given number of particles divided by Avogadro's number. This is one more result with the help of which you can calculate what exactly? You can calculate number of moles of the substance. Given number of particles divided by Avogadro's number. Now, there is one more result. To calculate moles. Moles of what? Moles of gas. And the gas has to be present at STP, standard temperature pressure. And this formula is nothing but, it is given volume of the gas in liters divided by 22.4 liters. Now, for example, if the given volume of the gas is not in liters, for example, that is in ml. So I'll be dividing with 22400 ml. Okay. So these are some results which you need to remember to calculate the moles of the substance. Given mass divided by molar mass. Given number of particles divided by Avogadro's number. Given volume of the gas in liters divided by 22.4 liters. Right? Okay. Remember, this particular result is only valid for gases. But these two results are valid for both. For all solids, liquids as well as gases. Okay. And if the condition is not STP mentioned, then you have to use the ideal gas equation to calculate the moles of the gas. And you can say N is equal to PV divided by RT. N is equal to PV divided by RT. Number of moles of the gas at any condition apart from STP will be equal to PV divided by RT. T is the pressure of the gas that will be given to me. P is the volume of the gas that will be given to me. T is the temperature of the gas. And this R is a universal gas constant. And let me tell you, it has got three values. One is 8.314 joules per Kelvin per mole. For calculation purpose, you can take 25 by 3. Its one more value is 0.0821 atm liter per Kelvin per mole. For calculation purpose, you can take it as 1 by 12. And its one more value is 1.98 calories per Kelvin per mole. Again, for calculation purpose, you can take it as 2. So remember all of this. And my dear students, if you can remember all of this, then you can tell me the answer of all these simple questions. How exactly? See. Calculate the number of moles in 160 grams of NaOH. 160 grams of NaOH. We are given with the mass of NaOH. We are supposed to calculate number of moles of NaOH. I'll say number of moles of NaOH will be given mass of NaOH divided by what would be the molar mass of NaOH? Quickly tell me. Sodium has got 23, oxygen has got 16, hydrogen has got 1. Take the sum of all this, the value comes out to be 40. So 40 grams is the molar mass of NaOH. So the value comes out to be 4. So 160 grams of NaOH means we have got 4 moles of NaOH. Simple. Number of moles in 67.2 liters of carbon dioxide gas. If you look carefully, here we are given with the volume of the gas and we are supposed to calculate moles. So given volume divided by 22.4. So I would say number of moles of carbon dioxide is equal to given volume of the gas in liters divided by 22.4 liters. The value comes out to be 3. Here if you can see, we are given with the atoms of carbon. So technically we are given with the particles. So number of moles of carbon will be equal to given number of particles divided by Avogadro's number. Divided by Avogadro's number. The value comes out to be 4. Again here we are given with the molecules of water. That means particles of water. So calculate moles. Number of moles of water will be equal to given number of particles divided by Avogadro's number, right? The value comes out to be 80. Perfect. I'm just showing you how do you use all these formulas. Perfect. Now, my dear students, for example, let's say I'm given with 16 AMU of helium. 16 AMU of helium. And they are asking me to calculate the moles. 16 AMU of helium. So here, if you look carefully, the mass is not in grams. The mass is not given in grams. The mass is given in AMU. If the mass was in grams, then given mass divided by molar mass. Given mass of substance in grams divided by molar mass of substance. That gives me moles. But what if mass is not in grams? Mass is in AMU. Then we have to convert it in grams first. So 16 AMU I can write as 16 into, instead of AMU, I can write 1 by Na grams. So what you have done? You have converted. You have converted AMU into grams. Now, I can say number of moles of helium will be equal to given mass of helium in grams, given mass of helium in grams, divided by molar mass of helium. And molar mass of helium is 4 grams. The value comes out to be 4 by Na. The value comes out to be 4 by Na. As simple as that. So if the mass is not in grams, if it is in AMU, then convert in grams first, then divide that with the molar mass. Perfect. Now guys, how can we solve some simple questions based on mole? How can we solve some simple basic questions based on mole? I'm over here going to give you one simple diagram, mole conversion diagram, which you have to remember. You can solve some basic questions of mole in very lesser time. What is that formula? See guys. First of all, as I told you, in order to calculate the moles, either I should be given with the mass of the substance, or I should be given with the number of particles of the substance, or I should be given with the volume of the gas in liters at STP. Now tell me just one thing. Just one thing. If mass is given and moles are to be calculated, then what do we have to do? Given mass divided by molar mass. Given mass divided by molar mass gives me moles. Or if moles are given, mass is to be calculated. Then moles are to be multiplied with molar mass. Moles are to be multiplied with the molar mass of the substance, you get mass. Simple, just the reverse of it. If you are given with number of particles, you are supposed to calculate what? Moles. Given number of particles divided by Avogadro's number. That gives me moles. Now reverse. If moles are given, particles are to be calculated. Then moles multiplied by Avogadro's number will give me the particles. Similarly, if volume is given, moles are to be calculated. Then what do we have to do? Given volume divided by 22.4 liters. That gives me moles. If moles are given, volume is to be calculated. Then moles are to be multiplied with 22.4 liters. Then you will get the volume. Right? This is one simple result which you have to remember, guys. Okay. Now, why am I giving you this result? See, for example, in some question, they'll give you mass. And they'll ask you to calculate particles. So you'll be starting from mass. And you will have to reach to particles. Is there any direct arrow between mass and particles? No, there is no direct arrow between mass and particles. So you will be following all the arrows which are going to take you from mass till particles. You are going to follow all the arrows which are going to take you from mass till the particles. Now you tell me which all arrows you have to follow to go from mass till particles. So this will be my first arrow. Given mass divided by molar mass, that will give me moles. Then moles multiplied by Avogadro's number, that will give me particles. Simple. There will be some questions in which particles will be given and volume is to be calculated. Particles are given and volume is to be calculated. Then I'll be starting with particles. I'll have to reach to volume. Is there any direct arrow between the two? No. I'll have to start with particles. I'll have to reach till volume. Right? So I'll be following all the arrows which take me from particles till the volume. So which all arrows I'll be following in that particular case? Given number of particles divided by Avogadro's number. That will give me moles. Then moles multiplied by 22.4 liters. That will give me volume. Okay. So my dear students, for example, tell me the answer of this question. I'm giving you 67.2 liters of carbon dioxide gas at STP. I'm asking you how many molecules will be there. How many molecules will be present in 67.2 liters of carbon dioxide gas? Tell me quick. See, first of all, what am I given with and what am I supposed to calculate? Check first of all. What am I given with and what am I supposed to calculate? Check it out carefully. Check it out carefully. I'm given with volume. I'm supposed to calculate molecules, right? I'm given with volume. I'm supposed to calculate molecules. So I'm given with volume. I'm supposed to calculate molecules. Molecules means particles. So I'll be starting from volume and I have to reach till particles. So I'll be following all the arrows which take me from volume till particles. Now, which all arrows I'll be following? Which all arrows I'll be following? Let me use some different color here. Which all arrows I'll be following? I'll have to start with volume. So given volume divided by 22.4 liters. That gives me moles. Then moles multiplied by 22.4 liters. That gives me, moles multiplied by Avogadro's number. That gives me the particles. So I'm going to solve this question in just 2 steps. The first step is given volume divided by 22.4. That gives me moles. So my first step is calculation of moles. Moles of carbon dioxide. Given volume of the gas in liters divided by 22.4. The value comes out to be 3. Now, I got the moles. Moles multiplied by Avogadro's number. That gives me the particles. Particles means molecules here. So molecules of carbon dioxide will be moles multiplied by Avogadro's number. So 3 multiplied by Na. So this is the answer of the question. Simple. Right? This is the answer of the question. You can keep it as 3Na directly. Perfectly done? Perfectly done, people? Perfectly done? Tell me one thing. Tell me one thing. Tell me if I, for example, give you something like this. I'm giving you 128 grams of SO2 gas at STP. I'm asking you, what is going to be its volume? What is going to be its volume? Tell me. I'm giving you mass. I'm asking you to calculate volume. Mass is given, volume is to be calculated. Mass is given, volume is to be calculated. Start from mass and reach volume. Follow all the arrows which take you from mass till volume. So, my first step is given mass divided by molar mass. That gives me moles. So, number of moles of SO2 will be equal to given mass divided by molar mass. The value comes out to be 2. Now, moles multiplied by 22.4. That gives me volume. So, volume of SO2 will be equal to moles multiplied by 22.4 liters. The value comes out to be 44.8 liters. I believe these sort of basic questions you can easily solve from now onwards. Okay. For example, I'm giving you a question like this. I'm telling you the mass of one atom of X is equal to 4 into 10 raised power minus 23 grams. How many moles are present in 96 grams of X? How many moles are present in 96 grams of X? I need to calculate the moles present in 96 grams of X. So I'm basically given with mass of X. I need to calculate moles. So number of moles of X is equal to given mass of X in grams divided by molar mass of X. What is the given mass of X as per question? That is 96 grams. Molar mass of X. I am not given with molar mass of X. I am not given with molar mass of X. I am given with mass of one atom of X. But we know how to get the molar mass. Molar mass of X is equal to mass of one atom of X multiplied by Avogadro's number. So what is the mass of one atom of X? 4 into 10 raised power minus 23 grams multiplied by Avogadro's number. So now this term is the molar mass. So this gets cancelled. The value comes out to be 96 divided by 6 for 24. 96 divided by 24 is 4. So I would say 96 grams of X means 4 moles of X. Understood? For example, I'm giving you one more question. This is again the asked question. It has been asked many a times in your JEE examination. How many moles of electrons? How many moles of electrons weighs 1 kg? Can you give it a try? How many moles of electrons weighs 1 kg? Again, you are given with mass, but mass is in kg. We need mass in grams. So 1 kg means 1000 grams. So we are given with mass of electron. We have to calculate moles of electron. So I would say number of moles of electron is equal to given mass of electron divided by molar mass of electron. Have we already calculated molar mass of electron? Do you remember? That was 54.6 into 10 raised power minus 5, I think, something around that. Something around that it was. Yeah. 28 minus 28, 10 raised power 23. Yeah. Something around that. So this is the number of moles of electron. Understood? So these basic questions, you can easily kill people. Okay. Okay. You might do a mistake in one question. Let me solve that too. I'm asking you to calculate the number of molecules in 1.8 liters of H2O liquid. 1.8 liters of H2O liquid, you are supposed to calculate molecules. Now, normal people will think that we are given with volume. We have to calculate molecules. We have to calculate particles. So what they will do? They'll divide the given volume with 22.4. They'll get the moles. Multiply that with the Avogadro's number. They'll get the molecules, right? But given volume divided by 22.4. Given volume divided by 22.4. That is only valid for gases. And the gas has to be at STP2. Is this gas or liquid? It is liquid. So you're not supposed to use that formula. So how do we solve this question? See, first of all, 1.8 liter water means 1800 ml of water. And since density of water is equal to 1 gram per ml, if density of water is 1 gram per ml, that means 1800 ml of water means 1800 grams of water. That means 1800 ml of water means 1800 grams of water, right? So, first step, number of moles of water will be equal to given mass of water in grams divided by molar mass of water. This value comes out to be 100. Because this is the universal formula. Given mass divided by molar mass. It is valid for solids, liquids, as well as gases. Right? So, my dear students, if you got moles, then moles are to be multiplied with Avogadro's number. You will be getting the molecules of water. So, molecules of water will be simply equal to 100 Ne. Done and dusted. Yeah? Perfectly done. I believe all this is clear. I believe all this is clear, guys. I believe all this is clear. Here, I have kept some homework questions as well. You can give them a try the similar way as we did. Okay. Now comes one more topic. What is that? That is your calculation of atoms, electrons, protons, neutrons, ions, valence electrons. From this particular topic, also questions are frequently asked. Now, how do we deal with such type of the questions, wherein you are supposed to calculate atoms, electrons, protons, neutrons, ions, valence electrons, etc., etc. My dear students, what you need to do is, I'll be again giving you one simple diagram. Just follow that. What is the diagram? Here I'm writing given quantity. Here I'm writing given quantity. Given quantity means whatever will be given to me in the question. Whatever will be given to me in the question. It can be mass, it can be particles, it can be volume, it can be anything. Whatever is given to me in the question, I'll be calling that as given quantity. Your first step always is going to be to convert the given quantity into moles. Your first step always is going to be to convert the given quantity into moles. Then, second step, moles are to be multiplied with Avogadro's number. Moles are to be multiplied with Avogadro's number. Now, let me tell you, in the question, if given substance is in molecular form, if the given substance is in molecular form, then remember, moles multiplied by Avogadro's number gives us what? Moles multiplied by Avogadro's number, it gives us molecules. So moles multiplied by Avogadro's number, it can give me the molecules. It can give me the molecules. And from the molecules, I can easily calculate atoms, electrons, protons, neutrons, ions, valence electrons, whatever things are asked in the question. All those things I can solve with the help of this particular diagram. Given quantity, convert that into moles. Moles multiplied by Avogadro's number. That will give me the molecules. if the given substance is in molecular form. If the given substance is in molecular form. And from molecules, you can easily calculate atoms, electrons, protons, neutrons, ions. How? That's something I'll tell you in some time. But before that, one more thing. If, for example, the given substance is in atomic form, if, for example, the given substance is in atomic form, if the given substance is not in molecular form, if it is in atomic form, then remember, moles multiplied by Avogadro's number, that gives you atoms. That gives you atoms. And for example, if the given substance is in ionic form, if the given substance is in ionic form, then remember, moles multiplied by Avogadro's number, that gives you ions directly. So these are few things which you need to take a note of. These are few things which you need to take a note of. Now. Let's exactly see how this sort of a question is asked and what all things can we conclude from here. How do we deal with such kind of the questions? Let's try to understand. Let's try to understand. For example, you have got one simple question. Okay, before solving the question, there is one more thing which I want to tell you here only, because I don't want to teach that separately. For example, I have got one molecule of carbon dioxide. One molecule of carbon dioxide. What all information you can write for carbon dioxide? What all information you know about one molecule of carbon dioxide? You can say one molecule of carbon dioxide contains one carbon atom. It contains two oxygen atoms. It contains two oxygen atoms, right? Or I can say in total, one molecule of carbon dioxide contains three atoms. In total, one molecule of carbon dioxide contains three atoms. Yeah? One molecule of carbon dioxide contains one carbon atom, two oxygen atoms, or I can say in total it contains three atoms. Now tell me, what about electrons, protons and neutrons, which are present in one molecule of carbon dioxide? If you talk about carbon dioxide, CO2, atomic number of carbon is 6, this is 12, this is 8, this is 16, this is 8, this is 16. Now, what is the atomic number of carbon? 6 plus. What is the atomic number of oxygen? 8. What is the atomic number of oxygen? 8. So 8, 8, 16, 6, 22. So there will be 22 electrons in one molecule of carbon dioxide. There will be 22 electrons in one molecule of carbon dioxide. There will be 22 electrons in one molecule of carbon dioxide. Similarly, how many protons? 22 protons as well. So whatever is the atomic number, you can calculate electrons as well as protons, right? Now, how do we calculate neutrons? Mass number minus atomic number. Mass number minus atomic number. 12 minus 6 is 6 plus 16 minus 8 is 8 plus 16 minus 8 is 8. Again, the value comes out to be 22. So, in one molecule carbon dioxide, there will be 22 electrons, 22 protons, as well as 22 neutrons. Yeah? Perfect? I believe I'm clear. Now, guys, try to understand. Let's modify this question. Calculate the number of atoms, also calculate the electrons, also calculate the protons, also calculate the neutrons present in 448 liters of carbon dioxide. So I'm showing all the things here in the same question only. My dear students, first thing, identify your given quantity. What are we given with? We are given with volume. We are given with volume. Our first step always is to convert the given quantity into moles. So first of all, number of moles of carbon dioxide will be equal to given volume of the gas in liters divided by 22.4 liters. The value comes out to be 20. So these are the moles. These are the moles. Second, moles multiplied by Avogadro's number. Second step, moles are to be multiplied with Avogadro's number. First step was convert the given quantity into moles. Second step, moles are to be multiplied with Avogadro's number. First of all, check the given substance. Is it in atomic form or molecular form? It is in molecular form. It is in molecular form. So moles multiplied by Avogadro's number. That gives me molecules here. So I got the molecules of carbon dioxide, which are present in 448 liters of carbon dioxide. I got the molecules of carbon dioxide. But do I need to calculate molecules? No, I have to calculate atoms. Now tell me one thing, a general information. General information. What about one molecule of carbon dioxide? Can I say one molecule of carbon dioxide contains one molecule of carbon dioxide? What does it contain? General information. One molecule of carbon dioxide contains three atoms. out of which there is one carbon atom and there are two oxygen atoms. There are two oxygen atoms, correct? One molecule of carbon dioxide contains 3 atoms, out of which one carbon and 2 oxygen atoms. Now we will think logically, if one molecule of carbon dioxide contains 3 atoms, if one molecule carbon dioxide contains 3 atoms, do we have one molecule of carbon dioxide with us? No. How many molecules we have? 20 Na. If one molecule carbon dioxide contains 3 atoms, I will say 20 Na molecules of carbon dioxide will contain 3 into 20. That means 60 Na atoms in total. 60 Na atoms in total. Out of which, how many are carbon? 1 into 20 comes out to be 20 Na carbon atoms. 20 Na carbon atoms. Similarly, 2 into 20 comes out to be 40. So it's going to be 40 Na oxygen atoms. So you did the calculation of atoms. Now, we are supposed to do the calculation of electrons, protons, as well as neutrons. Now, guys, you tell me one thing. If I ask you general information, in one molecule carbon dioxide, few minutes back we checked, in one molecule carbon dioxide, there are 22 electrons, there are 22 protons, even there are 22 neutrons in one molecule carbon dioxide. If in one molecule carbon dioxide, we have this much. Therefore, in 20 Na molecules of carbon dioxide, what will we have? 22 into 20. The value comes out to be 440 Na electrons, 440 Na protons, and 440 Na neutrons. I believe I'm clear with this. Yeah? Am I clear? Everyone in the chats? Everyone in the chats, people? Quickly. Let's solve one more question of the same type so that it becomes like very clear to you. For example, I'm giving you 170 grams of NH3. 170 grams of NH3. And I want you to calculate total number of atoms, electrons, protons, neutrons present in 170 grams of NH3. For example, we are given with 170 grams of NH3 and I want you to calculate the total number of atoms, the total electrons, protons, neutrons, right? Present in this. Can we do it? Sir, आपका रोजा नहीं है? Yes, I'm fasting already. रोजा है मेरा. इसलिए थोड़ा डिले करना पड़ा सेशन, इसलिए लेट किया मैंने सेशन स्टार्ट. Otherwise, the session was supposed to start at 10. Therefore, I started at 11. Okay, are we clear with this? The question is, calculate the total number of atoms, electrons, protons, neutrons present in 170 grams of NH3. Present in 170 grams of NH3. What is my first step always? Convert the given quantity into moles. So number of moles of NH3 will be equal to given mass of NH3 divided by molar mass of NH3. The value is 10. Second step, moles multiplied by Avogadro's number. Since the given substance is in molecular form, so moles multiplied by Avogadro's number, it gives me what? It gives me molecules. Molecules of what? Molecules of NH3. So I got the molecules of NH3. Kashmiri channel kal start ho rahi hai. Tomorrow it's starting. Tomorrow we are launching that. Okay, so I got the molecules of NH3, right? So I solved the question till here. Now tell me a general information. If I talk about one molecule of NH3, can I say in one molecule of NH3 there will be in total 3 plus 1, 4 atoms. In one molecule of NH3 there will be in total 4 atoms, out of which there is one nitrogen atom and 3 hydrogen atoms. One molecule of NH3 contains 4 atoms, out of which there is one nitrogen atom and 3 hydrogen atoms. Now you tell me one thing. If in one molecule of NH3 we have all this, therefore in 10 Na molecules of NH3, what do we have? 4 into 10 Na. That comes out to be 40 Na atoms. 1 into 10 Na comes out to be 10 Na nitrogen atoms. 3 into 10 Na comes out to be 30 Na hydrogen atoms. So I did the calculation of all the atoms here. Now. What about electrons, protons, neutrons? In order to do the calculation of electrons, protons, neutrons, I should know in one molecule of NH3. I should know in one molecule of NH3 how many electrons, protons, neutrons are there. So if I talk about NH3, this is your NH3, nitrogen 7, 14, 1, 1, 1, 1, 1, 1, right? Talk about electrons. Nitrogen 7 electrons, hydrogen 1, 1, 1. So there are total 10 electrons. Similarly, there will be total 10 protons. What about neutrons? 14 minus 7 is 7. 1 minus 1, 0, 1 minus 1, 0, 1 minus 1, 0. So there are 7 neutrons in one molecule NH3. So in one molecule NH3, there are total 10 electrons, there are 10 protons, and there are 7 neutrons. Now, if in one molecule NH3, we have got this much. Do we have only one molecule of NH3? No, we have got 10 Na molecules. So 10 Na molecules of NH3 will contain 10 into 10 Na, which comes out to be 100 Na electrons. Similarly, 100 Na protons. Similarly, 70 Na neutrons. I believe all of this is like very, very, very clear to you. Right? Break will be given at 1:15. 1:15. Now, my dear students, one more question I'm giving you. One more question I'm giving you. Calculate the valence electrons in 4.2 grams of N3 negative. Calculate the valence electrons in 4.2 grams of N3 negative. Now, first of all, if you look carefully, we are given with mass. Convert into moles first. So, number of moles of N3 negative is equal to given mass of N3 negative divided by what is the molar mass of nitrogen? That's 14. The value comes out to be 0.3. Moles we got. Now, moles multiplied by Avogadro's number. What does that give me? Given substance is in ionic form. So, these are the number of ions. So, total number of ions which we have is 0.3 Na. Right? Now, tell me one thing. Tell me one thing, guys. What are we supposed to calculate? Valence electrons? Tell me how many valence electrons will be there in one ion? How many valence electrons will be there in one ion of N3 negative? If I talk about N3 negative, atomic number 7, mass number 14. Correct? So nitrogen should have technically 7 electrons, but there is tri-negative charge. That means it has gained 3 electrons. So 7 plus 3 is 10. So in one ion of N tri-negative, there are 10 electrons. Out of 10 electrons, first 2 electrons will be in the first shell, and remaining 8 electrons will be in the second shell. And this second shell I'll be calling as valence shell, and electrons present in valence shell are called as valence electrons. So I can say one ion contains 8 valence electrons. Now, if one ion contains 8 valence electrons, 2 ions will contain multiplied by 2, 3 ions will have multiplied by 3, 4 ions multiplied by 4. How many ions we have? 0.3 Na. So 0.3 Na ions will be containing 8 into 0.3. The value comes out to be 2.4 Na valence electrons. Got it? Is it clear, people? Everyone in the chats once? Is it clear? Is it clear? Is it clear? Am I clear with all this? Everyone? Did you understand? Yeah? Everyone wants the chats. So same procedure, whatever I've been telling you, I'm following the same procedure in all the questions. Nothing else. Okay? For example, I'm writing one simple question. Calculate the atoms of oxygen in, or just leave this question for now. I have to tell you some more things before that. So I believe all the things are like very, very, very clear to you till now. Tell me the answer of all of this quickly. What do you think? स्ट्रक्चर ऑफ एटम स्टार्ट कीजिए. हाँ जी, मोल कौन सा भी यही छोड़ता हूँ, पहले स्ट्रक्चर ऑफ एटम पे आ जाता हूँ. Quickly, guys, what is going to be the answer of all of them? You should be in a position to solve this, people, on your own. See, calculate the atoms in 16 grams of helium. Atoms in 16 grams of helium. Convert the given quantity to moles. The number of moles of helium is equal to given mass divided by molar mass. The value comes out to be 4. Now, moles multiplied by Avogadro's number. Moles multiplied by Avogadro's number. The given substance is in atomic form. Therefore, moles multiplied by Avogadro's number gives you what? Atoms. So done and dusted. Here we are given with 16U of helium. 16U of helium. Or you can say 16 AMU of helium. Right? Convert the given quantity into moles. Given mass divided by molar mass. But that formula is applied only if the given mass is in grams. But here the given mass is in U, in AMU. So convert this in grams. So 16U means 16 into 1 by Na. 16 into 1 by Na. Or I can write 16 by Na grams. Now we have converted the mass into grams. Now calculate the moles. Number of moles of helium is equal to given mass of helium divided by molar mass of helium. The value comes out to be 4 by Na. If you got the moles, now moles multiplied by Avogadro's number. Moles multiplied by Avogadro's number. The given substance is in atomic form. So moles multiplied by Avogadro's number. That gives me atoms. So I got the atoms of helium, which came out to be 4. Right? Perfect. Or you could have just done it like this. What is the mass of one atom of helium? 4U. 4U means the mass of one atom of helium. If I multiply with 4, so 4 4s are 16U. 4 1s are 4. That means 16U means 4 atoms directly. 16U means 4 atoms directly. You could have solved it like this as well. Molecules in 126U of HNO3. Since the mass is in U, convert this in grams. 126 divided by Na grams. Now, convert the given quantity into moles. So number of moles of HNO3 will be equal to given mass divided by molar mass. The value comes out to be 2 by Na. Now, moles multiplied by Avogadro's number. Moles multiplied by Avogadro's number. The value comes out to be 2, right? Since the given substance is in molecular form, so moles multiplied by Avogadro's number directly gives me molecules. So molecules of HNO3 came out to be 2. Or you could have directly solved it too. What is the molecular mass of HNO3? Mass of one molecule of HNO3, which means molecular mass, that is 63U. If I multiply with 2, so this becomes 2 molecules. This becomes 126U. So 126U directly means 2 molecules. Simple. Right? Perfectly done. Now, my dear students, there is one more important topic. What is that? That is calculation of moles of atoms and molecules. Calculation of moles of atoms and molecules. See what this is all about. First of all, let me make you understand one statement. If I write 1 mole of H2SO4, 1 mole of H2SO4, general information about H2SO4, guys. Try to understand very carefully. Can I say 1 mole of H2SO4 contains 2 moles of H? Yes. It also contains 1 mole of S. Absolutely. It also contains 4 moles of O. It also contains 4 moles of O. Or, I can say, instead of 4 moles of O, I can say 2 moles of O2. Because 2 moles of O2 means 4 moles of O. 2 moles of O2 means 4 moles of O. Now, let me tell you one thing, which I want you guys to understand here. Sometimes, they'll ask you in the question to calculate the number of gram atoms. Or they can ask you to calculate the number of gram molecules. Or they can ask you to calculate the number of gram ions. Whenever you are supposed to calculate these things, the number of gram atoms, the number of gram molecules, the number of gram ions, understand, they're asking you to calculate the moles. Understand, they're asking you to calculate the moles. Do you understand? Sometimes in the question, they'll ask you to calculate gram atoms, gram molecules, gram ions. Understand? This is nothing but moles. So these are the different names which are given to the term mole. Correct? Look here. Is hydrogen in atomic form? Yes, hydrogen here is in atomic form. So I can write, instead of 2 mole hydrogen, I can write 2 gram atoms of hydrogen. Okay? Sulfur, atomic form. Instead of 1 mole hydrogen, I can write 1 gram atom of sulfur. oxygen in atomic form. So instead of 4 moles of oxygen, I can say 4 gram atoms of oxygen. 4 gram atoms of oxygen. 2 moles of O2. Oxygen is in molecular form. So 2, instead of moles, I can write gram molecules of oxygen. Because oxygen here is in molecular form. Understood? Okay, understood? Understood, people? For example, I can write one more statement to make things more clear to you. For example, I'm writing 1 mole of, let's say 1 mole of carbon dioxide. Can I say in 1 mole carbon dioxide, there'll be 1 mole carbon? Similarly, there'll be 2 moles of O. Or I can say there will be 1 mole of O2. Because 2 moles of O means 1 mole of O2. 2 moles of O means 1 mole of O2. Tell me one thing. Carbon in atomic form. So instead of 1 mole of carbon, I can say 1 gram atom of carbon. Instead of 2 mole of O, I can say 2 gram atoms of oxygen, because oxygen here is in atomic form. Now here oxygen is in molecular form, so I can write 1 gram molecule of oxygen. 1 gram molecule of oxygen. Do you understand? Unacademy J&K चैनल का ओरिएंटेशन कल है, कल शाम को 8 बजे. Okay, I believe all these things are clear. If all these things are clear, let's try to solve few questions based on the same concepts. The question is calculate the moles of O. Calculate the moles of O present in 196 grams of H2SO4. What is my given quantity? Mass. What is my first step always? Convert the given quantity into moles. So number of moles of H2SO4 will be equal to given mass of H2SO4 divided by molar mass of H2SO4. The value is 2. So 196 grams of H2SO4 means 2 moles of H2SO4. So technically, we have to calculate the number of moles of O present in 2 moles of H2SO4. Right? We have to calculate number of moles of O present in 2 moles of H2SO4. Now tell me one thing. If I talk about the general information, in 1 mole H2SO4, how many moles of O do we have? 1 mole H2SO4 contains 4 moles of O. Right? 1 mole H2SO4 contains 4 moles of O. So tell me one thing. If 1 mole H2SO4 contains 4 moles of O, therefore I can say 2 moles of H2SO4 will contain what? 2 moles of H2SO4 will contain 4 into 2. That means 8 moles of O. Correct? This is something I was supposed to calculate. Right? These are the moles of O which are present in 2 moles of H2SO4. Or I can say these are the moles of O which are present in 196 grams of H2SO4. Understood? Okay? I believe this is clear. My dear students, for example, the question is like this. Can you give this a try quick? Can you give this a try? Quickly. See guys, calculate the mass of H3PO4. Calculate the mass of H3PO4 that contains 0.25 moles of O. That contains 0.25 moles of O. See guys, first of all, if I ask you just one thing, look at H3PO4. Can I say 4 moles of O are present in 1 mole H3PO4? Something which we know, right? 4 moles of O are present in 1 mole H3PO4. Therefore, if I use the unitary method, I can say 1 mole of O will be present in 1 by 4 moles of H3PO4. Right? 1 mole of O will be present in 1 by 4 moles of H3PO4. Therefore, as per the question, 0.25 moles of O. So multiplying with 0.25 on both the sides. So I'll say 0.25 moles of O will be present in 1 by 4 multiplied by 0.25. The value comes out to be 1 by 16 moles of H3PO4. So these are basically the moles of H3PO4 that contains 0.25 moles of O. But, tell me one thing. Am I supposed to calculate moles of H3PO4? No. I want to calculate mass of H3PO4. How do you convert moles into mass? So moles multiplied by molar mass of H3PO4. The value comes out to be, I think this will be, it will be 6.125, right? 6.125 grams. Now tell me the meaning of this 6.125 grams. Tell me quickly. What is the answer of what is the meaning of 6.125 grams? Surya, I'm not the owner of this company, okay? I'm just an employee. Okay? So if you have some concerns, you can just put a mail to the CEO of the company. Got it? So my dear students, this is the mass of what? This is the mass of H3PO4. This is the mass of H3PO4 that contains 0.25 moles of O, which I was supposed to calculate. I hope these sort of questions will be easily solved by you from now onwards. I believe that. Okay, let's move on to one more important topic, that is stoichiometry. That is stoichiometry. My dear students, what kind of questions can be framed from stoichiometry? How we can solve the questions based on stoichiometry? How we can solve the questions based on stoichiometry? Now try to understand how. First of all, to understand properly, let's say I'm taking a reaction. The reaction is something like this: N2 gas plus H2 gas. It gives NH3 gas. This is the reaction, for example. I've taken a general reaction here. Is this reaction balanced or unbalanced? The reaction is unbalanced. So balance the reaction. This should be 1. This should be 3. This should be 2. Now let me tell you this 1, 3, and 2. This 1, 3, and 2. I'll be calling them as the stoichiometric. I'll be calling them as the stoichiometric coefficients. And stoichiometric coefficients are treated as, moles. Stoichiometric coefficients are treated as moles. Now, from these stoichiometric coefficients, I can generate a general information about this reaction. What is the information which I can generate about this reaction through the stoichiometric coefficients? I can say 1 mole of N2 completely reacts with 3 moles of H2 and produces 2 moles of NH3. I can say 1 mole of N2 completely reacts with 3 moles of H2 and produces 2 moles of NH3. This is the general information which I got about this particular reaction in terms of moles. This is the general information which I got about this particular reaction in terms of moles. I got to know 1 mole of N2 will react with 3 moles of H2. Then only 2 moles of NH3 will get formed. Right? Number 1. Number 2. Tell me one thing. What is the molar mass of N2? Molar mass of N2 is 28 grams. That means mass of 1 mole N2 is 28 grams. That means mass of 1 mole N2 is 28 grams. So I'm writing 28 grams of N2. What is the molar mass of H2? Molar mass of H2 will be 2 grams. That means mass of 1 mole of H2 is 2 grams. If the mass of 1 mole of H2 is 2 grams, the mass of 3 moles of H2 will be 2 into 3, that is 6 grams. Similarly, what is the molar mass of NH3? It will be 17 grams. So mass of 1 mole NH3 is 17 grams. Therefore, the mass of 2 moles NH3 will be 17 into 2. That means 34 grams of NH3. So I can say 28 grams of N2 completely reacts with 6 grams of H2 and produces 34 grams of NH3. Okay, produces 34 grams of NH3. Right? Now, similarly, guys, you can write one statement in terms of volume. You can say 1 liter of N2 completely reacts with 3 liters of H2 and produces 2 liters of NH3. How many informations, how many statements I wrote about the reaction? I got few information about the reaction. The first information about the reaction I got in terms of moles. The second information about the reaction I got in terms of mass. The third information about the reaction I got in terms of volume. Right? I got in terms of volume. I believe this is clear to everyone. I believe this is clear to everyone. Right? Now, can you write all these 3 statements for a reaction? You can absolutely write all these 3 statements about the reaction. You can absolutely do that. You can write all these 3 statements about all the reactions which you'll be given with. Okay. Now, guys, how do I use this in the questions? That's the point. Generally, in the questions, we use which method? We use mole method generally in the questions. In almost all the questions, I'll show you how to solve the questions with the help of mole method. Now, try to understand how. For example, this is the first and the basic question which is on your screen. Calculate the mass of O2 gas produced on heating 12.25 grams of KClO3. So as per the question, we are heating KClO3. How many grams of KClO3 we are heating? We are heating some 12.25 grams of KClO3. We are heating some 12.25 grams of KClO3. And let me tell you, when KClO3 is heated, we get KCl and we get oxygen. When KClO3 is heated, we get KCl and we get O2 gas as well. Now, first of all, is the reaction balanced? The reaction is not balanced at all. So it is high time to balance the reaction. 2 times, 3 times. Now the reaction is balanced, right? Now the reaction is balanced. First step always is to balance the reaction. Second step, convert the given quantity into moles. I am given with mass of KClO3. So calculate the moles of KClO3 first. It will be equal to mass of KClO3 in grams divided by molar mass of KClO3. The value comes out to be 0.1. So technically 12.25 grams of KClO3 means 0.1 moles of KClO3. So as per the question, I am going to heat up 0.1 moles of KClO3. I am going to heat up 0.1 moles of KClO3 and we have to check the mass of O2 gas produced on heating 0.1 moles of KClO3. So how do I solve this? See, guys, we have to calculate the data for oxygen. So I'm going to write a statement. Look here, stoichiometry coefficient here is 2, here it is 3. Stoichiometry is telling me that 2 moles of KClO3 on heating produces 3 moles of O2. Stoichiometry is telling me that 2 moles of KClO3 on heating produces 3 moles of O2. Therefore, I can say 1 mole KClO3 on heating should produce how much? Think over it. If 2 moles of KClO3 on heating produces 3 moles of O2, therefore 1 mole KClO3 should produce 3 by 2 moles of O2. Now, my dear students, am I going to heat up 1 mole of KClO3? No. As per the question, I have to heat up 0.1 moles of KClO3. So multiply with 0.1 on both the sides. So I can say 0.1 moles of KClO3 on heating will produce 3 by 2 into 0.1. The value comes out to be 0.15 moles of O2. So these are the moles of O2 which are produced. These are the moles of O2 which are produced on heating 0.1 moles of KClO3. These are the moles of O2 which are produced on heating 0.1 moles of KClO3. But as per the question, are we supposed to calculate moles of O2 produced? No. I need to calculate mass of O2 produced. So mass of O2 will be moles of O2 multiplied by molar mass of O2. The value comes out to be 4.8 grams. I would say 4.8 grams of O2 are produced when we heat up 12.25 grams of KClO3. When we heat up 0.1 moles of KClO3. Right? Right, people? I hope this is clear. Guys, one more thing. In this question, whose data we were supposed to calculate? In this question, we were supposed to calculate the data for oxygen. The one whose data is to be calculated, that's always on the right side of the statement. That's why this oxygen is on the right side of this statement. The one whose data is to be calculated, that's always on the right side of the statement. Okay? If I was supposed to calculate the data for KClO3, then KClO3 should have been on right side. That means we were supposed to reverse the statement then. We were supposed to write 3 moles of O2 are produced from 2 moles of KClO3. I'll show you one question of that. I'll show you one question like that as well. See, for example, the same question which we have. Okay, same question but in the reverse manner. Calculate the mass of KClO3 required to produce 4.8 grams of O2 during the decomposition. So as per the question, since we know KClO3 when heated gives KCl, and with KCl we get O2. Now as per the question, we are supposed to get 4.8 grams of O2. And in order to get 4.8 grams of O2, what mass of KClO3 should be used here? What mass of KClO3 is required to produce 4.8 grams of O2? That's the question. Now, first of all, check the reaction. Is it balanced? No. So balance the reaction. Now it's a balanced reaction. After balancing the reaction, convert the given quantity into moles. So number of moles of O2 will be equal to mass of O2 divided by molar mass of O2. The value comes out to be 0.15. So technically, through this reaction, we are supposed to produce 0.15 moles of O2. Now, whose data I'm supposed to calculate? I'm supposed to calculate the data for KClO3. That means KClO3 should be on the right side of the statement. So what should be the statement? Statement will be like this. 3 moles of O2 are produced. 3 moles of O2 are produced from 2 moles of KClO3. 3 moles of O2 are produced from 2 moles of KClO3. Therefore, it means that 1 mole of O2 will be produced from 2 by 3 moles of KClO3. Right? Am I supposed to produce 1 mole of O2? No, I'm supposed to produce 0.15. So I can say 0.15 moles of O2 will be produced from 2 by 3 into 0.15. The value comes out to be 0.1 mole KClO3. So I got the moles of KClO3 here. But am I supposed to calculate moles of KClO3 or mass? I need to get the mass of KClO3. So I can say mass of KClO3 is nothing but moles of KClO3 multiplied by molar mass of KClO3. The value comes out to be 12.25 grams. So this is the mass of KClO3. This is the mass of KClO3 which is required to produce 0.15 moles of O2, which is required to produce 4.8 grams of O2. Correct? Right? Perfect. Now guys, there is one more thing which I want to tell you. There are some reactions which are frequently used in stoichiometry. They'll give you a lot of times the questions based on these reactions. For example, you know calcium carbonate. When you heat calcium carbonate, what do you get? You get calcium oxide and carbon dioxide, correct? For example, you have got the same, which I wrote few minutes back, KClO3. When you heat it up, you get KCl, and with KCl, you get O2. Perfect. For example, you have got sodium bicarbonate, NaHCO3. When you heat it up, you get Na2CO3 plus carbon dioxide plus water. This is one more reaction on which question can be asked, right? For example, you have got Ag2CO3. When Ag2CO3 is strongly heated, what do we get? We get Ag solid. We get Ag solid plus carbon dioxide gas plus O2 gas, right? These are all basically the decomposition reactions. Okay? These are some reactions which you have to remember. Questions can be framed out of these reactions. Okay? Now, similarly, there is one more reaction from which questions are frequently asked. What is that? Understand. For example, you have got the reaction like this. You are taking a hydrocarbon, CXHY. It can be anything, methane, ethane, propane, ethyne, propine, whatever. You are, for example, doing its combustion. Combustion of hydrocarbon, it always leads to the formation of carbon dioxide and water. Combustion of hydrocarbon, it always leads to the formation of carbon dioxide and water. Now, there is a general way of balancing this reaction. How do we exactly balance this reaction? Tell me, how many carbon atoms do you see here? X take this X and make the stoichiometric coefficient of carbon dioxide. How many hydrogen atoms do you see? Y, take this Y and write it as Y by 2 here. And stoichiometric coefficient of O2 will be X plus Y by 4 here. This is the general way of balancing this sort of a reaction. Similarly, guys, for example, you will be having the reaction like this. CXHYOZ. Remember this. When you are doing its combustion, it will again lead to the formation of carbon dioxide, and with carbon dioxide, we have got water, right? There's a way of balancing this reaction too. How many carbon atoms? X. So make this X as the stoichiometric coefficient here. How many hydrogen atoms? Y. Make it as Y by 2, right? What is the stoichiometric coefficient of oxygen? It is going to be X plus Y by 4 minus Z by 2. This is the stoichiometric coefficient of oxygen. So this is the general way of balancing these reactions here. Okay, general way of balancing these reactions here. Let me try to solve one question so that it becomes properly clear to you. For example, question is, during the combustion of just a second, 12 into 3 will be how much? 36 plus 8 is 44. Okay, 440 grams of propane. During the combustion of 440 grams of propane. Calculate. During the combustion of 440 grams of propane, calculate. Number 1. Volume of carbon dioxide gas produced at STP. Number 2. Mass of water produced. Number 3. Molecules of O2 used. Let's say this is the question. Will we be able to solve this sort of a question, people? Will we be able to solve this sort of a question? I believe yes. How exactly? Understand. So first of all, we have got propane, C3H8. We are doing its combustion. When we do its combustion, we'll get carbon dioxide, and with carbon dioxide, what do we get? We get water. Check first of all, is the reaction balanced? No. So first of all, we are supposed to balance this reaction. This is 3, so make it 3. This is 8, 8 by 2 is 4. And this will be X plus Y by 4. 3 plus 8 by 4. 3 plus 8 by 4 is 5. Now the reaction is balanced. After balancing the reaction, convert the given quantity into moles. So number of moles of C3H8. Number of moles of C3H8 is equal. Given mass of C3H8 divided by its molar mass is 44. The value comes out to be 10. So technically, we are going to do the combustion of 10 moles of C3H8. Technically, we are going to do the combustion of 10 moles of C3H8. Now tell me one thing. What kind of information stoichiometry is giving me? Stoichiometry is telling me just one thing. What is that? Stoichiometry is telling me that 1 mole C3H8, when 1 mole of C3H8 undergoes combustion, it needs 5 moles of O2. When 1 mole of C3H8 undergoes combustion, it needs 5 moles of O2, due to which 3 moles of carbon dioxide are produced. Also, 4 moles of water are produced. This is the general information which I got from stoichiometry. General information. Now think over it logically. If 1 mole propane requires 5 moles of O2 for combustion, therefore 10 moles of propane will require 5 into 10. It will require 50 moles of O2. Due to which 3 into 10, 30 moles of carbon dioxide will be formed. And 4 into 10, 40 moles of water will be also formed. So I got the moles of water, I got the moles of carbon dioxide, I got the moles of O2. Now, we have to calculate molecules of O2. Since we calculate moles, how do we convert moles into molecules? So moles multiplied by Avogadro's number. So these are the molecules of O2 which are required. These are the moles of carbon dioxide. What do I need? I need volume of carbon dioxide. So moles multiplied by 22.4 liters. The value comes out to be 672 liters. So this is the volume of carbon dioxide which is produced. Now, mass of water produced. I got the moles. Moles multiplied by molar mass. Moles multiplied by molar mass. It gives me 720 grams. So 720 grams of water will be also produced. So all the 3 questions are done and dusted. Right? All the 3 questions are done and dusted, people. I believe this is clear. And if this is clear, Then let's move on. To one more type of the question which we have here. Or this I can give you as the homework. I'll try to solve one more question. This one I'll solve. See, look at these reactions. Is it 1 or 3? These are actually 3 reactions. These are basically 3 reactions. My dear students, understand. In the first and the second reaction, which one is common component? Common component is NO. Let's just give me a second. Anji, hello. Just a second, मैं check कर रहा हूँ. But कल तो नहीं आया था मुझे कुछ. मेल पे तो मुझे कुछ नहीं आया है. नहीं मेल पे तो नहीं आया है. मैं एक बार ऐप चेक करता हूँ जस्ट. नहीं, ऐप पे भी नहीं आया है. ऐप पे भी नहीं है. ओके. हाँ, आप मेरे को नहीं आया ना, मेल आया ना ऐप पे. ओके. डन. ओके. ठीक है. Okay. All right, should we continue? So what I was telling you, in the first and the second reaction, the common component is NO. In second and the third reaction, the common component is NO2. Now guys, understand one thing. NO in this reaction is the product. It is the product. So NO will get formed in this reaction. The same NO is the reactant here in the second reaction. So that means whatever amount of NO gets formed here, all that NO will be used here because NO is the reactant here. All that NO will be used here. And through this reaction, what gets formed? NO2 gets formed. And whatever NO2 gets formed here, all that NO2 is used here. And what do we get at the end? We get NO and HNO3. Do you understand the concept? I'll give the break at 1:15. Okay? 1:15. Don't worry. See, in the first reaction, NO will be getting formed. And whatever amount of NO gets formed in the first reaction, all that NO gets used here. And finally, what do we get? NO2. Whatever amount of NO2 we get here, all that NO2 will be used here. And finally, what do we get? We get HNO3. We have to calculate the mass of HNO3 formed on starting with, let me make the calculation easy, on starting with 224 liters of NH3 gas at STP. So technically, we are starting with 224 liters of NH3. So my dear students, what is my first step always? My first step always is convert the given quantity into moles. So number of moles of NH3 will be equal to given volume of NH3 in liters divided by 22.4 liters. The value comes out to be 10. So we are basically starting with 10 moles of NH3. Now guys, just use the stoichiometry. Since we are going to start with 10 moles of NH3, use the stoichiometry. Coefficient here is 4, here it's 4. Can I say stoichiometry is telling us that 4 moles of NH3 gives 4 moles of NO, which means that 1 mole of NH3 gives 1 mole of NO. 1 mole of NH3 gives 1 mole of NO. So therefore, I would say 10 moles of NH3 would give me 10 moles of NO. So these are the moles of NO which are formed in the first reaction. So in the first reaction, 10 moles of NO are formed. And whatever moles of NO are formed in the first reaction, all these moles of NO will be used in the second reaction. So I can say stoichiometry here. If you use the stoichiometry in the second reaction, I can say 2 moles of NO gives us 2 moles of NO2. Correct? Therefore, 1 mole of NO gives us 1 mole of NO2. How many moles of NO we have? Whatever NO got generated here, all that NO will be used here. So I would say 10 moles of NO will form 10 moles of NO2. So we got to know In the second reaction, 10 moles of NO2 are formed. And whatever moles of NO2 are formed here, all that will be used here. Now we use the stoichiometry. 3 moles gives 2 moles. I can say, or you can write it as such, 3 moles gives 2 moles. So 1 mole gives us 2 by 3. 10 moles of NO2 gives us into 10. The value comes out to be 6.66. So 6.66 moles of HNO3 are formed. 6.66 moles of HNO3 are formed. If you got the moles of HNO3, I need to calculate mass of HNO3. So moles of HNO3 multiplied by molar mass of HNO3. That will give you the mass of HNO3. Am I clear? Am I clear? Quickly in the chats, every one of you. Yeah? Perfect. I think let's take a break here. The ones who want to do the lunch, they can do the lunch. The ones who want to pray, they can pray. Right? I'll also be back. So I think we'll be back exactly at what time? 1:45, huh? So at 1:45, I'll start the session again. Huh? At 1:45, we'll start the session again. All right? So be back on time. And I would request everyone to be back. Then it's going to be fun. Otherwise, there will be no fun at all. Okay? I'll see you exactly at 1:45. We have a lot of things to discuss today. A lot of things. So, see you next. See you. Is everyone back? Yes. Is everyone back? So guys, whatever topics we have discussed till now, is every single thing clear? Can you just let me know once in the chats quick? Whatever things we have discussed till now, is every single thing clear to everyone? Yeah? All right. All right, people. All right, got it. So let's continue then. And I think people will keep on joining till then. Okay, let's continue with one more topic, guys. One simple topic this is, right? From which questions can be asked. And the topic name is vapor density. So first of all, how do we exactly define the term vapor density? Let me tell you that first. My dear students, vapor density is defined as, the ratio of density of the gas to that of the density of H2 gas at same pressure and temperature. At same pressure and temperature. What does it mean? Let's try to understand, people. Let's try to understand. So first of all, if you have to define vapor density of a gas, vapor density of a gas is nothing but, it is defined as density of the gas divided by density of hydrogen gas when the pressure and temperature of both the gases is kept same. So basically, for example, imagine these are the two containers which I'm taking. And in one container, imagine that you are keeping a gas, some random gas you are keeping, for example, oxygen, nitrogen, whatever, right? In the other container, for example, you are keeping hydrogen gas. In the second container, you are keeping the hydrogen gas in particular. Now, I'm assuming that whatever is the pressure of the gas in this container, same is the pressure of hydrogen in this container. So I would say pressure of gas and pressure of hydrogen gas. For example, they are same. Similarly, temperature of this gas and temperature of hydrogen, that's also same. So technically, I'm keeping both the gases at same pressure as well as same temperature. Now, when both the gases are kept at same pressure and temperature, definitely at that point of time, this gas will be having some density. And this hydrogen gas will also have some density. If I take the ratio of these two, density of the gas divided by density of hydrogen gas, when pressure and temperature of both the gases kept same, this ratio is what you call as the vapor density. This ratio is what you call as the vapor density of the gas. So for example, let's say I'm asking you to calculate vapor density of oxygen. So what you'll be doing? You'll be writing vapor density of oxygen is equal to density of oxygen divided by density of hydrogen when pressure and temperature of both are same. For example, I'm telling you, what is the vapor density of nitrogen gas? You will write vapor density of nitrogen gas is equal to density of nitrogen divided by density of hydrogen when pressure and temperature of nitrogen as well as oxygen as well as hydrogen is kept same. Right? So simple. This ratio is called as the vapor density. Now, since the vapor density of the gas, since it is the ratio of two same things, density as well as density, so I would say this vapor density is going to be unitless term. It is going to be a unitless term. Now, if you ask me what kind of information this vapor density gives us, what kind of information this vapor density is giving us. See guys, for example, I'm telling you vapor density of some gas is equal to 2, for example. It means that density of the gas divided by density of hydrogen is equal to 2, which means that density of the gas is equal to 2 times the density of hydrogen when pressure and temperature is kept same. So I can say that particular gas whose vapor density will be 2, it means that particular gas is 2 times denser than hydrogen at same pressure and temperature. For example, I'm telling you, vapor density of the gas is 5. It means the gas is 5 times denser than hydrogen when pressure and temperature is kept same. I believe this is clear. Now, my dear students, I can simply generalize a statement. I can say vapor density of a gas gives an idea about how many times a gas is denser than hydrogen gas at same pressure and temperature. Okay? Now, there is one result which I would want every one of you to know. Okay, I'm not going to derive the result. I'm just going to give you the result. Remember it. I'll be frequently using it. The result is molar mass of the gas is always equal to 2 times vapor density of the gas. So whenever I'll be given with the vapor density of the gas, I can calculate its molar mass for sure. So molar mass of the gas is nothing but it is 2 times vapor density of the gas. Okay. Now guys, how do I use this concept in the form of questions? What kind of questions can be framed from this? For example, one simple question I'm writing here. The question is, for example, vapor density of the gas is equal to 5. I'm asking you to calculate the mass of 10 moles of the gas. I'm asking you to calculate the mass of 10 moles of the gas. It's a simple question. So first of all, since the vapor density of the gas is given, so I can calculate molar mass of the gas. Molar mass of the gas is 2 times the vapor density. So the value comes out to be 10 grams. So I got the molar mass of the gas. Molar mass means mass of 1 mole, right? So molar mass of the gas is 10 grams. It means that the mass of 1 mole of the gas is equal to 10 grams. Now think logically, if the mass of 1 mole of the gas is 10 grams, therefore mass of 10 moles of the gas will be, if 1 mole of the gas has got the mass of 10 grams, therefore I would say 10 moles of the gas will have the mass of 10 into 10, which comes out to be 100 grams, right? This can be one of the simplest questions framed out of this. Similarly, if I reverse the same question, for example, the question is like this. Vapor density of the gas is equal to 5. Calculate the number of moles. Calculate the number of moles present in 100 grams of the gas. Calculate the number of moles present in 100 grams of the gas. This can be one more question. But dear students, it's pretty much simple. Have a look. Since vapor density of the gas is given, so I can calculate molar mass of the gas, which is 2 times the vapor density. So it will come out to be 10 grams. What do we have to calculate? The number of moles in 100 grams of the gas. So I can say number of moles of the gas will be equal to mass of the gas in grams divided by molar mass of the gas. What is the mass of the gas in grams? That's 100 divided by what is the molar mass of the gas? That's 10. The value comes out to be simply 10. Right? Pretty much simple. Similarly, my dear students, there can be, for example, a question like this. The question can be, the density of the gas at STP is equal to 1 gram per liter. Density of the gas at STP is equal to, for example, 1 gram per liter. Let's say they are asking us to calculate vapor density of the gas. This is the question. How do you deal with such kind of the question? Vapor density of the gas is equal to density of the gas divided by density of hydrogen. No doubt I'm given with density of the gas, but I do not know the density of hydrogen. So how do I deal with this question? See guys, it's again pretty simple. See, as far as the question is concerned, density of the gas at STP is given us 1 gram per liter. 1 gram per liter. What does it mean? It means that 1 gram per liter. It means 1 liter of the gas has got the mass of 1 gram. It means 1 liter of the gas has got the mass of 1 gram at STP. Condition in the question is given to me as STP. So if 1 liter of the gas has got the mass of 1 gram, What do you think about 22.4 liters of the gas? If 1 liter of the gas has got the mass of 1 gram, so 22.4 liters will have the mass of 22.4 grams. Right? 22.4 liter gas at STP means 1 mole of gas. 22.4 liter gas at STP means 1 mole gas. So it means 1 mole of gas has got the mass of 22.4 grams. And you know, mass of 1 mole of the gas is what you call as the molar mass of the gas. So technically, I got the molar mass of the gas. Now, you know, a few minutes back I told you, molar mass of the gas is equal to 2 times vapor density of the gas. So can I say vapor density of the gas will be equal to molar mass of the gas divided by 2? Absolutely. What is the molar mass of the gas? That's 22.4 divided by 2. The value comes out to be 11.2. So I would say vapor density of the gas is 11.2, which means the gas will be 11.2 times denser than hydrogen gas, right? At STP condition. I believe this is clear to everyone. And if this is clear to everyone, let's move on to one more easy topic, one more simple topic from which questions can be framed. That's what you call as mass percentage of an element in a compound. Mass percentage of an element in a compound. Now, what is meant by that? What is meant by mass percentage of an element in a compound? Again, a simple topic, guys. See, mass percentage of an element in a compound is nothing but it is defined as the mass of an element in grams, which is present in 100 grams of compound. Mass of an element in grams, which is present in 100 grams of compound. So basically, for example, I'm asking you, what is the mass percentage of carbon in carbon dioxide? For example, I'm asking you, what is the mass percentage of carbon in carbon dioxide? So technically, what am I asking you? I'm asking you, what mass of carbon is present in 100 grams of carbon dioxide? For example, I'm asking you, what is the mass percentage of nitrogen in NH3? So technically, I'm asking you, what is the mass of nitrogen which is present in 100 grams of NH3? Do you understand? Do you understand? And my dear students, I'm going to give you a direct formula with the help of which you can calculate mass percentage. And the formula is something like this. You'll write molar mass of the element multiplied by Z divided by molar mass of compound multiplied by 100. This is one simple formula with the help of which we can calculate mass percentage of an element in a compound. Now, the point is, what is ME, what is MC? ME represents molar mass of the element. Molar mass of the element. MC represents molar mass of the compound. Molar mass of the compound. And this Z, it represents, in short, number of atoms of the element in one molecule. What does it mean? Try to understand. For example, I am taking the compound as carbon dioxide and I want you guys to tell me the mass percentage of carbon here. Mass percentage of carbon. In what? In carbon dioxide. So it is technically mass percentage of element in a compound. It is technically mass percentage of element in a compound, which will be equal to molar mass of element, molar mass of carbon, that's 12, multiplied by. How many carbon atoms do you see here? 1, divided by molar mass of entire compound, molar mass of carbon dioxide, 44, multiply it with 100. You'll be getting the mass percentage of carbon here. Similarly, if I ask you, what is the mass percentage of oxygen here? You'll write molar mass of oxygen multiplied by. How many oxygen atoms? 2, divided by molar mass of compound, 44, multiplied by 100. This is going to give you the mass percentage of oxygen here. Isn't it simple? For example, I'm writing the compound CH3COOH. I'm asking you to calculate the mass percentage of carbon here. You will write molar mass of carbon multiplied by. How many carbon atoms do you see here? 2, divided by molar mass of this entire compound. When you calculate 60, multiplied by 100. For example, I'm asking you to calculate mass percentage of hydrogen. What is the molar mass of hydrogen? That's 1, multiplied by. How many hydrogen atoms do you see? 4, divided by molar mass of compound, 60, multiplied by what? Multiplied by 100. Yeah? Pretty much simple. I believe this is clear. Now, my dear students, questions like these can be asked. Calculate the mass percentage of this element in this compound, etc., etc. Questions can be formed out of this manner as well, right? Or there can be one more type of question asked from here. What is that type of the question? The question will be like this. The question is the mass percentage of sulfur. It's a famous question. The mass percentage of sulfur in insulin is 3.2%. Is 3.2%. Calculate the minimum molar mass of insulin. Calculate the minimum molar mass of insulin. This can be one more pattern of the question which can be asked from this particular topic. See guys, what do we do here? As far as the question is concerned, you are given with a compound that its name is insulin, right? Its name is insulin, and mass percentage of sulfur in insulin is given. Mass percentage of sulfur in insulin is given 3.2%, right? What do I have to calculate? Minimum molar mass of insulin. Do I know the formula of insulin? No, I do not know the formula of insulin. Neither you will be knowing the formula of insulin, I'm pretty much sure, right? But I don't need the formula of insulin here. Why is that? See, mass percentage of sulfur in insulin, it will be molar mass of sulfur multiplied by. Now the point is, how many sulfur atoms will be there in insulin? How many sulfur atoms will be there in insulin? To know that, we should know the formula of insulin, but we do not know the formula. Therefore, a hint is given in the question. Calculate the minimum molar mass of insulin. Calculate the minimum molar mass of insulin. Molar mass of insulin can be minimum if there will be minimum sulfur atoms in insulin. And minimum, how many sulfur atoms can be there? Minimum, there can be just one sulfur atom. So whenever a question is asked based on the minimum molar mass, you have to take the Z value as 1. Remember it directly, right? Divided by molar mass of compound. Compound here is insulin, multiplied by 100. This value as per the question is equal to 3.2. When you solve this, you'll get the molar mass of compound as 1000 grams. So you got technically the minimum molar mass of insulin as 1000 grams. I believe this sort of a question you should be in a position to solve if it is asked in your examination, right? I believe it's clear. Now, my dear students, I'm going to move on to one more important topic. What is that? That's your limiting reagent. Limiting reagent. What is limiting reagent, first of all? My dear students, limiting reagent is that reactant. It is that reactant in a chemical reaction which gets completely consumed. For example, understand what I'm going to say. For example, I'm taking a general reaction as A plus B. It gives C. Let's say it's a balanced chemical equation. Now, for example, if I write time t is equal to 0, time t is equal to 0 means the reaction has not started. So if the reaction has not started yet, that means product has not got formed yet. If the reaction has not started, that means product formation has not taken place yet. So at time t is equal to 0, the container in which the reaction has to proceed, in that container, at time t is equal to 0, there will be only moles of A and B present. Let's say there are some 10 moles of A present and there are some 5 moles of B present. Initially, at time t is equal to 0, when the reaction has not started yet. Right? Now, my dear students, when the reaction will start, what will happen? These reactants will start reacting. And they will start forming the products. Right? Now, when the reactants will start reacting, what will happen to the number of moles of reactants? Can I say number of moles of reactants are going to decrease with time? Number of moles of reactants. Since when the reaction starts, these reactants will start reacting and they will lead to the formation of products, due to which number of moles of reactants are going to decrease with time. Can I say out of these two reactants, there will be one reactant which will get completely consumed? Which one do you think that is, A or B? The one that is present in lesser amount here, that will be completely consumed. So I would say after some time, when the reaction starts, there will be 0 moles of B left in the container. But there will be some moles of A present in the container. And also some moles of C would have got formed too after some time. And at this particular point of time, when B has got completely consumed, A is still left, right? And C has got formed. Will the reaction be still going on? No, the reaction would have stopped. Because B has got completely consumed. The reaction would have got stopped. That particular reactant in a reaction which gets completely consumed, you call that as the limiting reagent. The other one is called as the excessive reagent. And let me tell you, entire product formation, as well as the amount of reactant left, amount of excessive reagent left in the container, amount of product formed, as well as the amount of excessive reagent left in the container at the end of the reaction, all the things are decided by the limiting reagent. Limiting reagent is the one that decides everything. Limiting reagent is going to tell you how much C would have got formed at the end of the reaction, how much A would be left in the container at the end of the reaction, right? How exactly? That's what we have to see. And questions are asked from that particular part. Let's get to know how limiting reagent is going to decide all the things. Try to understand. For example, you have got the question like this. You are writing a reaction N2 plus H2. Gives what? It gives NH3. My dear students, at time t is equal to 0, for example, I have got 10 moles of N2 in the container as well as 10 moles of H2 in the container. So this will be 0 because the reaction has not started yet. Now, the first thing, is the reaction balanced? No. So balance the reaction. This should be 3 times, this should be 2 times, and this should be 1. The reaction is balanced. Now, after balancing the reaction, you have to check which one is the limiting reagent. The point is, how do we check which one is the limiting reagent? For that, what you have to do, you have to divide these given moles of reactants by the respective stoichiometry coefficients. So 10 divided by 1, 10 divided by 1, 10 divided by 3. This value comes out to be 10, this value comes out to be 3.33. So given moles divided by respective stoichiometry coefficients. Now tell me, whose value is lesser, 10 or 3.33? I'll say this value is lesser. The one that gets the lesser value, that's always your limiting reagent. So H2 here is my limiting reagent. That means N2 automatically is going to be my excessive reagent. Okay. Now, if I got to know that H2 is my limiting reagent, that means when the reaction starts, after some time, you will find 0 moles of H2 left in the container. It would have got completely consumed, right? And entire product formation will be decided by this limiting reagent. How much excessive reagent is left? That's also decided by the limiting reagent. How exactly? Understand. See, stoichiometry is telling us that 3 moles of H2 gives 2 moles of NH3. 3 moles of limiting reagent gives us 2 moles of NH3. This is stoichiometry telling me this. I mean, this information is given by stoichiometry. Now think over it. If 3 moles of H2 gives 2 moles of NH3, I can say 1 mole of H2 will be giving me 2 by 3 moles of NH3. Correct? Did I have 1 mole of H2 or 10 moles of H2? I had some 10 moles of H2. So I can say 10 moles of H2 are going to give me 2 by 3 multiplied by 10. The value comes out to be 6.66 moles of NH3. So I got to know 6.66 moles of NH3 would have got formed at the end of the reaction. 6.66 moles of NH3 would have got formed at the end of the reaction. Now, my dear students, the point is, I got the moles of NH3 formed. They can ask me the mass of NH3 formed. I got the moles. Moles multiplied by molar mass. Moles multiplied by molar mass of NH3. That gives me the mass of NH3 formed. They can ask me about the volume of NH3 formed. I got the moles multiplied with 22.4 liters at STP. You get the volume of NH3 formed. They can ask me the molecules of NH3 formed. I got the moles multiplied by Avogadro's number. That gives me the molecules of NH3 formed. So anything can be asked. Now the point is, this N2 is the excessive reagent. If N2 is the excessive reagent, definitely there will be some moles of N2 still left in the container when the reaction would have stopped. How do I check that? How do I check how much N2 has left? How much N2 is left? Again, that information is going to give me, I'll be getting that information again from the limiting reagent. If you look at the stoichiometry is telling us that 3 moles of limiting reagent reacts with 3 moles of limiting reagent reacts with what? 1 mole of N2. Correct? Therefore, 1 mole of limiting reagent would have reacted with 1 by 3 moles of N2. 1 mole of limiting reagent would have reacted with 1 by 3 moles of N2. But did we have 1 mole of limiting reagent or 10? I would say 10 moles of limiting reagent would have reacted with 1 by 3 into 10. The value comes out to be 3.33 moles of N2. So these are the moles of N2 that have reacted. These are the moles of N2 that have reacted. These are the moles of N2 that have reacted. How many moles of N2 I took in the beginning? 10. Out of 10, how many are reacting? 3.33. So 10 minus 3.33 will come out to be 6.66. So I would say 6.66 moles of N2 will be still left in the container as such at the end of the reaction. If I'm clear with this particular concept, let me know once in the chats. I'll take one more example. With that, things will be more clear to you. Okay? I'll take one more example. With that, things will be more clear to you. For example, this is the question. I'm given with the reaction, and the reaction is already given to me in the balanced format. Reaction is given, and also reaction is given in the balanced format. So let me write the reaction again. 6 times LiH plus 8 times BF3. It gives me what? It gives me 6 times LiBF4. And with that, what do we have? We have got B2H6, right? Now, initially at time t is equal to 0, we are starting with 2 moles each of reactants. We are starting with 2 moles each of reactants. Now, in the question, they're asking you, calculate the moles of B2H6 formed. At the end of the reaction, how many moles of B2H6 would have got formed? That is the question. First of all, the reaction is balanced. Now, first thing, we have to identify the limiting reagent. How do we identify? Given moles divided by respective stoichiometric coefficients. The one that gets the lesser value is your limiting reagent. So 2 divided by 6 and 2 divided by 8. Which value is lesser? This value is lesser. The one that gets the lesser value, that's my limiting reagent. So I would say BF3 is my limiting reagent. If BF3 is my limiting reagent, I'll be left with nothing. 0 moles of BF3 will be left in the container at the end of the reaction. Now, entire product formation and how much excess reagent is left, everything is decided by this limiting reagent. But we don't have to calculate everything in this question. In this question, we just have to check how many moles of B2H6 have got formed. Look at the stoichiometry. This is 8 here. This is 1. So I would say stoichiometry is telling me that 8 moles of BF3, 8 moles of BF3 produces 1 mole of B2H6. This is the information given to me from stoichiometry, right? 8 moles of BF3 gives 1 mole of B2H6. Therefore, I would say 1 mole BF3 gives what? Gives 1 by 8 moles of B2H6. But did I have 1 mole of BF3? No, we had 2 moles of BF3. So I would say 2 moles of BF3 would be giving me 1 by 8 multiplied by 2. The value comes out to be 1 by 4, which means 0.25 moles of B2H6 would have got formed at the end of the reaction. So you got to know 0.25 moles of B2H6 have got formed at the end of the reaction. That's something I was supposed to calculate. I believe I'm clear. So I hope you can solve the questions of limiting reagent like this easily, right? If this concept is clear, let me know once in the chats quickly. Then I'm going to move on to one more concept. You can take this question as a homework. Similar question. Similar question, we just have to calculate the moles of barium phosphate formed, right? Similar sort of question. You can take this as a homework. Tell me quickly, if all these things are very, very, very much clear to you. Yeah? Everyone. Everyone, people. Everyone in the chats once. Perfect. All right. Now comes one more topic, that is percentage yield. Questions are asked from this topic as well. Now, what is percentage yield? If I talk about percentage yield of the reaction, percentage yield of the reaction is nothing but it is defined as experimental amount, or you can call it as the actual amount. Experimental amount or actual amount divided by expected amount, or you can call it as a theoretical amount. Theoretical amount multiplied by 100. So basically, what is meant by this percentage yield, you can understand only if I solve the question on it. So I'm going to directly solve a question on it. From that, you'll understand what this percentage yield is all about. But before doing the question, let me tell you one thing. This experimental amount will be generally given to you in the question. Experimental amount, which is the actual amount, that is generally given to you in the question. And this expected amount, we will be calculating with the help of stoichiometry. Just remember these two things for now. Experimental amount will be given to me in the question. Expected amount I will be calculating with the help of what? With the help of stoichiometry, right? How exactly? For that, one question I have, and this question will make you understand everything. Understand properly what I'll be saying. In the question, they have mentioned that on heating 40 grams of calcium carbonate, 20 grams of calcium oxide was obtained. In the question, they are mentioning that on heating 40 grams of calcium carbonate, 20 grams of calcium oxide was produced, right? Remember, whatever data will be given to you in the question, whatever data will be given to you in the question, that's always experimentally verified data. That would have been experimentally checked. So this data which is given to me in the question, it would have been seen experimentally. What has been seen experimentally? In the lab, they would have heated up 40 grams of calcium carbonate and 20 grams of calcium oxide would have got produced in the lab itself. So this is something which has been observed experimentally, that when you heat up 40 grams of calcium carbonate, 20 grams of calcium oxide was produced, right? So this has been checked experimentally. So I'll be calling this amount as the experimental amount or actual amount. Now, in order to calculate the yield, how many amounts do I need? I need 2 amounts. Experimental already we have. What do we need now? We need expected amount. Expected amount we can calculate with the help of stoichiometry. See how. First of all, if I ask you what is the molar mass of calcium carbonate, when you calculate it, molar mass of calcium carbonate will come out to be 100 grams. That means mass of 1 mole of calcium carbonate is 100 grams, right? Mass of 1 mole of calcium carbonate is how much? 100 grams. So I can say 100 grams of calcium carbonate on heating. What is the molar mass of calcium oxide? Molar mass of calcium oxide will be 56 grams when you calculate it. Therefore, mass of 1 mole of calcium oxide is nothing but 56 grams. So stoichiometry is telling me that, stoichiometry means this theoretical calculation, which I am doing on pen paper. Stoichiometry is telling me that 100 gram calcium carbonate upon heating, 100 gram calcium carbonate upon heating should give, I'm using the term should. So this is something which I'm writing on pen paper. This is my expectation that 100 gram calcium carbonate upon heating should produce 56 grams of calcium oxide. Therefore, as per our calculations, 1 gram of calcium carbonate upon heating should produce 56 divided by 100 grams of calcium oxide, right? Or I can say, as per our calculations, 40 grams of calcium carbonate, 40 grams of calcium carbonate upon heating should produce 56 divided by 100 multiplied by 40. When you solve this, this value comes out to be 22.4 grams of calcium oxide. So this is the amount of calcium oxide. This is the amount of calcium oxide which should get formed as per our calculations. This is the amount of calcium oxide which should get formed as per our calculations. So when we heat up 40 grams of calcium carbonate, this is the amount of calcium oxide that should get formed as per our calculations. So this is my expectation basically. So I'm calling this amount as the expected amount, right? How much calcium oxide is getting formed in reality? In reality, 20 grams of calcium oxide is getting formed. So this is the actual amount of calcium oxide which is getting formed in the lab. This is the amount which I was expecting as per our calculations. Now, if I ask you, what is the percentage yield of the reaction? What is the efficiency of the reaction? Percentage yield is also what is efficiency. What you will be writing? Experimental amount divided by expected amount multiplied by 100. This value comes out to be 89%. So it means that efficiency of this particular reaction is 89%. It means the efficiency of this reaction is 89%. Or I can say something like this. How much calcium oxide should have got formed as per our calculations? As per our calculations, 22.4 grams of calcium oxide should have got formed. In reality, in the lab, how many grams are actually getting formed? Only 20 grams. That means while carrying out the experiment, there should have been some errors. There should have been some human errors, instrumental errors, due to which whatever amount I was expecting to get formed as per stoichiometry, right? In reality, lesser amount got formed than expected. Got it? Or you can say one thing. How much amount was getting formed? How much amount I was expecting to get formed? 22.4 grams. In reality, only 89% of this amount is actually getting formed. When you calculate 89% of 22.4, when you solve this, this value will exactly come out to be 20 grams. This value will exactly come out to be 20 grams. Now, I'm asking you a question. If the yield of the reaction was 100%, if the yield of the reaction was 100%, if the efficiency of the reaction was 100%, at that point of time, whatever amount you would have expected through your calculations, in lab also same amount would have got formed. Only when the yield of the reaction is 100%. Only when the yield of the reaction is 100%. Got it? Got it, people? Let's try to solve one more question. See, this is again the similar type of question. So let me not solve this. Let me solve a different question. Just a second. Let me solve a different question. For example, a question is like this. On heating 150 grams of calcium carbonate. On heating 150 grams of calcium carbonate. What mass of calcium oxide will get formed? What mass of calcium oxide will get formed if the yield of the reaction is 75%? This is the question, for example. Yeah, this is the question. Now see, guys, how I'm going to deal with such type of the question. Try to understand. As far as the question is concerned, we are heating up calcium carbonate, right? We are heating up calcium carbonate. And you know, when calcium carbonate is heated, calcium oxide gets formed and carbon dioxide is formed, right? Yield of the reaction is, efficiency of the reaction is 75%. As per the question, we are heating 150 grams of calcium carbonate. We have to check on heating 150 grams of calcium carbonate, what mass of calcium oxide will get produced if the efficiency of the reaction is 75%. This is the question. Now, how do I deal with this? Understand? I can say from stoichiometry, I can say 100 grams of calcium carbonate upon heating should produce 56 grams of calcium oxide. This is my calculation. This is my stoichiometry. Stoichiometry is telling me that 100 gram calcium carbonate on heating should produce 56 grams of calcium oxide, which means that 1 gram of calcium carbonate on heating, 1 gram of calcium carbonate on heating should produce 56 divided by 100 grams of calcium oxide. Therefore, technically, 150 grams of calcium carbonate on heating should produce 56 divided by 100 multiplied by 150. The value comes out to be 84 grams of calcium oxide. So this is the mass of calcium oxide that should get formed. But what is the yield of the reaction? 75%. What is the efficiency of the reaction? 75%. So whatever amount I'm expecting to get formed, only 75% of this amount will be getting formed in reality in the lab. So that means if the yield of the reaction is 75%, so what is the mass of calcium oxide which will be getting formed in the lab? It will be 75% of the amount which we have expected. So 75% of 84, the value comes out to be 63 grams. So this is the mass of calcium oxide which would be getting formed in the lab in reality. Am I clear with this? Am I clear with this? Yes or no? Quickly in the chats. I believe these sort of questions you should be in a position to solve from now onwards. Right? Going to one more topic. What is that? That is your percentage purity. That is your percentage purity. My dear students, how do we define percentage purity first of all? You should know that. I would say percentage purity of a compound. It is defined as the mass of compound in grams present in 100 grams of impure sample. Present in 100 grams of impure sample. What does that mean? Let me make you understand this topic as well. For example, this is a container. Imagine in this container, I'm keeping calcium carbonate. And with calcium carbonate, for example, I have got some impurities as well in this container. Imagine that in this container, we have got calcium carbonate. And apart from calcium carbonate, we have got some impurities as well, right? So first of all, let's assume that the mass of the whole sample, the mass of the entire sample, which I call as the mass of impure sample. Mass of impure sample, for example, is 50 grams. Mass of impures, mass of the entire sample. That means mass of calcium carbonate plus mass of impurities. Mass of the entire sample is, for example, 50 grams. Let's say out of 50 grams, there are 10 grams of pure calcium carbonate. Let's say out of 50 grams, there are 10 grams of pure calcium carbonate in the container. So can I say 50 grams of the sample, 50 grams of the impure sample contains 10 grams of pure calcium carbonate? Yes. Therefore, I would say 1 gram of the sample should contain 10 divided by 50 grams of calcium carbonate. Absolutely. 1 gram of the sample should contain 10 by 50 grams of pure calcium carbonate. So as per this calculation, I would say 100 grams of the sample, 100 grams of the sample should contain 10 by 50 multiplied by 100 grams of calcium carbonate. Now think logically what we have calculated. I can say this is the mass of pure calcium carbonate. This is the mass of pure calcium carbonate, which is present in 100 grams of the impure sample. And as per the definition, that mass of pure compound, which is present in 100 grams of the sample, what do I call that as? Percentage purity. So technically, this is the percentage purity of calcium carbonate in the sample. Right? Now, you do not have to do all this process over here. I'm just going to give you one formula. You're going to remember that. What is that formula? Remember percentage purity of a compound. Percentage purity of a compound in a sample. It's always equal to mass of pure compound divided by the mass of the impure sample. The mass of the impure sample multiplied by 100. This is the formula with the help of which you can calculate percentage purity of a compound in a sample. A general formula, direct formula. Okay. Now remember one thing, one more statement, which I want you guys to take a note of. Remember, in a chemical reaction, only pure substance participates. In a chemical reaction, only pure substance participates. Only pure substance participates. Impurities do not take part in a chemical reaction. Impurities do not take part in a chemical reaction. Impurities do not take part in a chemical reaction. In a chemical reaction, it's only the pure substance that's going to participate. Impurities are not going to participate in a chemical reaction. Okay? Now guys, one more important thing. Sometimes in a question, you will be given with a statement like this. For example, 50 grams of 80% pure calcium carbonate. I'm writing a statement. 50 grams of 80% pure calcium carbonate. What does that mean? It means that you have got a sample containing calcium carbonate and impurities. The mass of the whole sample is 50 grams. The mass of the whole sample is 50 grams. And out of 50 grams, the mass of pure calcium carbonate will be how much? That will be 80% of 50. That will be 80% of 50. The value comes out to be 40 grams. So I would say in the sample, there will be 40 grams of pure calcium carbonate. Do you understand this? Do you understand what I'm saying? Yeah? I believe this is clear, right? I hope you can decode these sort of statements if they are written in the question. Now, my dear students, let's see what kind of question can be framed out of it. There can be a lot of questions framed. I'll show you one. Look at this question. The question is 50 grams of 80% pure calcium carbonate is heated. 50 grams of 80% pure calcium carbonate is heated. That means you've got a sample containing calcium carbonate and impurities. In that sample, what is the mass of pure calcium carbonate? Tell me that first. The mass of pure calcium carbonate in the sample is 80% of 50. The value comes out to be 40 grams. So basically what you have done, you have taken a sample and this sample contains calcium carbonate with some impurities. The mass of this entire sample is 50 grams. The mass of this entire sample is 50 grams, out of which I got to know 40 grams is the mass of calcium carbonate. 40 grams is the mass of calcium carbonate. Now, if I ask you, how many moles of calcium carbonate are there in the sample? You'll say mass of calcium carbonate divided by molar mass of calcium carbonate. So these are the moles of calcium carbonate present in the sample. Now, my dear students, as per the question, we are heating this sample. When we heat the sample up, what will happen? When we are going to heat the sample up, this calcium carbonate technically will automatically get heated. And when calcium carbonate gets heated, it breaks down into calcium oxide and carbon dioxide. Now, in reality, how many moles of calcium carbonate are getting heated? 0.4. So 0.4 moles of calcium carbonate technically we are going to heat up, right? Now, stoichiometry is telling me what? Stoichiometry is telling me that 1 mole calcium carbonate on heating produces 1 mole carbon dioxide. Stoichiometry is giving me this information. If 1 mole calcium carbonate on heating produces 1 mole carbon dioxide, therefore I would say 0.4 moles of calcium carbonate which were there in the container upon heating should produce 0.4 moles of carbon dioxide, right? So these are the moles of carbon dioxide which are being produced. But am I supposed to calculate moles of carbon dioxide or volume? I need to calculate volume of carbon dioxide, which means moles multiplied by 22.4. The value comes out to be 8.96 liters, right? So 8.96 liters of carbon dioxide will be produced at the end of the reaction. Am I clear? This is something I was supposed to calculate. I believe these sort of questions you can easily solve from now onwards. If I'm clear, let me know once in the chats quickly. Okay? Similarly, guys, let's try to solve one more question. Look at this particular question carefully. The question is 410 grams of limestone. Limestone means a sample of calcium carbonate plus some impurities. You have got 410 grams of limestone. That means mass of the impure sample is 410 grams. Okay? 410 grams of limestone is treated with oxalic acid. So that means you are introducing oxalic acid here to produce 512 grams of calcium oxalate. 512 grams of calcium oxalate are getting produced. Calculate the percentage purity of calcium carbonate in the sample. Calculate the percentage purity of calcium carbonate in the sample. Try to understand. We need to calculate percentage purity of calcium carbonate in the sample, which will be equal to mass of pure calcium carbonate in the sample divided by the mass of impure sample multiplied by 100, right? Well, the mass of impure sample is given to me in the question, 410 grams. What do I need? I need the mass of pure calcium carbonate. I told you already, my dear students. In a chemical reaction, it is a pure substance that participates. Impurities do not take part in the chemical reaction. So basically, when you have introduced oxalic acid here, I would say that oxalic acid would have reacted with pure calcium carbonate. And as per the question, it has formed 512 grams of calcium oxalate. So I will just use stoichiometry, and with the help of stoichiometry, I'll get to know how many grams of calcium carbonate have participated in this reaction. And whatever mass of calcium carbonate has participated in this reaction, that's eventually going to be the pure mass of calcium carbonate. Because in the reaction, it is the pure substance that participates. Impurities do not take part. Now, how do I get to know the mass of pure calcium carbonate? See, guys. First of all, what is the molar mass of calcium oxalate? Calcium has got 40, carbon is 12, 12 into 2 is 24, oxygen is 16, 16 into 4 is 64. This value will come out to be 128 grams. This is the molar mass of calcium oxalate. What is the molar mass of calcium carbonate? Similarly, it's going to be 100 grams, right? So can I say, stoichiometry is telling me just one thing, 128 grams of calcium oxalate, 128 grams of calcium oxalate are produced from 100 grams of calcium carbonate. Therefore, 1 gram of calcium oxalate will be produced from 100 divided by 128 grams of calcium carbonate. Or I can say 512 grams of calcium oxalate would be produced from 100 divided by 128 multiplied by 512. The value comes out to be 400 grams of calcium carbonate. I would say this is the mass of calcium carbonate that has participated in the reaction. This is the mass of calcium carbonate that has participated in the reaction. And that mass of calcium carbonate, which would have participated in the reaction, that's going to be the pure mass of calcium carbonate. Because in the reaction, it is a pure substance that participates. Impurities do not take part, right? So I got the mass of pure calcium carbonate, that is 400 grams. So technically, since when you are introducing oxalic acid, you got to know 400 grams of calcium carbonate have reacted with oxalic acid. And that mass of calcium carbonate that would have reacted with oxalic acid, that is the pure mass, which is how much? 400 grams divided by 410 multiplied by 100. When you solve, the value comes out to be 98%. So I would say percentage purity of calcium carbonate in the sample is 98%. Okay? Am I clear with this? And similarly, my dear students, in the mole concept, there is one more topic that is left. What is that? That is your empirical and molecular formula. Empirical and molecular formula. Empirical and molecular formula. Now, what is the empirical formula? What is molecular formula? What kind of questions can be framed from it? Again, this is one important topic from which a question is frequently asked, right? See, guys. First of all, if I talk about glucose, right? Do you know any formula of glucose? I believe yes. C6H12O6. Everyone of you would be knowing. In glucose, there is carbon, hydrogen, oxygen. What is the atomic ratio of these elements here? It is 6:12:6. This is the atomic ratio of these elements in glucose. 6:12:6. My dear students, can I convert this into simplest form? Can I make this ratio as the simplest ratio? I can do that. It becomes 1:2:1, right? So basically, how many ratios do you see here? 2 ratios. This 1:2:1 is what you call as the simplest whole number ratio. This is what you call a simplest whole number ratio. And this ratio over here, you'll be calling it as the actual ratio. 1 is the simplest whole number ratio. 1 is the actual ratio. As per the actual ratio, the formula is C6H12O6. And as per the simplest ratio, formula should be C1H2O1. So how many representations of glucose do we have here? How many formulas of glucose do we have here? We have 2 formulas. This particular formula is giving you the simplest whole number ratio. This particular formula is giving you the simplest whole number ratio, right? I'll be calling this as the empirical formula. And this particular formula is giving you the actual ratio between the atoms. You call this as the molecular formula, right? So basically, one is called as the molecular formula, one is called as the empirical formula. Empirical formula gives me the simplest whole number ratio between the atoms. Molecular formula gives me the actual ratio between the atoms, right? And at the same time, one more thing. My dear students, with the help of molecular formula, you can calculate molecular mass. And with the help of empirical formula, you can calculate empirical mass. Now, molecular mass can be calculated with the help of molecular formula. This is the molecular formula. Now calculate the molecular mass. 12 into 6 plus 1 into 12 plus 16 into 6. The value comes out to be 180 U. This is the molecular mass of glucose. Now, if you use the empirical formula, 12 into 1 plus 1 into 2 plus 16 into 1, the value comes out to be 30 U. This is what I call as empirical mass. I got the molecular mass, I got the empirical mass. Molecular mass, we calculate with the help of molecular formula. Empirical mass, we calculate with the help of empirical formula, right? Now, my dear students, if you look carefully, there is one more term which I'm defining here. I represent that term with X. And what is X? X is the ratio of molecular mass to that of empirical mass. X is the ratio of molecular mass to that of empirical mass. And remember, once you get X, there is one more formula which I'll be using in the questions. What is that? Molecular formula is always equal to empirical formula multiplied by X. Okay? Molecular formula is always equal to empirical formula multiplied by X. You can check it out also if this formula is valid or not. Tell me, what is the molecular formula for glucose? C6H12O6. What is the empirical formula of glucose? C1H2O1. What is the X value for glucose? X value for glucose, 180 divided by 30, that's 6, right? So this is 6 ones are 6, 6 to 12, 6 ones are 6. So LHS, RHS are coming out to be equal. So remember, molecular formula is equal to empirical formula multiplied by X, right? Did you understand what empirical formula is all about, what molecular formula is all about? Now, my dear students, the point is, how do we calculate the empirical formula? How do we calculate the empirical formula? There is a particular procedure which you have to follow. There's a particular procedure which you have to follow in order to calculate the empirical formula. And what is that procedure? Let's talk about that. Let's talk about that. See guys, for example, I'm starting with the question directly. I'm starting with one question directly. Just give me a second. Okay. Look at this question. Look at this question, guys. Calculate the empirical formula of a compound that contains 26.6% potassium, 35.4% chromium, and 38.1% oxygen by weight. So basically, we have got a compound. And that compound contains potassium, it contains chromium, it contains oxygen. We have got some compound which contains potassium, chromium, oxygen. My dear students, in the question, you will be either given with the mass percentage of these elements, or you will be given with the masses of these elements directly, or you will be given with the mass ratio of the elements. Out of these three things, anything can be given to you. So you have got a compound containing potassium, chromium, oxygen. I am telling you, in the question, you will be either given with mass percentage of these elements, or you will be given with the masses of these elements directly, or you will be given with the mass ratio of these elements. And in this question, we are given with the mass percentage. So tell me, what is the mass percentage of potassium that's given to me? It is 26.6%. What is the mass percentage of chromium that's given to me? 35.4%. What is the mass percentage of oxygen that's given to me? 38.1%. Right? These are the mass percentage of the elements which are given to me. Now tell me one thing. Do I know the atomic masses of the elements which are given to me? Atomic mass of potassium is 39 AMU. Atomic mass of chromium, that is 52 AMU. Atomic mass of oxygen, that is 16 AMU. Right? Well, it will be given in the question like this. 19, 52, and 16. Right? Remember, the first step always is to calculate the atomic ratio. The first step always is to calculate the atomic ratio. How do we calculate atomic ratio? Just you have to do one thing. Whatever things are given to us, just divide these things with respect to atomic masses. Right? So 26.6 divided by 39. 26.6 divided by 39. Similarly, 35.4 divided by 52. Similarly, 38.1 divided by 16. Perfect. When you calculate, this value I believe will come out to be 0.68. Even this value will come out to be 0.68. And this value will come out to be 2.38. These are the values I got. Now tell me which one is the smallest term among all. 0.68. I'm going to divide all of them with the smallest term. Therefore, I'll be getting the least atomic ratio. So 0.68 divided by 0.68. Similarly, 0.68 divided by 0.68. Similarly, 2.38 divided by 0.68. The value comes out to be 1. The value here comes out to be 3.5. So basically, in the compound, there are three elements. Which all? Potassium. In the compound, there are three elements. Which all? Potassium, chromium, oxygen. I got the least atomic ratio as 1:1:3.5. If I ask you, is this ratio the whole number ratio? It is not the whole number ratio. Empirical formula gives you the simplest whole number ratio. This is not the whole number ratio yet. So convert it into whole number. So I'm multiplying this with 2, this with 2, and this with 2. So this becomes 2, this becomes 2, this becomes 7. So I would say the empirical formula will come out to be K2 CR2O7, right? So 2:2:7 is the simplest whole number ratio between these elements, and that particular formula that gives me the simplest whole number ratio, you call that particular formula as the empirical formula. I believe I'm clear with this. Yes? Let's try to solve one more question of this same pattern so that you can understand and analyze things in a better way. See guys, a compound of nitrogen and oxygen was found to contain. You have got a compound that contains nitrogen and oxygen. Well, my dear students, in this particular question, the mass percentage of these, the mass ratio of these elements is given to us as how much? The mass ratio is given to us as 7:16. 7:16. I told you, out of three things, anything can be given, either mass percentage or masses or mass ratio. So mass ratio of elements is given to me. Now, what is the first step? That is atomic ratio. How do we get the atomic ratio? How do we get the atomic ratio? Whatever is given to you, divide with respect to atomic mass. So 7 divided by 14, 16 divided by 16. The value comes out to be how much? 0.5. The value here comes out to be 1. Now, which one is the smallest among the two? 0.5. Now, the second is least atomic ratio. So 0.5 divided by 0.5, that's 1. 1 divided by 0.5, that's 2. So I would say, in the compound, there are two elements, nitrogen and oxygen, and I got the least atomic ratio. That is 1:2, which is the simplest whole number ratio, I would say. So as per this particular ratio, the formula has to be N1O2. So this particular formula is giving me the simplest whole number ratio. I'm calling this particular formula as the empirical formula. But in the question, am I supposed to calculate empirical formula or molecular formula? In the question, they have asked me to calculate the molecular formula. Now, how do you calculate the molecular formula? Molecular formula is nothing but empirical formula multiplied by x. Have we calculated empirical formula? Yes. Now we have to calculate x. What is x exactly? X is molecular mass divided by empirical mass. Is the molecular mass given? No. But vapor density is given. 46. If vapor density is given, can't we calculate molar mass? I've told you molar mass is equal to 2 times the vapor density. So the value comes out to be 92 grams. So if the molar mass is 92 grams, that means molecular mass will be 92 AMU or 92 U. So we have the molecular mass divided by empirical mass. We calculate with the help of empirical formula, right? So I'll be using the empirical formula to calculate empirical mass. Empirical mass will be 14 into 1 plus 16 into 2, which again comes out to be 46. So empirical mass is 46. X value here is coming out to be 2. If the value of X is 2, I would say molecular formula is equal to empirical formula, which is N1O2, empirical formula multiplied by X. And X value we got known as 2. The value is going to be N2O4. This is going to be the molecular formula of the compound. Right? Am I clear, guys? So with this, your empirical molecular formula concept is done and dusted too. And you can expect similar sort of question in your examination too. I'm keeping you one question as the homework in this topic as well. And this is the question. You can consider this as a homework and you can give it a try. Okay? Perfect. Should we move on to the next chapter? We are not going to move on to the next chapter. There is one more topic left in this particular chapter. What is that? That's concentration terms. Okay? It's not going to take me more than like 20 to 25 minutes to complete those concentration terms. So let's complete them here only, so that this chapter gets completed 100%. Okay? See, guys. Now, if I talk about the concentration terms. First of all, I'll be covering all the concentration terms first. And at the end, once I cover all the concentration terms, then I'll do the questions based on the concentration terms as well. Okay? See, guys. Understand. First of all, if I talk about a solution, now one thing which I believe you all will be familiar with, solution has got two components. There are two components which a solution has. One is called as solute, one is called as solvent. Right? Solute is generally present in lesser amount, and solvent would be present in larger amount. Now, I'm not going into the definition of solution and all, definition of solute, solvent, no. I'm just going to talk about those things which are required in the concentration terms. My dear students, from now onwards, solvent you are going to represent with number 1 or letter A. And solute you are going to represent with number 2 or letter B. Solvent you are going to represent with number 1 or letter A. Solute you are going to represent with number 2 or letter B. And at the same time, one more thing. There are few terms which I'm writing, like W, like N, like E, like M. Let me tell you, W stands for mass of the substance, N stands for the moles of the substance, E stands for the equivalent mass of the substance, which we have to discuss later, and M stands for the molar mass of the substance. Okay? Now, my dear students, tell me one thing. For example, if I sometimes write W1, what does it mean? W stands for mass, 1 stands for solvent. That means W1 is nothing but it is the mass of solvent. It represents mass of solvent in grams. For example, sometimes I write N2. N stands for moles, 2 stands for solute. That means I'm talking about the moles of solute. For example, if I write M1, M is molar mass, 1 is solvent. So that means I'm talking about the molar mass of solvent. Right? These are few things which you need to know first of all. And at the same time, one more thing, guys. One more thing. See. Since your solution consists of solute and solvent, your solution consists of solute and solvent. So mass of the solution is purely due to mass of solute as well as the mass of solvent, right? So I can write mass of solution is always equal to mass of solute, which is W2, mass of solvent, which is W1. Similarly, guys, one more thing. Sometimes in the question, they'll mention a term called as aqueous solution. Sometimes in a question, they'll mention a term called as aqueous solution. What is an aqueous solution? Aqueous solution is the one wherein the solvent used is water. Aqueous solution is the one wherein the solvent used is water. Okay? Solvent used is water. Perfect. Now, my dear students, the first concentration term that we are going to discuss here, what is that? You call that as weight by weight percentage of solute. Weight by weight percentage of solute, or you can call it directly as the mass percentage of solute. Now, how do we define it? Mass percentage of solute is simply defined as the mass of solute in grams, which is present in 100 grams of solution. Whatever mass of solute would be present, in 100 grams of solution, that's called as mass percentage of solute. How do we calculate it? What is its formula? Pretty much simple, guys. I'll write weight by weight percentage of solute is equal to the mass of solute in grams divided by the mass of solution in grams multiplied by 100. This is the direct formula with the help of which we can calculate weight by weight percentage of solute, or you call it as the mass percentage of solute. Similarly, sometimes if they ask you to calculate the weight by weight percentage of solvent, it is going to be equal to mass of solvent in grams divided by mass of solution in grams multiplied by 100. This is the formula with the help of which you can calculate weight by weight percentage of solvent, right? My dear students, for example, if I write something like this, 20% weight by weight of NaCl aqueous solution. NaCl aqueous solution. Let's say this is the statement I'm writing. Now tell me one thing. What does this aqueous mean? Aqueous means the solvent uses water. If the solvent is water, that means NaCl becomes your solute. NaCl becomes your solute, right? NaCl becomes your solute. Now, this is 20% weight by weight of solute. What does that mean? That means, as per definition, 20 grams of solute are present in 100 grams of solution. Correct? This is your concentration term number 1. Concentration term number 2. What is that? That is weight by volume percentage of solute. How do I define the weight by volume percentage of solute? My dear students, it's again pretty much simple. Let me write its definition. Definition says that weight by volume percentage of solute is nothing but it is defined as the mass of solute in grams which is present in 100 ml of solution. The mass of solute in grams which is present in 100 ml of solution. So whatever mass of solute would be present in 100 ml of solution, you'll be calling that as weight by volume percentage of solute. Now again, it has got formula as well. So I'll say weight by volume percentage of solute will be equal to mass of solute in grams divided by volume of solution in ml multiplied by 100. This is the formula to calculate weight by volume percentage of solute. Similarly, if I ask you to calculate weight by volume percentage of solvent, it will be directly equal to mass of solute in grams, sorry, not mass of solute, mass of solvent in grams, mass of solvent in grams divided by volume of solution in ml multiplied by 100. This is the formula with the help of which you can calculate weight by volume percentage of solvent, right? And similarly, guys, if I write a statement like this, if I write 20% weight by volume of NaCl aqueous solution, what does it mean now? It means that 20 grams of your solute, 20 grams of your NaCl are present in 100 ml of solution, because I've used the term weight by volume here, right? Perfect. Now, similarly, guys, let's move on to the third concentration term. And what is my third concentration term? Before writing the third concentration term, there is one important result which I would want every one of you to take a note of. A result is, I'm writing it directly, I'm not deriving it. Weight by volume percentage of solute is always equal to weight by weight percentage of solute multiplied by density of solution. And this density of solution is taken in grams per ml. This is one direct result that relates weight by weight and weight by volume. Okay? It has got derivation as well, but I've got nothing to do with the derivation right now. Now, my dear students, I'm going on to the third concentration term. That's volume by volume percentage of solute. How do we define volume by volume percentage of solute? Volume by volume percentage of solute is defined as, it is defined as the volume of solute in ml, that is present in 100 ml of solution. The volume of solute in ml that is present in 100 ml of solution. Okay? So whatever volume of solute would be present in 100 ml of solution, you'll be calling that as V by V percentage of solute. Again, how do I write its formula? Its formula is also simple. If I write V by V percentage of solute, it's going to be equal to volume of solute in ml divided by volume of solution in ml multiplied by 100. This is the formula with the help of which you can calculate volume by volume percentage of solute. Similarly, if they ask you to calculate volume by volume percentage of solvent, it's going to be equal to volume of solvent in ml divided by volume of solution in ml multiplied by what? Multiplied by 100. This is the formula with the help of which you can calculate volume by volume percentage of solvent. Now, similarly, my dear students, if I ask you to decode this statement, I'm writing 20% volume by volume of NaOH aqueous solution. What would be its meaning? What does it mean? It means that 20 ml, since it's V by V, so 20 ml of solute is present in 100 ml of the solution. Is present in 100 ml of the solution, right? Perfect. Perfect, guys. Now, similarly, if I talk about the fourth concentration term, what is my fourth concentration term here? My fourth concentration term here will be mole fraction. Mole fraction. My fourth concentration term will be here, the mole fraction. For example, I want to define the mole fraction of solute. Mole fraction of solute is simply defined as number of moles of solute in the solution divided by total moles present in the solution. Mole fraction of solute is nothing but number of moles of solute in the solution divided by total moles present in the solution. Similarly, if I talk about the mole fraction of solvent, let me tell you, mole fraction of solvent is nothing but number of moles of solvent divided by total moles present in the solution. Mole fraction of solvent is equal to moles of solvent divided by total moles present in the solution, right? Now, guys, comes the most important concentration term. You call that as the molarity. Molarity, which we represent with capital M, right? How do we define molarity? Molarity, in short, is defined as number of moles of solute present in 1 liter of solution. The number of moles of solute which would be present in 1 liter of solution. Number of moles of solute which would be present in 1 liter of solution, you call that as molarity. For example, if I say in 1 liter solution there are 2 moles of solute, that means molarity of the solution is 2. In 1 liter solution there are 10 moles of solute, that means molarity of the solution is 10. In 1 liter solution there are 20 moles of solute, molarity of the solution is 20. Simple. And what are its formulas? Molarity, the first formula, number of moles of solute divided by volume of solution in liters. Divided by volume of solution in liters. This is the volume of solution here. This is the first result with the help of which we can calculate molarity. Second, you can write mass of solute in grams multiplied by 1000 divided by molar mass of solute and volume of solution in ml. This is the second result which we can use to calculate molarity of the solution, right? The third result, one direct result, 10 multiplied by weight percentage of solute multiplied by density of solution divided by molar mass of solute. One more result, one direct result from which question can be framed. Or one more result, 10 multiplied by weight by volume percentage of solute divided by molar mass of solute. This is one more result with the help of which you can calculate molarity of the solution. There is one more result with molality as well, but that's something I'll tell you in some time, right? So these are few results which you have to remember to calculate molarity of the solution. I have not derived any result here. I'm just giving you the results and I'll show you its application in the form of questions, right? Now guys, if I ask you, what are the units of molarity? It's going to be moles per liter. Moles per liter. Or you call it directly as molar. So for example, that means if I write 2 molar, NaCl aqueous solution, what does it mean? If I write 2 molar NaCl aqueous solution, it means that 2 moles of solute, which is NaCl, will be present in 1 liter of solution. Now one more thing, remember this molarity is temperature dependent. It is temperature dependent concentration term. Temperature dependent concentration term. So basically, any concentration term whose formula includes volume. Any concentration term whose formula includes volume. Do you see volume here? Yes. So that concentration term will be temperature dependent because volume depends on temperature. See, volume depends on temperature, right? And molarity depends on volume. That means molarity and temperature, they are related. And how they are related, you can talk about that as well. Remember, on increasing the temperature of the solution, volume of the solution increases, due to which molarity decreases. On increasing the temperature, volume of the solution increases. If volume of the solution increases, that means molarity of the solution will automatically decrease, right? So similarly, guys, there is one more important concentration term which we have, that is molality. How do we define molality? Molality is first of all defined, it is represented by small m, and how do we define it? Number of moles of solute. Number of moles of solute which are present in 1 kg of solvent. Which are present in 1 kg of solvent. What was molarity? What was molarity? What was molarity? Molarity was number of moles of solute present in 1 liter of solution. This is 1 kg of solvent here, right? And what is going to be its formula? The first formula is number of moles of solute divided by mass of solvent in kg. The first formula. Second is going to be simply mass of solute in grams multiplied by 1000 divided by molar mass of solute multiplied by mass of solvent in grams. Second formula. Third formula is mole fraction of solute multiplied by 1000 divided by 1 minus mole fraction of solute multiplied by molar mass of solvent, right? One more formula. 1000 multiplied by molarity divided by 1000 multiplied by density of solution minus molarity multiplied by molar mass of solute. So from these results, a lot of times direct questions are asked. I'll show you in some time. Like there will be some questions in which molarity will be given and they'll ask you to calculate molality. Directly use the result. There'll be some questions in which mole fraction of solute will be given and they'll ask you to calculate molality. So you can use direct result. No need to use your brain a lot in these questions. Okay. Now, if I ask you what are the units of it, it's going to be mole per kg. Unit of it is going to be mole per kg. Or you can call it as molal. You can call it as molal as well. Okay. For example, if I sometimes write like this, I'm writing 2 molal NaCl aqueous. What does it mean? It means that 2 moles of solute, 2 moles of NaCl are present in 1 kg of solvent. 1 kg of solvent. Now, if I ask you, is molality temperature dependent or independent? Molality is temperature independent concentration term. Because if you look at its formula, there is no volume included in this formula. Okay? There is no volume included in this formula. I believe this is also clear. I believe this is also clear. Right? And if this is clear, guys, let's have a look on one more concentration term. What is that? Well, I'm not going to discuss normality here. Normality I'll be discussing in the next chapter, redox reactions. Okay? Next concentration term is going to be your parts per million, ppm of solute. ppm of solute. How do we define parts per million of solute? Again, simple. It is defined as the mass of solute. I'm writing the definition as per mass. Mass of solute in grams, which is present in 10 raised power 6 grams of solution. Which is present in 10 raised power 6 grams of solution. Mass of solute in grams, which is present in 10 raised power 6 grams of solution. And what about its formula? Its formula is like this. Mass of solute in grams divided by mass of solution in grams multiplied by 10 raised power 6. This is its direct formula, with the help of which you can calculate parts per million of solute. And similarly, there is one more term. What is that? That's parts per billion of solute. Parts per billion of solute. What is parts per billion of solute? We define it like this. It is the mass of solute in grams, which is present in 10 raised power 9 grams of solution. And how do we, what is its formula? Its formula will be mass of solute in grams divided by mass of solution in grams multiplied by 10 raised power 9. Multiplied by 10 raised power 9. So these are all the concentration terms and their formulas, right? Which you were supposed to know. So first of all, let's try to solve few questions which will make things very much clear to you. This is the first question on your screen. Can we give it a try? Can we give it a try? Absolutely we can. See guys, calculate the molality of the solution containing 10% weight by weight of NaOH aqueous solution. First thing, do we know how to decode this particular statement? The statement is 10% weight by weight of NaOH aqueous solution. It means that 10 grams of NaOH are present in 100 grams of solution. Right? This is its meaning. 10 grams of NaOH are present in 100 grams of solution. So basically, I got the mass of solute. Mass of solute we represent with W2. That will be 10 grams. Mass of solution is how much? Mass of solution is 100 grams. Therefore, what would be the mass of solvent? If mass of solution is 100, mass of solute is 10. So mass of solvent would be 90 grams. Similarly, what is the molar mass of solute? What is the molar mass of NaOH? What is the molar mass of solute? Molar mass of NaOH. That is nothing but 40 grams. What do I need to calculate? I need to calculate molality. Few minutes back, I gave you a result. Molality is equal to W2 multiplied by 1000 divided by M2 multiplied by W1 in grams. So what is W2? That is 10 multiplied by 1000 divided by molar mass of solute. Molar mass of solute is 40. Mass of solvent in grams is how much? That is 90. Matter of calculation, do it and solve. That's it. Yeah. Similarly, for example, this is the question. Calculate the mole fraction of solute in 10% weight by weight of NaOH aqueous solution. Calculate the mole fraction of solute present in 10% weight by weight of NaOH aqueous solution. So first of all, what is the meaning of 10% weight by weight of NaOH? It means that 10 grams of NaOH are present in 100 grams of solution, which again means the mass of solute is equal to 10 grams. Mass of solvent is equal to 90 grams, right? What do I need to calculate? I need to calculate mole fraction of solute. How do you calculate mole fraction of solute? It is number of moles of solute divided by total moles present in the solution. Number of moles of solute divided by total moles present in the solution. Now, First of all, in order to calculate mole fraction, I need N1 and N2. So first of all, what is N2? N2 means number of moles of solute, which will be mass of solute divided by molar mass of solute. Mass of solute is 10 grams. Molar mass of solute is 40. The value comes out to be 1 by 4. Similarly, N1, number of moles of solvent, will be equal to mass of solvent divided by molar mass of solvent. So it's 90 divided by molar mass of solvent. Solvent here is water because the solution is aqueous. If it is aqueous here, the solvent is water and molar mass of water is how much? 18. So this value comes out to be 5. So I can directly calculate mole fraction of solute here, which is number of moles of solute, 1 by 4 divided by number of moles of solvent, that's 5 plus 1 by 4. The value comes out to be how much? I think 1 by 21, yeah? So this is the mole fraction of solute here. Yes? So directly just use the formulas and we are done. Right? Directly we are supposed to use the formulas and we are done. Similarly, if you look at this particular question, calculate the molality of a 2 molar solution. So molarity is given. Molality is to be calculated. I gave you one direct result between molality and molarity. This was the result, right? Molarity is given as 2. Density of solution is given to you. M stands for molarity, that's given. Molar mass of solute, molar mass of NaOH, that is 40. Again, this calculation you have to do and you are done. Right? If you just remember the formula, you don't have to use your brain a lot. You don't have to use your brain a lot. Okay, look at this question. Look at this question, for example. Dissolving 120 grams of urea in 1000 grams of water. Look at this question carefully. So we are dissolving 120 grams of urea in what? In 1000 grams of water. So when you will be dissolving urea in water, you will be getting a solution here, right? As per the question, density of this solution is given. How much? 1.15 grams per ml. I need to calculate what? I need to calculate molarity. There is one of the formula of molarity, that is mass of solute multiplied by 1000 divided by molar mass of solute multiplied by volume of solution in ml. This is one of the formulas to calculate molarity. Now let's first of all see what all things are we given with. See, among urea and water, which one is present in lesser amount? That's urea. So urea is my solute here. So what is the mass of solute? That's 120 grams. What is the mass of solvent? That is 1000 grams, right? What would be the mass of solution? Mass of solution would be this plus this, 1120, right? Mass of solution we know. What is the molar mass of solute? Molar mass of urea. Let me tell you, urea, its molar mass is 60 grams per mole. If you do not know the formula of urea, its formula is NH2CONH2. This is the molecular formula of urea, right? Its molar mass is 60. Perfect. So basically, W2 value is given to me, M2 is given to me. I just need volume of solution. Volume of solution I can calculate from density. Since density of solution means mass of solution divided by volume of solution. And this, as per the question, is 1.15. So I'll say volume of solution will be equal to mass of solution divided by 1.15. What is the mass of solution? 1120 divided by 1.15. When you solve this, the value comes out to be 973 ml. Right? This is the volume of solution. So you got all the terms. Put all the terms in this equation and get the molarity of the solution. Right? You should be in a position to solve this. Perfect. Now similarly, one more type of question that can be asked. Calculate the mole fraction of solute. Calculate the mole fraction of solute in 0.1 molal aqueous solution. So technically, molality of the solution is given, 0.1. Aqueous is used. That means solvent is water. And molar mass of water is how much? Molar mass of solvent is 18 grams. All right. And what do I need? I need the mole fraction of solute. I gave you one result which directly relates molality with mole fraction. If you remember, molality is equal to mole fraction of solute multiplied by 1000 divided by 1 minus mole fraction of solute multiplied by molality of solvent. Sorry, divided by molar mass of solvent. Now, what is M? M is 0.1 is equal to chi2 into what? Into 1000 divided by 1 minus chi2 into what? M1. M1 is 18. Do you see? One equation, one unknown, cross multiple and get the value of chi2. Chi2 is mole fraction of solute, which you were supposed to calculate. Right? Simple, correct? If you just know the results, you are done. You are sorted. If you just know the results, you are done. Right, people? Let me know in the chats. Perfect. Is it clear, guys? All right. There is one more thing which you need to know. What is that? That is molarity of dilution and molarity of mixing. Well, let me tell you that too. But I'm not going into the depth of it. I'll just give you the formula and I'll show you how to use it. If I talk about the molarity of dilution. Molarity of dilution. What is molarity of dilution exactly? First of all, I told you a few minutes back, molarity is equal to number of moles of solute divided by volume of solution in liters. So I can say number of moles of solute will be equal to molarity into volume of solution in liters. Number of moles of solute will be equal to molarity of the solution multiplied by volume of solution in liters, right? Now, for example, imagine you have got a container and this container contains a solution. It contains a solution. For example, the solution is, let's say, HCl aqueous. Just to make you understand, HCl aqueous solution is there in the container. Let's say molarity of this solution is M1, volume of this solution is V1. If I ask you how many moles of solute will be there in this solution, number of moles of solute is molarity into volume. M1 multiplied by V1 will give you number of moles of solute right now in the container. Okay. Now tell me, have I done any dilution yet? What is dilution? Dilution means addition of extra solvent. Dilution means addition of extra solvent. So I have not added some extra solvent yet. I have not added some extra solvent yet. I have not done the dilution yet. So these are the number of moles of solute present in the container before dilution, right? Now, if you are adding some extra solvent as well, if you are adding some extra solvent in the container, that means you are doing the dilution. If you are doing the dilution, what will happen to the volume of this solution? What will happen to the volume of this HCl aqueous solution? Volume of this solution will definitely increase. Let the new volume of the solution be V2. If volume changes, if volume increases, that means molarity has to decrease. So molarity of this solution initially was M1. Now let it be M2. So due to dilution, first of all, does molarity increase or decrease? Molarity decreases, right? And volume increases. Perfect. Now, this is the case which we have after dilution. After dilution, the solution which we have, its molarity is M2, volume is V2. So if I say M2 multiplied by V2, this gives me number of moles of solute present in the container after dilution. How many moles of solute were there in the container before dilution? M1, V1. How many moles of solute are there in the container after dilution? M2, V2. Just tell me one thing. Just tell me one thing. Just one thing. Tell me, what have I done? I've just added solvent. I've just added solvent into the container. Have I done anything with the solute? I have done nothing with the solute. I have done nothing with the solute. So whatever solute was there in this container, same amount of solute will be there in this container because I have not changed solute anything. I have not done anything with the solute. I have just added solvent. Nothing done with the solute. So I'll just use one simple statement. I'll say number of moles of solute before dilution has to be equal to number of moles of solute after dilution. Number of moles of solute before dilution, which is M1, V1. Number of moles of solute after dilution, that is M2, V2. And this particular result is what you call as your dilution formula. And for example, if they ask you, calculate the volume of the solvent added, how much solvent you have added, you can say initial volume of the solution was V1. Then you added some extra solvent. So final volume of the solution became V2. So volume of the extra solvent added will be nothing but V2 minus V1. right? So you can just solve this question and tell me its answer quick, very quick. How much water should be added to 200 ml of 2 molar solution of HCl to make its concentration 0.2 molar? So basically, initial molarity of the solution is given as 2. Initial volume of the solution is given as 200 ml. This is your solution. Now you are doing some dilution. You are adding some solvent, due to which final molarity of the solution is coming out to be 0.2, and let the final volume of the solution be V2. Then this is the case of dilution. So I can use the dilution formula. M1V1 is equal to M2V2. What is M1? That is 2. What is V1? That is 200. What is M2? 0.2. V2, I'll be calculating here. When you calculate V2, it will come out to be 2000 ml. Right? But am I supposed to calculate V2? Am I supposed to calculate final volume? Am I supposed to calculate final volume of the solution? No. I need to calculate the volume of extra solvent added. What was the initial volume of the solution? 200 ml. What is the final volume of the solution? 2000 ml. What is the initial volume of the solution? 200 ml. What is the final volume of the solution after dilution? That is 2000 ml. That means how much solvent you have added. How much extra solvent you have added. It's going to be V2 minus V1. So 2000 minus 200 comes out to be 1800 ml. It means that 1800 ml. It means that 1800 ml of solvent has to be added. Then only molarity of the solution will go from 2 to 0.2. Yes? Am I clear, guys, with this particular topic? Same goes for the molarity of mixing of non-reacting solutions. So if you talk about the molarity of mixing, of non-reacting solutions, for example, this is your solution number 1. Let's call this as HCl aqueous solution. Let's say its molarity is M1. Let's say its volume is V1. Similarly, for example, you have got a container here, right? Let's say this container also contains HCl aqueous solution. For example, its molarity is M2. Its volume is V2. Now you are mixing them. When you mix them, you'll be getting a final solution here. Let the molarity of this final solution be MR. Let the volume of this final solution be VR, which is going to be V1 plus V2 if the final solution is ideal in nature. Right? Now again, how many moles of solute are there in this container? M1 into V1. How many moles of solute are there in this container? M2 multiplied by V2. How many moles of solute will be there in this container? It's going to be MR multiplied by VR. Right? Before this arrow, this is the case of before mixing. I've not mixed them yet. Before mixing. And this is the scenario which we have after mix. This is the after mix scenario, right? So since we are adding the two solutions, so can I say the amount of solute which was present in this container plus the amount of solute which is present in this container, all that solute would have reached into this container, right? Because you are mixing them up in this particular container. Right? So whatever solute you add in this, plus whatever solute you add in this, all that solute will be finally going here, right? So I'll say number of moles of solute before mixing has to be equal to number of moles of solute after mixing. And number of moles of solute before mixing is M1 V1 plus M2 V2. These are the total moles of solute before mixing. Has to be equal to total moles of solute after mixing. So this is one more result with the help of which you can calculate the final molarity of the solution, right? And my dear students, with this, my mole concept chapter is done and dusted. This is its one application. Perfect. The simple application of it. You are mixing the two solutions. You are supposed to calculate molarity of the resulting solution. It's going to be same. M1 V1 plus M2 V2 divided by VR. VR is nothing. V1 plus V2. All the parameters are given. You just have to put the values. Okay. So with this, we are done with the mole concept chapter. Right. Let's take a small break for 15 minutes. Okay. A small break for 15 minutes. Okay. And then we'll be starting the next chapter. The next chapter will be either equilibrium or redox. I think we'll go with redox because redox will take lesser time to complete. Okay? I think we'll go with redox. Redox will take lesser time to complete. Okay? It is 3:27. So we have got break till 3:45. Okay? But be back on time. That is my only request to you. Be back on time. Guys, can you hear me? Am I again audible, visible to everyone? Yes. Am I again audible, visible to everyone? All right, welcome back, welcome back, welcome back. So now we are going to start one more chapter. That's going to be a redox reaction. Again, one important chapter this is. Okay, and this is the easy chapter also. You know it already, I think. Okay, and I believe this is not going to take a lot of time because it's a small chapter. So should we start? Should we start? Should we start? Everyone wants in the chats. Is everyone ready? Is everyone ready? Perfect, guys. So let's get going then. Let's get started with the new chapter, which is your redox reactions. Okay. So my dear students, the first thing which we have to study in redox reaction, what is that? What is your oxidation state? That is your oxidation state. First of all, if I ask you what is oxidation state? Oxidation state in simple words is defined as the charge present on an atom of an element. The charge present on an atom of an element in a given compound. In a given compound. What it means exactly. What it means exactly. Let's try to understand. Or before making you understand this particular point, let me write down few points here so that it becomes properly clear to you. See, the charge present on an atom of an element in a given compound is called as oxidation state. The point number two, the charge can be real or virtual. Charge can be real or virtual. In ionic compounds, the charge is real. And in case of covalent compounds, let me tell you, the charge is virtual. Now let's try to understand what all of this exactly means. Okay? Let's try to understand what all of this exactly means. See, guys. For example, I am taking an ionic compound here. Let's say I'm taking an ionic compound. Now, you know what is the most typical example of ionic compound? Most common example of ionic compound, that is NaCl, right? My dear students, in case of NaCl, how many elements do you see? There are two elements, sodium and chlorine. You know, sodium is metallic in nature and chlorine is non-metallic in nature. And you must be knowing metals have got the tendency to lose electrons and non-metals have got the tendency to gain electrons. If I talk about sodium, since sodium has got only one electron in its outermost shell, so it is easily going to lose this electron and get converted into Na positive. If you talk about chlorine, chlorine has got 7 electrons in its outermost shell. So I would say this electron, which is given by sodium, chlorine is going to take this one electron, it is going to gain this one electron and get converted into Cl negative. So basically, a cation got formed as well as the anion got formed. Now between these oppositely charged ions, there will be electrostatic force of attraction. Between these oppositely charged ions, there will be electrostatic force of attraction. And this electrostatic force of attraction here is what you call as the ionic bond. It is called as the ionic bond. And that particular compound in which this ionic bond exists, that compound is called as the ionic compound. That particular compound in which ionic bond exists, you call that particular compound as the ionic compound. Now, my dear students, if I talk about this NaCl, we got to know that in NaCl, it is actually Na positive here. In NaCl, it's actually Cl negative here. Now, if I ask you, do you see any charge present on sodium? Yes, the charge is +1. If I ask you, do you see any charge present on chlorine? Yes, the charge is -1. And the charge present on an atom of an element, the charge present on an atom of an element is what you call as oxidation state. So I would say the sodium here is in +1 oxidation state. This chlorine here is in -1 oxidation state, right? The charge present on an atom of an element. If I talk about the sodium, there is +1 charge present on one atom of sodium. There is -1 charge present on one atom of chlorine. And the charge present on one atom of an element is what you call as the oxidation state. So you got to know, in case of NaCl, the oxidation state of sodium is +1, the oxidation state of chlorine is -1. Now, at the same time, do you see complete loss and gain of electrons happening here? Sodium is losing one electron completely. Chlorine is gaining one electron completely. So complete loss and gain of electrons is happening. And due to complete loss and gain of electrons, the charges which come on atoms, they are basically the real charges. So real charges arise on the atoms due to the complete loss and gain of electrons. So in case of ionic compounds, whatever will be the charges on the atoms, these are the real charges because they arise due to the complete loss and gain of electrons, right? Similarly, my dear students, if you talk about the covalent compound, for example, I'm taking an example like this. Let's say there is a covalent bond between A and B. Right? I'm assuming B is more electronegative than that of A. So what's going to happen? If B is more electronegative than that of A, I will say B will have more tendency to attract the bonded pair of electron towards itself, due to which this B gets delta negative and A gets delta positive. So if you ask me what is the oxidation state of A here, it's again +1. Oxidation state of B here, it is -1. But are these the real charges? No, these are not the real charges. Real charges arise due to complete loss and gain of electrons. There is no complete loss and gain of electrons. It is just the shifting of electron pair. And due to the shifting of electron pair, when the charges come on the atoms, these charges are called as the virtual charges, right? So this is basically the virtual charge. This is also the virtual charge. I believe this is clear to everyone. I hope you got to know what oxidation state exactly is all about. The charge present on an atom of an element. The charge can be real as well as virtual. In case of ionic compounds, due to complete loss and gain of electrons, the charges on the atoms are real. And in case of covalent compounds, due to the shifting of electron pairs, these charges are not real, these are virtual, right? Now, people, let's try to understand few important things. For example, you talk about your HF molecule. This is HF. Which one is more electronegative, hydrogen or fluorine? Absolutely fluorine. So I would say fluorine has got more tendency to attract the electron pair towards itself, due to which fluorine gets delta negative, hydrogen gets delta positive. If I ask you what is the oxidation state of hydrogen, it has to be +1. Oxidation state of fluorine, -1. Now, if I ask you, are these real charges? No, these are not real charges. These are virtual charges. Real charges arise due to complete loss and gain of electrons. But here only shifting of electron pair is happening due to the electronegativity difference between the atoms. Okay? Now, my dear students, let's talk about, I hope you got the concept of idea of what oxidation state is. Now, there are some rules which we have to follow in order to calculate oxidation state. There are some rules to calculate the oxidation state. Okay? Now, what are the rules? Let's have a look one by one. My dear students, rule number 1. Let me tell you oxidation state of an element. Oxidation state of an element in free state, or elemental form, or I can say or allotropic form. or allotropic form is taken as 0. Is taken as 0. What does that mean? Let's have a look. For example, what is the free state of hydrogen? That's H2. What is the free state of nitrogen? That's N2. What is the free state of oxygen? That's O2, right? So whenever you see an element present in the free state, its oxidation state is taken as 0. Similarly, for example, iron in nature exists as Fe, zinc in nature exists as Zn, copper in nature exists as copper, right? So these elements are also present in their free state. Their oxidation state will be taken as 0 as well. Similarly, for example, carbon. Carbon has got two main allotropes. What is that? One is graphite, one is diamond. Whenever you see an element in allotropic form, its oxidation state is also taken as 0. So whenever you see an element in free state, that means that particular state in which the element exists in nature, right? Its oxidation state will be taken as 0. Whenever you see an element in elemental form, its oxidation state is 0. Whenever you see an element in allotropic form, its oxidation state again will be taken as 0. This is rule number 1, which you are going to remember. Rule number 2. Rule number 2, your group first elements, which you call as your alkali metals, Let me tell you, alkali metals, your group first elements, they show the oxidation state of +1. And similarly, if you talk about your group second elements, you call them as the alkaline earth metals. Let me tell you, their oxidation state is taken as +2. Your group first elements will always show the oxidation state of +1, and group second elements, they are going to show the oxidation state of +2. This is your rule number 2, which you have to remember. Now you must be thinking, what are group 1 and what are group 2? Your lithium, sodium, potassium, rubidium, cesium, they are your group first elements. They are always going to show +1 oxidation state. Similarly, beryllium, magnesium, calcium, strontium, barium, they are your group second elements, so they are going to show the oxidation state of +2. Okay. Similarly, my dear students, rule number 3. Rule number 3 is basically for hydrogen. Rule number 3 is basically for hydrogen. Rule number 3 is for hydrogen. Let me tell you, whenever hydrogen will be present in its free state, what is the free state of hydrogen? That's H2. This is the free state of hydrogen. Its oxidation state will be taken as 0. Right? Similarly, whenever you see hydrogen attached to more electronegative element than itself, remember the oxidation state of hydrogen is taken as +1. You can take the example. For example, you have got water, H2O, you have got HF. Over here, hydrogen is attached with more electronegative element than itself. Hydrogen attached with more electronegative element than itself. Hydrogen attached with more electronegative element than itself. Whenever hydrogen will be attached with more electronegative element than itself, its oxidation state will be taken as +1. Similarly, when you see hydrogen attached to less electronegative element than itself, its oxidation state will be taken as -1. For example, you talk hydrides, you talk about metal hydrides. For example, you have got NaH, sodium hydride, you have got MgH2, right? Whenever your hydrogen will be attached to metals, right? So I would say, at that point of time, the oxidation state of hydrogen will be taken as -1, because your metals, they are less electronegative than hydrogen. So these are the 3 things which I want you guys to remember about what? About hydrogen. Similarly, rule number 4. My dear students, rule number 4 I'm going to give you for oxygen. Rule number 4 is basically for oxygen. And oxygen, this is something which you have to remember. And for oxygen, before oxygen, one more thing I forgot to tell you. Remember, the most common oxidation state, the most common oxidation state of hydrogen is basically +1. The most common oxidation state of hydrogen is +1. Okay? And people, let's have a look and talk about oxygen. Number 1, whenever you see oxygen present in its free state means O2. This is the free state of oxygen. Whenever you see oxygen present in its free state, its oxidation state will be taken as 0. Number 2, whenever you see oxygen attached to less electronegative element than itself, its oxidation state will be taken as -2. For example, you have got MgO. For example, you have got H2O, right? You have got Cl2O. You have got Cl2O. Everywhere oxygen is attached with less electronegative element than itself. So its oxidation state everywhere is going to be -2. Similarly, whenever you see oxygen attached to more electronegative or leave more electronegative right now, let's first of all talk about few more important compounds which oxygen shows. My dear students, let me tell you, oxygen forms some important compounds. You must have heard about peroxides. You must have heard about peroxides. You must have heard about superoxides. Maybe you would have heard about oxyfluorides as well. Oxyfluorides. Maybe you would have heard about ozonide as well. These are the special compounds which oxygen forms. Peroxide. Whenever you see oxygen in this form, O2 dinegative. Whenever you see oxygen in this form, O2 dinegative, that means it's a peroxide. Whenever you see oxygen in the form of O2 negative, it's a superoxide. In case of peroxides, the oxidation state of oxygen is taken as -1. In case of superoxides, the oxidation state of oxygen is taken as -1/2. Okay? See, on 2 oxygen atoms, the charge is -2. On 2 oxygen atoms, charge is -2. Therefore, on 1 oxygen atom, charge will be -1. Right? And the charge present on 1 atom of an element is called as oxidation state. On 2 oxygen atoms, the charge is -1. So on 1 oxygen atom, the charge will be -1/2. Right? And the charge present on 1 atom of an element is called as oxidation state, which is -1/2 here. Right? Similarly, if I talk about ozonide, leave the oxyfluoride aside. If I talk about ozonide, in case of ozonide, oxygen exists in this form, O3 negative. Right? On 3 oxygen atoms, the charge is -1. So on 1 oxygen atom, the charge will be -1/3. So whenever oxygen forms ozonide, its oxidation state is taken as -1/3. Right? Similarly, if I take the examples, for example, you have got H2O2, hydrogen peroxide. Hydrogen peroxide, right? If you look at its structure, this is its structure, H2O2. Correct? Now, my dear students, think logically. This is the bond between oxygen and hydrogen. Which one is more electronegative? Oxygen. So this bond pair will be shifted towards oxygen, due to which oxygen gets -1, hydrogen gets +1. This bond pair again will be shifted towards oxygen. So -1, +1. Nothing will happen due to this particular bond, because on one side there is oxygen, on another side also there is oxygen. Right? So the charge present on 1 oxygen atom here is -1. Okay? Similarly, my dear students, superoxide. For example, you have got KO2, potassium superoxide. KO2, potassium superoxide. Now, how do you get to know whether this is superoxide or not? See, this is KO2, correct? If I break it, KO2, potassium belongs to group 1. Group 1 is going to show +1. If group 1 shows +1, that means this one should show -1. Then only the entire compound is going to be neutral, right? So on 2 oxygen atoms, the charge is -1. So on 1 oxygen atom, the charge will be -1/2. So your example here is KO2. Similarly, in case of ozonide, it forms potassium ozonide, KO3. KO3. See, KO3 actually, potassium belongs to group 1. It's going to show +1. If there is +1 on potassium, that means on this part there should be -1. That's how +1 -1 neutralizes. So on 3 oxygen atoms, charge is -1. So on 1 oxygen atom, the charge will be -1/3. Correct? Similarly, in case of your oxyfluorides, in oxyfluorides, there are 2 examples. One is your OF2, one is your O2F2. Remember, the oxidation state of oxygen in OF2 is +2. The oxidation state of oxygen in O2F2 is +1. This is the set of oxidation states. This is the range of the oxidation states which oxygen shows. Okay? So you have to remember, oxygen shows 0 also, -2 also, -1 also, -1/2 also, +1, +2, -1/3. This is the range set of oxidation states which oxygen shows, which you have to remember. Okay? Now, similarly, guys, the next point. This was about oxygen. Next rule is for halogens. Next rule is for halogens. If I talk about your halogens, first thing, whenever you see halogen present in its free state, halogen means your group 17. Halogen means group 17. Chlorine, chlorine, bromine, iodine, astatine. Right? In case of your halogens, whenever you see halogen present in free state, its oxidation state will be directly taken as 0. Right? Whenever you see halogen I'm representing with X, whenever you see halogen present with less electronegative element than itself, the oxidation state of halogen will be taken as -1, right? Can halogens show positive oxidation state? Yes, halogens can show positive oxidation state. If halogen is attached to more electronegative element than itself, the oxidation state of halogens can be positive. If I take the examples, for example, you have got the compound BRF3. I want to calculate oxidation state of this bromine. Bromine is the halogen, right? For example, you have got IF7. I want to calculate oxidation state of iodine here. For example, Cl2O. I want to calculate oxidation state of chlorine here. Now, if you talk about bromine here shows +3 oxidation state. Iodine shows +7 oxidation state. Chlorine here shows +1 oxidation state, right? So halogens can show positive oxidation states as well when they are attached to more electronegative element than itself. And these compounds here, where do you see two halogens have formed a compound? Two halogens have formed a compound. So you call these compounds as the interhalogens. So in case of your interhalogens, I must say the oxidation state of halogens can be positive as well. Okay, I believe this is clear. And my dear students, if this is clear, then there is one more thing which I want to tell you. What is that? If you talk about your p block elements, my dear students, your p block elements, they show variable oxidation states. They show range of oxidation states. And what is the range of oxidation states p block elements shows? The range of oxidation state will be group number -18 to group number -10. Group number -18 to group number -10. For example, if I take the case of phosphorus, phosphorus is a group 15 element. Its group number is 15. So what is the range of the oxidation states here? Group number -18. So 15 minus 18 is -3. 15 minus 10 is +5. Right? So your phosphorus, its range of oxidation states will be -3 to +5. For example, if I talk about chlorine, chlorine belongs to group number 17. It's a p block element. So its range of oxidation states will be group number -18. So 17 minus 18 is -1. 17 minus 10 is +7. Right? Perfect. So your p block elements, they show a range of oxidation states basically. Yeah? I believe this is clear. Similarly, remember one thing. There are two d block elements which I want you guys to remember, which I'll be frequently using here. One is going to be your chromium, one is going to be your manganese. Remember, the maximum oxidation state, highest oxidation state shown by chromium will be +6, and highest oxidation state shown by manganese will be +7. You'll be using these in the questions in some time. Okay? Are all the things clear till here? Right. Similarly, guys, there are a few more things. When you talk about a coordinate bond, I hope you know what is a coordinate bond. If you talk about your coordinate bond, for example, the coordinate bond is like this: A, arrow towards B. This is a coordinate bond between A and B. Let's say this A is the donor atom here. This B is the acceptor atom. Now remember, if electronegativity of donor is less or equal to the electronegativity of acceptor. If electronegativity of donor is less or equal to electronegativity of acceptor, at that time, the donor shows the oxidation state of +2, acceptor shows the oxidation state of -2. But remember, if electronegativity of donor is greater than the electronegativity of acceptor, so remember at that point of time, oxidation state shown by donor is 0 and oxidation state shown by acceptor also is taken as 0. Oxidation state of acceptor also is taken as 0. Right? Perfect. I hope this is clear. And my dear students, one more thing. Remember, the sum of oxidation states of all the atoms present in a molecule is always equal to the net charge is always equal to the net charge present on the molecule. What does it mean? For example, you have got the molecule like this, A, B, C. This is a molecule. Let's say this molecule is neutral. There is no charge here. There is no charge here. First of all, as per this rule, sum of oxidation states. Oxidation state of A, oxidation state of A. Oxidation state of A means the charge present on one atom of A. And we have got only one atom of A here. So multiplied by 1. Plus oxidation state of B. Oxidation state of B means charge present on one atom of B. And we have only one atom of B. So multiplied by 1. Plus oxidation state of C multiplied by 1. This will be equal to the net charge present in the molecule, that is 0. Okay. For example, you have got the molecule of this type, A2BC. And for example, there is negative charge here. There is negative charge here. Now remember what you have to do here. I'll say oxidation state of A multiplied by 2 plus oxidation state of B multiplied by 1 plus oxidation state of C multiplied by 1. This has to be equal to the net charge. Net charge is -1. So the sum of oxidation states of all the atoms present in the molecule is equal to what? Is equal to the net charge, right? Guys, one thing which I forgot to tell you. What is that? When you talk about your oxygen, the most common oxidation state, most common oxidation state shown by oxygen is -2. The most common oxidation state shown by oxygen is -2. Remember this thing as well. Okay. Now, let's try to use all these in some simple questions so that you understand it better. We have to calculate the oxidation state of these underlined atoms. Okay. Let the oxidation state of chromium is X, so it becomes 2X. The most common oxidation state of oxygen is -2. There are 7 oxygen atoms. Net charge here is -2. When you solve this, the value of X comes out to be +6. Okay. Similarly, let the oxidation state of sulfur is X, so this becomes 2X plus oxygen shows -2. There are 3 oxygen atoms. Net charge is -2. How much this will be? X value will come out to be +2. Okay. Nitrogen. Let the oxidation state of nitrogen is X. The most common oxidation state of hydrogen is +1. There are 4 hydrogen atoms. Net charge is +1. When you solve it, X value will come out to be -3. Let the oxidation state of chlorine is X. Oxygen will show -2. There are 4 oxygen atoms. Net charge is -1. When you solve it, the value comes out to be +7. Similarly, here it comes out to be +6. Right? If I take few more compounds, for example, you have got C3O2. You have got Br3O8. Right? You have got NH4NO2. And here I'm underlining 2 nitrogen atoms. Right? For example, you have got Fe0.930. Fe0.930. You have to calculate oxidation state of this iron as well. How do we do it? Okay. Carbon has got the oxidation state of X, so it's going to be 3X. Oxygen will show -2. There are 2 oxygen atoms. Net charge is 0, so X value will come out to be +4/3. Similarly, bromine, it's going to be 3X plus -2 into 8 is equal to 0. This value will come out to be +16/3. Now this NH4NO2, it's a special compound. It exists as NH4 positive dot NO2 negative. It exists as NH4 positive dot NO2 negative. So we'll be calculating the oxidation state of this nitrogen as well as this nitrogen. Now, in order to calculate oxidation state of this nitrogen, I'll consider this as a separate entity. In order to calculate oxidation state of this nitrogen, I'll consider this as a separate entity. Now, oxidation state of this nitrogen, let that be X. Hydrogen will show +1. There are 4 hydrogen atoms. Net charge here is +1. When you solve, the value of X will be -3. So this nitrogen is -3. Similarly, calculate this one as well. Let this be X. Oxygen will show -2. There are 2 oxygen atoms. Net charge here is -1. When you calculate, X value will be +3. So this nitrogen here is in +3 oxidation state, right? Similarly, talk about the oxidation state of this iron. Let the oxidation state of the iron be X. How many we have? 0.93. So multiplied with 0.93. Oxygen shows -2 oxygen state. Net charge is 0. When you solve it, the value of X will come out to be +200 divided by 93. It comes out to be +200 divided by 93 when you solve it, right? I believe this is like very much clear to every one of you. And my dear students, if you are clear with this particular point, then there are a few more things which I would want to tell you here. What is that? Remember, take a note of this statement. The maximum oxidation state of an element cannot be greater than cannot be greater than plus 7. Except, there are few exceptions, but you have to remember just one. Except osmium in OSO4, osmium tetroxide, where it shows plus 8. Where it shows plus 8. So normally you have to remember the maximum oxidation state of an element, it cannot be greater than plus 7. Okay? It cannot be greater than plus 7. But there is one exception, osmium in osmium tetroxide, where osmium shows plus 8 oxidation state. Why this particular statement is important? Why this particular statement is important? For example, I'm writing a compound CrO5 and I'm asking you to calculate the oxidation state of chromium. I'm asking you to calculate the oxidation state of chromium. What do you think? Can you calculate it with the help of same rules which I gave you? Let the oxidation state of chromium is X. Oxidation is going to show -2. There are 5 oxygen atoms. Net charge is 0. When you calculate it, X value comes out to be plus 10. But plus 10 is not possible because maximum oxidation state can be plus 7. Right? So this is wrong. Something is wrong here. For example, you have got CrO6. Let the oxidation state of chromium be X. Oxygen is going to show -2. There are 6 oxygen atoms. Net charge is 0. So the value of X will come out to be plus 12. But is plus 12 possible? Plus 12 is not possible. Plus 12 is not possible. Right? So what do we have to do? In order to know the actual oxidation state of chromium here, we should know their structures. We should know the structures of these compounds. In order to find the actual oxidation state of chromium, definitely we should know what exactly? We should know the structures of these compounds. Now, we are going to talk about the structures of some very, very, very important compounds. We are going to know about the structures of very, very, very important compounds. Your first compound is going to be, my dear students, first of all, let me tell you, there is no trick for these structures. Whatever structures I'm giving you, there is no trick. You just have to try them 2-3 times and you'll be done. You'll be sorted. Okay? There is no trick for them. First of all, CrO5. CrO5 has got butterfly-like structure. It has got butterfly-like structure. And remember, it is deep blue in color. How it looks like? This is Cr, double bond. First of all, this butterfly-like, this is logically incorrect. But your book writes it, so you can remember it too. Otherwise, it's logically incorrect. Cr double bond O, this is oxygen, oxygen single bond. And similarly, this is oxygen, oxygen single bond. This is the structure of your CrO5. Now guys, let me show you how to check the oxidation state with the help of structure. Let me tell you how to calculate the oxidation state of chromium with the help of structure. Understand. This is a single bond between chromium and oxygen. Which one is more electronegative? Oxygen. So this bond pair will be towards oxygen. Oxygen -1, chromium +1. Due to this particular bond, again oxygen -1, chromium +1. Due to this particular bond, oxygen -1, chromium +1. Due to this particular bond, oxygen -1, chromium +1. Due to this double bond, oxygen -2, chromium +2. Tell me the total charge present on chromium here. +2, +3, +4, +5, +6. So chromium is in +6 oxidation state. It is not in +10 oxidation state, right? And guys, at the same time, do you see the single bonded linkage between 2 oxygen atoms? Yes. Single bonded linkage between 2 oxygen atoms? Yes. This single bonded linkage is what you call as peroxide linkage. This is what you call as your peroxide linkage, right? Now, they can ask you one more question. How many peroxide linkages are there? Number of peroxide linkages in CrO5. 1, 1, 1, 2. They can ask you how many oxygen atoms are there with -1 oxidation state. How many oxygen atoms are there with -1 oxidation state? Remember, number of peroxide linkages multiplied by 2. Number of peroxide linkages multiplied by 2. That gives you the number of oxygen atoms with -1 oxidation state. So there will be 4 oxygen atoms with -1 oxidation state. So this is your CrO5, which you have to remember. Now, second is your CrO6. This was the question asked in your, I think, NEET 2021 or 2022. What is the oxidation state of chromium in CrO6, right? So again, you should know its structure, then only you can draw it. You can write it. So structure is like this. Single bond, again. Single bond, again. Between 2 oxygen atoms, single bond. Now, my dear students, look at this particular bond. It's between chromium and oxygen. Which one is more electronegative? Oxygen. So oxygen will have -1 due to this bond and chromium +1. Due to this particular bond, again oxygen -1, chromium +1. Due to this particular bond, oxygen -1, chromium +1. Due to this particular bond, oxygen -1, chromium +1. Due to this particular bond, oxygen -1, chromium +1. Due to this particular bond, again -1, again +1. So what is the total charge present on chromium here? It is again going to be +6 only. If I ask you how many peroxide linkages do you see? There are 3 peroxide linkages. This, and this. How many oxygen atoms will be there with -1 oxidation state? 3 2s are 6. Okay? I believe this is clear. The third structure which we have, my dear students, from which the questions have been frequently asked, that is your Carrot's acid. And Carrot's acid is basically your H2SO5. Carrot's acid, H2SO5. How this Carrot's acid exactly looks like? This is sulfur, double bond O, oxygen attached with hydrogen, again oxygen, oxygen, hydrogen. Now when you calculate the oxidation state with the help of structure, which I showed you already how to check, its oxidation state is +6. There is 1 peroxide linkage. If there is 1 peroxide linkage, that means there will be 2 oxygen atoms with -1 oxidation state, right? Sir, how can we know the structure? Again, I'm telling you, you have to remember all these structures by practicing. There's no trick to them. Similarly, if I talk about the fourth structure, that is your S4O6 dinegative, or you can write it as Na2S4O6. Na2S4O6. You can write it like that as well. So how it looks like? Structure is simple. S, 4 sulfur atoms, double bonded O. This is again double bond, oxygen with negative charge and oxygen with negative charge. Now, if you want to calculate the oxidation states of all these sulfur atoms, let's get to know the oxidation states of all these sulfur atoms. Let me show it one by one. There is a double bond between sulfur and oxygen. Since oxygen is more electronegative, right? So due to this double bond, sulfur will have +2. Due to this double bond, again sulfur will have +2. Due to this single bond, sulfur will have +1. Due to this single bond, sulfur will have +1. So in total, it's coming out to be +5. This sulfur, its oxidation state will be 0. This will be 0. This will be also +5. Now there are 4 sulfur atoms. So if I ask you what is the average oxidation state of sulfur here, you will say the first sulfur has got +5, second sulfur 0, third sulfur 0, fourth sulfur +5, divided by total sulfur atoms 4, the value comes out to be +2.5. This is the average oxidation state of sulfur in case of your tetrathionate ion, S4O6 dinegative. Okay. Now, my dear students, similarly, there is one more structure which I have to remember, that is for oleum. Oleum is basically H2S2O7. How it exactly looks like? SOS, double bond O, oxygen attached with hydrogen and oxygen attached with hydrogen. Now, my dear students, this is S double bond O. Oxygen is more electronegative. So this will have +2. This will again have +2. Due to this bond, it's going to be +1. Due to this bond, +1. So this sulfur is basically in +6 oxidation state. Similarly, this sulfur will be also in +6. So if you ask me what is the average oxidation state of sulfur, +6 divided by 2 will be +6 only. Okay? It will be +6 only. Okay? Similarly, so 5 structures I made till now. Let's have a look on the 6th structure. 6th structure is your Marshall's acid. It is your Marshall's acid. H2S2O8. H2S2O8. How it looks like? This is going to be its structure. This is going to be its structure. Now, my dear students, let me tell you one thing. When you calculate the oxidation state of this sulfur, again it's going to be +6. This will be also +6. When you check one by one with the help of bonds. Okay? Again, if I ask you what is the average oxidation state of sulfur here, it's again going to be +6 only. Marshall's acid. Similarly, you have got K3CrO8. How exactly it looks like? This is Cr. Oxygen, oxygen, single bond. This is oxygen, 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 and potassium, potassium, potassium. When you calculate the oxidation state with the help of structure, it will come out to be +5, right? Because these are 5 single bonds with 5 oxygen atoms. Okay. Now, if I ask you how many peroxide linkages do you see? This is the first peroxide, second one, third one, fourth one. So, number of peroxide linkages here will be 4. And How many oxygen atoms will be there in -1? There will be 8 oxygen atoms here with -1 oxidation state. I believe again this is clear. Okay, this was your K3CrO8. Now similarly guys, there are a few more, like you have got C3O2, carbon suboxide. C, double bond C, double bond C, double bond O, and double bond O. Now if you look carefully, there is a double bond between carbon and oxygen. So oxygen will have -2, carbon will have +2. Due to this double bond, nothing will happen because on both the sides carbon. This will have -2, this will have +2. So if I talk about the average oxidations of carbon here, the first one shows +2, second one shows 0, third one shows +2. Total there are 3 carbon atoms, so it's going to be +4/3. +4/3, right? Similarly, if I talk about the ninth structure, ninth structure is your Br3O8. Br3O8. How it looks like? Br, single bond Br, single bond Br, double bond O, double bond O, double bond O, double bond, double bond, double bond. Everywhere it's double bond. So what I can say is, oxidation state of this bromine. Due to this double bond, it will show +2. Due to this double bond, +2. Due to this double bond, again +2. Nothing will happen to this. So it's going to be +6. Similarly, this is going to be +4. And similarly, this is going to be +6. So average oxidation state of bromine, if I ask you, the first bromine will show +6, second +4, third +6, total 3 bromine atoms, 6, 6, 12, 4, 16. So +16/3 is basically the average oxidation state of bromine in your Br3O8. Okay? I hope this is clear. Now similarly, there are a few more compounds which I would want you guys to remember. What is that? One is going to be your H3PO2. One is going to be your H3PO3. These are important as well. H3PO3. One is going to be your H3PO4. And one is going to be your H3PO5. H3PO5. How do you make their structures? P double bond O, oxygen with hydrogen. This is, what is it? H3PO2. So this is hydrogen directly attached, this hydrogen directly attached. So this is H3PO2. And remember, in case of H3PO2, the oxidation state, when you calculate it, it will come out to be +1. H3PO3. This is how your H3PO3 looks like. And here, the oxidation state of phosphorus, when you calculate, it will come out to be +3. H3PO4. In case of H3PO4, the oxidation state of phosphorus will be +5. And in case of H3PO5, guys, these structures are important. You'll understand their significance in some time, right? Its oxidation state is +5. So these are some of the structures which I want you guys to remember. Because from these structures, anything can be asked. Achha, by the way, you must be thinking, how come oxidation state of this phosphorus is +1? Chalo, let me show you one in detail. If you look carefully, there is a double bond between phosphorus and oxygen. Oxygen is more electronegative, so phosphorus will show +2. Due to this single bond, phosphorus will show +1. Among phosphorus and hydrogen, phosphorus is more electronegative, so -1. Again -1. So when you check it out, it comes out to be +1 over here. Okay? I hope this is clear to everyone. Similarly, there is one more compound, bleaching powder. Remember that? In case of your bleaching powder, this is one more compound. In case of your bleaching powder, the formula of bleaching powder, you must be knowing CaOCl2. Remember, in case of bleaching powder, one chlorine is in +1 oxidation state, one more chlorine is in -1 oxidation state. There are 2 chlorine atoms. One chlorine will be in +1, one more chlorine will be in -1. So if I talk about the average oxidation state of chlorine here, average oxidation state of chlorine in bleaching powder will be 0. Perfect? Perfectly done, guys. So these were the structures and some important things which you should know about the oxidation state. Now, my dear students, if you got to know about the oxidation state, if you got to know how to calculate the oxidation state, then there is something called as oxidation and reduction, right? How many ways are there to define oxidation? Oxidation involves loss of electrons. Oxidation involves removal of hydrogen, right? Addition of oxygen is called as oxidation. Addition of more electronegative element is also called as oxidation. These are few important. I won't say important, okay? These are few definitions which you have to remember about oxidation. Okay. Similarly, reduction, just opposite of oxidation. Gain of electrons. Gain of electrons is called as oxidation. Addition of hydrogen is called as oxidation. Removal of oxygen is called as reduction. Similarly, removal of more electronegative element is called as reduction. Gain of electrons is called as reduction. Addition of hydrogen called as reduction. Removal of oxygen is called as reduction. Removal of more electronegative element is called as reduction. Right? These are some of the ways by means of which you can define oxidation and reduction. What is important in all of these? Try to understand. For example, let me write the reaction here. If I write the reaction, Na gives Na positive plus 1 electron. In this reaction, is the loss of electron happening? Yes, the loss of electron is happening. Loss of electron is called as oxidation. So sodium is undergoing oxidation here. Sodium is undergoing oxidation here. Now, similarly, removal of hydrogen. Let's say I'm writing the reaction like this. H2O gives H2 plus O2. What is happening? Removal of hydrogen is happening. Addition of oxygen. C plus O2 gives CO2. Addition of oxygen is happening. Right? Addition of more electronegative element. Or make it like this. Ca plus O2. You'll get CaO. Addition of more electronegative element. For example, C plus Cl2 gives CCl4. If I make it 2 times. Right? So all these are basically examples of what? Oxidation reactions. Now, what is common in everyone? That is important. What is common in everyone? See, if you talk about the oxidation state of this sodium, it's 0 here, and it is plus 1. So if I ask you, is the oxidation state of sodium increasing or decreasing? 0 to plus 1, increasing. Oxidation state of sodium is increasing. Water, oxygen minus 2, oxygen 0. Minus 2 to 0. Again, oxidation state is increasing. 0 to plus 2. Again, oxidation state is increasing. Right? 0 to plus 4. Again, oxidation state is increasing. Do you see something common in all these? What is the common thing? What is the common thing? I'm asking you. Is oxidation state increasing or decreasing? Increasing. Remember from now onwards, in case of oxidation state of an element increases. So in short, I just want you guys to remember one thing. Increase in the oxidation state of an element is called as oxidation. Increase in the oxidation state of an element is called as oxidation. Similarly, let me tell you, decrease in the oxidation state of an element is called as a reduction. Increase in the oxidation state of an element. Whenever you see oxidation state of an element increasing, remember, increase in the oxidation state of an element is called as oxidation. And decrease in the oxidation state of an element is called as a reduction. Just these 2 things I want you to remember, that's all. Okay? Just these 2 things. Now, if you understood these 2 things, then there are a few more things which I want to tell you. What are those? There is something called as oxidizing agent and reducing agent. Something called as oxidizing agent and reducing agent. How do you identify in a reaction which one is oxidizing agent and which one is reducing agent? See, there's a way to do that too. How exactly? Magnesium, oxidation state 0. Oxygen, oxidation state 0. Right? This magnesium, oxidation state plus 2. This magnesium, oxidation state minus 2. And you know how to check it. Is the oxidation state of magnesium increasing or decreasing? 0 to plus 2, increase. Increase in the oxidation state is what you call as oxidation. So I would say magnesium is undergoing oxidation. And remember, the one that undergoes oxidation is what you call as the reducing agent. Similarly, 0 to minus 2, decrease in the oxidation state. Decrease in the oxidation state is what you call as a reduction. And the one that undergoes a reduction is going to be your oxidizing agent. The one that undergoes reduction will be the oxidizing agent. The one that undergoes oxidation will be your reducing agent. Okay, let me take one more example. With that, things will be more clear to you. For example, this is the reaction given, and I have to identify which one is oxidizing agent and which one is a reducing agent. My first thing is to calculate the oxidation state of every element. This iron, when you calculate x minus 2 is equal to 0, so plus 2. X minus 8 is equal to minus 1, so plus 7. This HCl, it is giving me the idea about the medium, that the reaction is taking place in acidic medium, so nothing to do with that. This iron, 2x minus 2 into 3 is equal to 0, so plus 3. Right? This manganese, x, this is minus 1 into 2 is equal to 0, so plus 2. So check it out. Plus 2 to plus 3, increase. Increase in the oxidation state is what you call as oxidation. So I would say this FeO is undergoing oxidation. If it undergoes oxidation, That means it has to be the reducing agent. Simple. Similarly, +7 to +2, decrease in the oxidation state. Decrease in the oxidation state is what we call as reduction. So I would say MnO4 negative is undergoing reduction. If it undergoes reduction, so it is the oxidizing agent. This is how you are going to check whether the substance is going to be your oxidizing agent or the reducing agent. Am I clear with this? Say yes or no in the chats. Did you understand how to check whether the substance is your oxidizing agent or the reducing agent? Yes or no? Now, this was something which was pretty much simple. The reaction was given, and you are just supposed to check whether the substance is oxidizing agent or reducing agent. Now, guys, if I ask you one thing, for example, I'm not giving you the reaction. For example, I'm not giving you the reaction. I'm just giving you the substance like this, HCl, and I'm asking you, is this oxidizing agent or reducing agent, or both? I'm giving the substance H3PO4. H3PO4. I did not give you any reaction here. I'm just giving the substance H3PO4, and I'm asking you whether this is oxidizing agent or reducing agent. How do we check this? There is a logic for that. How do we check this? Remember, the first thing always which you are going to do is to calculate the oxidation state of the central atom. Your first step always will be to calculate the oxidation state of central atom. For example, I'm taking the case of, let's say, H3PO4. I'm taking the case of H3PO4. Now, I want to know whether this is oxidizing agent or reducing agent. So first thing, I'll be calculating the oxidation state of central atom. And few minutes back, I told you that's +5. So my first step is to calculate the oxidation state of central atom. Right? Now, my dear students, remember, if the central atom is already in lowest possible oxidation state, if the central atom is already in lowest possible oxidation state, if the central atom is already in lowest possible oxidation state, that means it cannot further decrease its oxidation state. If the central atom is already in lowest oxidation state, so that means it cannot decrease its oxidation state more. If it cannot decrease, no doubt it cannot decrease, but it can increase. When it increases, it will undergo oxidation. When it undergoes oxidation, it is going to behave like reducing agent. Remember, the substance at that time is a reducing agent. Right? Similarly, if the central atom is already in highest possible oxidation state, if the central atom is already in highest possible oxidation state, so that means it cannot further increase. Central atom is already in highest oxidation state. It cannot further increase. It cannot further increase, no doubt. But it can decrease. When it decreases, it will undergo reduction. And when it undergoes reduction, it's going to be the oxidizing agent. Okay? Perfect. And my dear students, one more thing. If the central atom is in intermediate oxidation state, that means if the central atom is neither in lowest oxidation state nor in highest, if the central atom is neither in lowest oxidation state nor in highest, that means its oxidation state is in the middle, neither highest nor lowest. So it can increase also, decrease also. That means the compound is going to behave like the reducing agent as well as oxidizing agent. Okay? Perfect. Right? Now, you can take certain examples and let's check few things. For example, K2Cr2O7. Is it the oxidizing agent or reducing agent? Calculate the oxidation state of central atom. It will be +6. The maximum oxidation state of chromium is already +6. So chromium is already in maximum oxidation state, highest oxidation state. If chromium is already in highest, so it has to behave like the oxidizing agent. Right? For example, KMnO4. Calculate the oxidation state of central atom. It will be +7. +7 is the highest oxidation state of manganese. We know it. +7 is the highest oxidation state of manganese. So manganese is already in highest oxidation state. Right? So it's going to be the oxidizing agent. Perfect. For example, you have got HCl. You have got HCl. Chlorine here is in -1 oxidation state. Already we know chlorine is a p block element. What is the range of oxidation state it shows? I've told you already. -1 to +7, right? -1 to +7. So this is the lowest possible oxidation state of chlorine. This is the highest possible oxidation state of chlorine, right? And chlorine here is in -1. -1 means chlorine is already in lowest. Chlorine is already in lowest. If the central atom is in lowest, it's going to be the reducing agent. So it is going to be the reducing agent here, right? For example, you have got H2O2. H2O2, hydrogen peroxide. In hydrogen peroxide, oxygen state of oxygen is -1. And what is the range of oxidation states which oxygen shows? Oxygen belongs to group 16, P block. And P block means group number -18 to group number -10. So 16 minus 18 is -2, 16 minus 10 is +6. So -2 to +6. -2 to +6. Now look here carefully. Look here carefully. Oxygen is in -1. -1 is neither lowest nor its highest. So -1 is its intermediate. If it is its intermediate, in between, so it's going to behave both oxidizing agent as well as a reducing agent. I hope these sort of questions you can easily solve from now onwards. Yes? And my dear students, one more thing which you have to remember. Whenever a question is asked based on strength of oxidizing agent, if they ask you a question, if they give you 3-4 oxidizing agents and you have to arrange them on the basis of their strength of oxidizing agent. Remember, strength of oxidizing agent is directly proportional to oxidation state of central atom. Remember, strength of oxidizing agent is directly proportional to oxidation state of central atom. More the oxidation state of central atom, stronger is going to be the oxidizing agent. Similarly, if I talk about the strength of reducing agent, it is directly proportional to it is inversely proportional to the oxidation state of central atom. Remember this particular point as well. Sometimes they can ask you the questions about these as well. Okay? I hope you got the idea about oxidizing agents, reducing agents, oxidation, reduction, and similarly their rules, etc., etc. If every single thing is clear, let me know once in the chats. Let me know once in the chats. Quickly. Quickly, guys. Perfect. Now let's move on to one more topic. What is that? That is your equivalent mass. That is your equivalent mass. What is equivalent mass exactly all about? So first of all, if I write its definition, equivalent mass is basically the mass of the substance that can combine or displace. Number one, either 1 gram of hydrogen, or number 2, 8 grams of oxygen. Number 3, 35.5 grams of chlorine. Number 4, 108 grams of silver. Number 5, 80 grams of bromine. Equivalent mass of the substance is nothing but it is that mass of the substance. It is that mass of the substance which can combine either with 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine and so on. Let's try to understand its meaning. Okay, let's try to understand its meaning. See, guys, for example, I'm writing a reaction here, N2 plus 3 times H2. it gives 2 times NH3. This, for example, your reaction. Okay, this is your reaction. I'm asking you, calculate the equivalent mass of nitrogen here. Calculate the equivalent mass of nitrogen. The first thing, my dear students, the first thing that should be in your mind, nitrogen is combining with hydrogen. Nitrogen is combining with hydrogen. I want to calculate equivalent mass of nitrogen. No doubt, I want to calculate equivalent mass of nitrogen. And I got to know nitrogen is combining with hydrogen. So I am going to calculate the equivalent mass of nitrogen with respect to hydrogen. I'm going to calculate equivalent mass of nitrogen with respect to what? With respect to hydrogen. How exactly? See, what is the molar mass of H2? Molar mass of H2 is 2 grams. That means mass of 1 mole of H2 is 2 grams. If the mass of 1 mole of H2 is 2 grams, I would say mass of 3 moles of H2 would be 6 grams. So I'm writing 6 grams of hydrogen. Combines with. Molar mass of N2 will be 28 grams. 28 grams of nitrogen. Right? Stoichiometry told me that 6 grams of hydrogen combines with, sir, I think it's 16 grams of oxygen. No, it's 8 grams of oxygen. See, stoichiometry told us that 6 grams of hydrogen combines with 28 grams of nitrogen. Now think about it logically. If 6 grams of hydrogen combines with 28 grams of nitrogen, that means 1 gram of hydrogen. 1 gram of hydrogen combines with 28 by 6. The value comes out to be 14 by 3 grams of what? Grams of nitrogen. Right? So my dear students, think logically again. What is this particular term? What is this particular term? It is the mass. Mass of what? Mass of nitrogen. It is the mass of nitrogen that has combined with 1 gram of hydrogen. And that mass of substance which combines with 1 gram of hydrogen, what do you call that as? Equivalent mass. So this is technically the equivalent mass of nitrogen here. Did you understand? Did you understand? I'll take one more example. With that, things will be more clear. For example, I'm taking the reaction like this. Mg plus O2 gives what? Gives MgO. If I balance the reaction, this should be 2 times, this should be 2 times. Now, I want to know equivalent mass of magnesium. I want to know equivalent mass of magnesium, right? I want to know equivalent mass of magnesium. Now, my dear students, try to understand. Since magnesium is combining with oxygen, so basically, in order to calculate the equivalent mass of magnesium, I should check what mass of magnesium has combined with 8 grams of oxygen. I have to check what mass of magnesium has combined with 8 grams of oxygen. And how do I check it? Understand? What is the molar mass of O2? 32 grams. So I'll write 32 grams of oxygen here. Combines with, what is the mass of 2 moles of magnesium? 24 into 2 is 48. So from this balanced chemical equation, I got to know 32 grams of oxygen combines with 48 grams of magnesium. Therefore, 1 gram of oxygen combines with 48 divided by 32 grams of magnesium. So as per definition, 8 grams of oxygen would have combined with 48 divided by 32 multiplied by 8. Value comes out to be 12 grams of magnesium. So what is this particular term if you ask me? It is basically the mass of magnesium. It is basically the mass of magnesium that has combined with 8 grams of oxygen. And that mass of magnesium which has combined with 8 grams of oxygen, what do you call this as? You call this as equivalent mass of magnesium. You call this as the equivalent mass of the magnesium. Understood? Is it clear? Is it clear, guys? Tell me once. Perfect. Okay, we'll take a small break here because I know a lot of students are fasting right now. They want to pray, right? So let's take a small break of 15 minutes and get back. Okay, so I'll be resuming the class at 5:15 or 5:10. Let's resume the class at 5:10. So be back on time. Huh? Be back on time. All right? Be back on time. I'll be resuming the class at 5:10 exact. I'm giving you 15 minutes of time. You can quickly come back. And some people who want to have some tea or something, you can have it. Okay? But be back on time quickly. Is everyone back or not? Is everyone back or not? So guys, can you tell me whatever things we discussed till now, is every single thing clear? Is every single thing clear? Yes. All right, people. So we have discussed what equivalent mass is all about, right? I've told you how to calculate equivalent mass with the help of the definition. How to calculate equivalent mass with the help of definition. Okay? Now, my dear students, there is one formula. There is one formula with the help of which we can calculate equivalent mass of different substances directly. And what is that formula? That formula is equivalent mass is equal to molar mass of the substance divided by n factor, or you call it as the valency factor. Equivalent mass of the substance is nothing. It is equal to molar mass of the substance divided by n factor of the substance. You can call it as the valency factor of the substance as well. So basically, in order to calculate equivalent mass of any substance, we just need to know molar mass of the substance, and we have to divide that with the n factor of the substance. Now the point is, how do we check the n factor of different substances? See, molar mass we already know for all the substances, right? We have to know how to calculate the n factors, right? So the first n factor calculation which we are going to do here, that is going to be the n factor of an element. N factor of an element. And let me tell you, n factor of an element is nothing but, it is the valency of an element. It is the valency of an element. N factor of an element is nothing but, it is the valency of an element. For example, take certain elements. Let's say I'm talking about nitrogen. It's an element. Oxygen, an element. Sodium, one more element. Magnesium, one more element. If I ask you what is the valency of nitrogen, you should know it. Valency of nitrogen is 3. Valency of oxygen is 2. Valency of sodium is 1. Valency of magnesium is 2. And whatever is going to be the valency of an element, that's what I'll be calling as n factor of an element. So these are the respective n factors of these elements, right? If these are the n factors of the elements, you can easily calculate equivalent masses. Equivalent mass is nothing but molar mass divided by n factor. For example, equivalent mass of nitrogen will be equal to molar mass of nitrogen divided by n factor, right? For example, equivalent mass of magnesium will be equal to molar mass of magnesium divided by n factor, right? Perfect. So the point is, n factor of an element is nothing but the valency of an element. As simple as that. This was the first case in case of n factor calculation. The second case, my dear students, n factor of an ion. N factor of an ion. N factor of an ion is basically what? It is the magnitude of charge present on an ion. N factor of an ion is nothing but the magnitude of charge present on an ion. For example, I'm taking certain ions here. Na positive, Cl negative. For example, SO4 di negative, right? For example, PO4 tri negative. These are some ions which I've taken over here. What is the charge on this ion? +1. Just take the magnitude. That's 1. Charge on chlorine. -1 here. Just take the magnitude. That's 1. Here, the magnitude. That's 2. Here, the magnitude. That's 3. Okay? And magnitude of charge present on ion is what you call as n factor. So these are the respective n factors of the ions. And if you got the n factors of these ions, you can calculate their equivalent masses. Molar mass divided by n factor. For example, this sodium, its molar mass is 23. 23 divided by 1. right? 35.5 divided by 1. SO4, 96 divided by 2. PO4, 95 divided by 3. As simple as that. As simple as that. I hope this is clear to everyone. This was how to calculate the n factor of the ions. The third one is n factor of a salt. N factor of a salt. N factor of a salt is nothing but LCM of charge on cation, comma, the charge on anion. Charge on cation, comma, the charge on anion. Okay, or you can say total cationic charge or total anionic charge. See guys, for example, I'm taking different salts here. Let's say you've got NaCl. Let's say you've got BaCl2. Let's say you've got AlCl3. Let's say you've got Al2SO4 whole thrice. Okay. Now, my dear students. Have a look. First of all, how do we get the charge on the cation and anion? You just have to crisscross the things. This 1 over here, this will go here as +1. This 1 here will go -1. This 2 will here come as +2. This 1 will here come as -1. This 3 will here come as +3. This 1 will come as -1. This 3 will come as +3. This 2 will come as -2. Right? So you got the charges on cation and anion. Now, what is the LCM of 1 and 1? LCM of 1 and 1 is 1. LCM of 2 and 1 is 2. LCM of 3 and 1 is 3. LCM of 3 and 2 is 6. And my dear students, LCM of charge on cation and anion, that gives you the n factor of the salt. And if you got the n factor of salt, you can easily calculate the equivalent mass. That means molar mass divided by n factor, molar mass divided by n factor, molar mass divided by n factor. As simple as that. Okay. Now, case number 4. Case number 4 is going to be n factor of an acid. N factor of an acid. N factor of an acid is nothing but it is the basicity of the acid. It is the basicity of the acid. And how do we define basicity? We can define basicity in few ways over here. The first way, number of H positives an acid donates. Number of H positives an acid donates. Number of OH negatives an acid accepts. An acid accepts. Similarly, you can say number of lone pairs an acid accepts. Number of H positives an acid donates. Number of OH negatives an acid accepts, or the number of lone pairs the acid accepts. For example, my dear students, take the case of HCl. A very common acid this is. Take the case of H2SO4. Take the case of HNO3. Take the case of H3PO4. These are some acids which I've taken. Tell me one thing. When you introduce this HCl in water, how many H positives it will give? 1 H positive. How many H positives this will give? 2 H positives. This will give 1 H positive. This will give 3 H positives. And the number of H positives an acid donates. The number of H positives an acid donates. That defines its n factor. So n factor of HCl is 1. This is 2. This is 1. This is 3. And if you got the n factor of these acids, you can calculate their equivalent masses. Molar mass divided by n factor. Right? Now, my dear students, if I talk about H3PO2, this is one of the acids. H3PO3, H3PO4, and H3PO5. Tell me, how many H positives it's going to give? 3. This will give 3 H positives. This should give 3 H positives. This should give 3 H positives. So their n factor should be 3. The n factor of all of them should be 3. But that's not the case. Why is that? Have a look. I'm writing a statement. Statement is, an acid donates. An acid donates only that H positive. An acid donates only that H positive, which is attached to more electronegative element. more electronegative element like fluorine, oxygen, nitrogen. If you look at the structure of this H3PO2, I've already given you the structure of H3PO2. Its structure used to be like this. Talk about the structure of H3PO3. Structure of H3PO4. H3PO4, H3PO5. Okay. My dear students, look carefully. How many hydrogen atoms do you see here? 3. But out of 3, how many hydrogens are attached to more electronegative element like oxygen? 1. How many hydrogens do you see here? 2 hydrogens attached to more electronegative element like oxygen. 3 hydrogen atoms. 3 hydrogen atoms. And as per this statement, an acid is going to donate only that hydrogen in the form of H positive, which is attached to more electronegative element, like fluorine, oxygen, nitrogen. So this acid is going to donate only 1 H positive. So its N factor is 1. This acid is going to donate 2 H positives. So its N factor is 2. Its N factor is 3. Even its N factor is 3. If you got the N factor of these acids, you can calculate their equivalent masses, their molar mass divided by respect to N factors, right? Now, my dear students, similarly, there is one more acid which you need to know. That's called as boric acid. Boric acid. Its formula is H3BO3. Or you can write it as like this also. BOH whole thrice. This is boric acid. Remember, it's a special case, this boric acid. Remember, it's a weak Lewis acid. It is a weak Lewis acid. And what happens exactly? When this boric acid is introduced in water, it gets converted into BOH4 negative. It gets converted into BOH4 negative. Okay. Now, my dear students, if I ask you, how many OH do you see here? 3. How many OH do you see here? 4. So when boric acid goes into water, has it accepted OH negative? Earlier it has 3 OH negatives. Now there are 4. So when it goes into water, I would say it has accepted 1 OH negative. And the number of OH negatives an acid accepts, that defines its basicity. And whatever is the basicity of the acid, that's what you call as its N factor. So I would say N factor of boric acid is equal to 1. N factor of boric acid is equal to 1. Remember this particular case as well, right? My dear students, now few more things. What is that? For example, I'm writing a reaction H2SO4 plus NaOH gives NaHSO4 plus water. Second, H2SO4 plus twice NaOH gives Na2SO4 plus 2 times water. These are the 2 reactions which I mentioned over here. Now, I want to calculate N factor of H2SO4 here as well as N factor of H2SO4 here in both the reactions. Let's see whether the N factor of H2SO4 in both the reactions is coming out to be same or different. See, one thing I'm going to tell you, you must be knowing when one H positive combines with one OH negative, it forms one water molecule, right? When 2 H positives combine with 2 OH negatives, they are going to form 2 water molecules. Now understand, how many water molecules are formed here? 1, right? If 1 water molecule is formed here, that means this acid would have given 1 H positive and this base would have given 1 OH negative, which would have combined and formed 1 water molecule. So I would say this acid has donated 1 H positive. This acid has donated 1 H positive. And my dear students, the number of H positives an acid donates, that defines its basicity. And whatever is the basicity, that's what you call as N factor. The N factor of H2SO4 is 1. Right? Now, my dear students, look here. How many water molecules are formed here? 2. That means this acid would have given 2 H positives. From here, 2 OH negatives would have come, right? And they would have formed 2 water molecules. So this acid here, it is donating 2 H positives. And the number of H positives acid donates, that defines its basicity. Basicity is what we call as N factor. So n factor of H2SO4 in both the reactions, is it same or different? It is different. N factor of H2SO4 here is 1, n factor of H2SO4 here is 2. If n factor of H2SO4 is coming out to be different, that means its equivalent mass will come out to be different in both the reactions. Its equivalent mass will be different in both the reactions, right? Which means that if we talk about the equivalent mass, is equivalent mass a fixed quantity or variable? It is a variable quantity. It is a variable quantity, unlike molar mass. Unlike molar mass. Molar mass of the substance is always fixed, whereas equivalent mass of the substance, it's variable. It's not fixed. It is not fixed. Okay? Equivalent mass of a substance can change on changing the type of the reaction. So when you change the type of the reaction here, equivalent mass of the same substance came out to be different. Okay? So this was your n factor of what? N factor of acids. Now similarly, we'll talk about the n factor of bases. That is our n factor 5. Fifth case. Talk about n factor of the base. Talk about n factor of the base. N factor of the base is what you call as acidity of the base. Acidity of the base. And acidity, I'm again going to define in 3 ways. Number 1. Number of OH negatives a base donates. Number of OH negatives a base donates. Number 2. Number of H positives a base accepts. Number 3. Number of lone pairs a base donates. A base donates. Okay? Now, my dear students, try to understand. For example, I'm taking a common base, that is NaOH. Let's say you have got calcium hydroxide. Let's say you have got AlOH whole thrice. Now tell me one thing. When you put it in water, how many OH negatives it will give? It will donate 1 OH negative. This will donate 2 OH negatives. This will donate 3 OH negatives. And the number of OH negatives a base donates, that defines its n factor. So n factor here is 1, here the n factor is 2, and here the n factor is 3. If you got their n factors, you can calculate their equivalent masses. Molar mass divided by n factor, molar mass divided by n factor, right? Now, for example, you have got a base as NH3. You have got the base as NH3. For example, you are introducing this in water, and it's giving you NH4 positive. I'm asking you, what is the n factor of this base here in this reaction? Since there is no OH, right? So what is going to donate? Nothing. Yeah? Now tell me one thing. Since it has 3 hydrogen atoms, when you introduce it in water, it's going to convert into NH4 positive. In NH4 positive, how many hydrogens do you see? 4. So that means when NH3 has been introduced in water, can I say it has accepted 1 H positive? It has accepted 1 H positive. And the number of H positives a base accepts, that defines its n factor. So its n factor here is 1. Its n factor here is 1. I believe this is clear. Yes? I believe this is clear. Okay? I believe this is clear. Right, people? Am I clear with this? Perfect. Now, guys, one more thing. For example, I'm giving you a question like this. The question is zinc hydroxide plus HCl gives ZnOHCl plus water. This is one reaction. Second one, zinc hydroxide plus 2 times HCl gives ZnCl2 plus 2 times water. Plus 2 times water. Now, first of all, how many water molecules are formed here? 1. How many water molecules do you see here? 2, right? Now, you tell me. If 1 water molecule is getting formed, that means this acid would have given 1 H positive and this base would have given 1 OH negative. So, this base is donating 1 OH negative. That means its N factor has to be 1. Since 2 water molecules are formed here, so this base would have given 2 OH negatives, right? And the number of OH negatives a base donates, that defines its N factor. So, if you got the N factors, you can calculate their equivalent masses. Molar mass divided by N factor, right? Perfect. Perfect, people. I believe this is clear. So this was about the N factor of bases. And if you got the N factor of base, you can calculate the equivalent mass of the base. That will be molar mass divided by the respective N factor. Okay. Now, my dear students, the sixth case, that is N factor of an oxidizing agent or reducing agent. N factor of an oxidizing agent or reducing agent. Let me tell you, N factor of an oxidizing or reducing agent is nothing but, it is defined as number of moles of electrons lost, gained, or exchanged. Lost, gained, or exchanged by 1 mole of substance. Number of moles of electrons lost, gained, or exchanged by 1 mole of substance. So now try to understand what exactly I'm going to say. For example, you have got the reaction like this. A plus B, let's say it gives A positive plus B negative. This is your reaction. What is the oxidation state of A here? 0. Oxidation state of B here? 0. Oxidation state of this A? +1. Oxidation state of this B? -1. Now 0 to +1. Increase. Increase means oxidation. Oxidation means reducing agent. 0 to -1. Decrease. Decrease is what we call as reduction. Reduction means oxidizing agent. So you identified your oxidizing agent and reducing agent. Now, my dear students, since you identified your oxidizing agent, and reducing agent, now how do we calculate the N factor of the oxidizing agent and reducing agent? See, for example, N factor of A. How do I calculate it? Tell me, what is the initial oxidation state of A? 0. What is the final oxidation state? +1. Initial oxidation state of A is 0. Final oxidation state of A is +1. So it's going to be final oxidation state minus initial oxidation state. This is the change in the oxidation state. Final oxidation state minus initial oxidation state. Take the mod, multiplied by. I want to know the N factor of this A. Check its subscript. It's 1. So multiply this with 1. So the overall value comes out to be 1 only. So N factor of A here is 1. Okay. Now, my dear students, for example, N factor of B. N factor of B. 0 to -1. 0 to -1. This is initial. This is final. So, N factor of B, I want to calculate. This is initial oxidation state of B. This is final. So, just do one thing. Final oxidation state of B minus initial oxidation state of B. Come mod. Multiplied by. What is the subscript of B? That's 1. So, multiply it with 1. So, the value comes out to be 1. This is the N factor of B. Perfect. This is the N factor of B. For example, if I take the case like this, let's say I've got the reaction like this, A2 plus B2. It gives, for example, 2 times A positive plus 2 times B negative. Okay. Oxidation state, here is 0, here it is 0, here it is +1, here it is -1. Now 0 to +1, increase. Increase means oxidation. Oxidation means reducing agent. 0 to -1, decrease. Decrease means reduction. Reduction means oxidizing agent. So I identified my oxidizing agent and reducing agent. Now, my dear students, tell me one thing. How do I calculate N factor of A2 here? How do I calculate N factor of A2? See, initial oxidation state, final. So write final minus initial ka mod multiplied by. What is the subscript here? 2. So multiplied with 2, the value comes out to be 2. This is N factor. Similarly, N factor of B2 will be equal to change 0 to -1. Final minus initial. Final minus initial ka mod multiplied by. its subscript is 2. The value comes out be 2. The value comes out be 2. Perfect. Similarly, guys, if I want you to calculate n factor of A positive here, if I want you to calculate n factor of A positive here, this, so what you have to do, you have to go in the reverse manner. You have to go in the reverse manner. Now, this will be initial and this will be final. So, write final minus initial. Final minus initial ka mod multiplied by. I want to calculate its n factor. Check its subscript, that's 1. So, multiplied with 1. So, its n factor will be 1. Do you understand? Do you understand, people? Okay. I believe this is clear to everyone. I believe this is clear to everyone. I hope you got to know how to calculate the n factors of oxidizing and reducing agents. Therefore, you can calculate the equivalent masses of these oxidizing and reducing agents. Right? Perfect. Now, my dear students, there is one very important oxidizing agent. That's your KMnO4. Remember this one. It's a very strong oxidizing agent. And this KMnO4, it shows different reactions in different mediums. It shows different reactions in different mediums. In acidic medium, it gets converted into Mn di positive. KMnO4, when it participates in acidic medium, it gets converted into Mn di positive. In neutral or slightly alkaline medium, it gets converted into MnO2. And let me tell you, in strongly alkaline medium, it gets converted into MnO4 dinegative. MnO4 dinegative. Now, first of all, if I ask you what is the oxidation state of manganese over here, it's going to be +7. Oxidation state of manganese here, +2. Oxidation state of manganese here, when you calculate, +4. Oxidation state of manganese here, +6. Now, +7 to +2, what is the change? Final minus initial ka mod, the value comes out to be 5. 5 is the change for one manganese, and we have got only one manganese, so its n factor here is 5. So KMnO4's n factor in acidic medium is 5. Now, +7 to +4, +7 to +4, what is the change? 3. So its n factor here is 3. So n factor of KMnO4 in neutral medium is 3. Similarly, +7 to +6, change is 1. So n factor of this is 1. N factor of KMnO4 in strongly alkaline medium is 1. Now, if you got the n factor of KMnO4 in all the mediums, you can calculate its equivalent mass in all the mediums. Molar mass divided by n factor. Molar mass divided by n factor. Right? Now, similarly, for example, you have got K2Cr2O7. This is again a strong oxidizing agent. Okay? Let me tell you, in acidic medium, it gets converted into Cr tripositive. See, oxidation state +6, +6 to +3, change. Final minus initial, 3. 3 is the change for 1, so 3 2s are 6. Its n factor here is going to be 6. So remember it directly, n factor of K2Cr2O7 in acidic medium is nothing but 6. Okay? Now, my dear students, like this, you can calculate n factor of different substances. For example, there are few questions I'm giving you. Let's say I'm giving you a question like this. I2 gives IO3 negative. I'm asking you to calculate the n factor of I2 here. For example, VO, vanadium oxide, gives V2O5. I'm asking you to calculate the n factor of this VO. For example, C2O4 dinegative, it gives CO2. I'm asking you to calculate its n factor. Similarly, for example, we have got, what else can I take? IO3 negative, it gives, for example, IO4 negative. I want to know the n factor of this particular species. How do I get their n factors? Again, pretty much simple. The same thing which I discussed with you till now. Oxidation state of iodine here is 0. Here iodine is in +5 oxidation state. 0 to +5. change, final minus initial, the value is 5. 5 is the change for 1, so 5 2s are 10. So its n factor here is 10. The vanadium here is in +2 oxidation state. Here the same vanadium is in +5 oxidation state. +2 to +5. +2 to +5. Change, it is 3. 3 is the change for 1 vanadium. I have only 1, so its n factor is 3. Right? Carbon, +3. Here carbon, +4. So +3 to +4, change is 1. Final minus initial, that comes out to be 1. 1 is the change for 1, I have 2. So n factor here is 2. Iodine here is in +5 oxidation state, here is in +7. So +5 to +7, change. Final minus initial, that's 2. 2 is the change for 1 iodine, I have only 1. So n factor here is 2. 2 into 1, that is 2. I hope you got to know how do we calculate the n factor of different oxidizing and reducing agents. Right? Perfect. Now, my dear students, till now, I was talking about those oxidizing and reducing agents in which oxidation state of only one element was changing. See, here only oxidation state of iodine, vanadium was changing, only carbon was changing, only iodine was changing. That's why I was calculating the change in the oxidation state of these elements only. Now, what if there is a compound? What if there is a compound in which? What if there is a compound in which oxidation state of more than one element changes? What if there is a compound in which oxidation state of more than one element changes? So, the next category of n factors is n factor of those substances. N factor of those substances in which oxidation state of more than one element changes. Oxidation state of more than one element changes. How do we calculate their n factors? For example, you have got a compound like this AB. Let's say this is a compound AB. Let's say this compound is participating in some reaction. And during the reaction, let's say oxidation state of A as well as B is changing. Now, how they can change? For example, oxidation state of both the elements can decrease. Oxidation state of both the elements during the reaction can increase. Oxidation state of both the elements during the reaction can decrease. Or oxidation state of one element can increase, another one can decrease. Now, how do we calculate their n factors? My dear students, if the oxidation state of both these elements are increasing or both these elements is decreasing, then remember, its n factor is simply going to be n1 plus n2. Similarly, if oxidation state of both the elements is decreasing also, its n factor is still going to be n1 plus n2. And remember, if oxidation state of one element increases, another one decreases. So its n factor will be magnitude of n1 minus n2. n1 minus n2. If n1 is not equal to n2. Okay? Remember this particular stuff, guys. If you have got a compound in which oxidation state of, for example, two elements is increasing simultaneously, its n factor is going to be n1 plus n2. If the oxidation state of two elements is decreasing simultaneously, again n1 plus n2. If oxidation state of one element increases, another decreases. So it's going to be n1 minus n2 ka mod. Right? Okay? Now, my dear students, one more important thing. Let me take certain examples so that it becomes properly clear to you. Let me take few examples by means of which it becomes very, very, very clear to you. Just a second. For example, this is the case. I want to calculate n factor of this particular substance. Now, first of all, if I calculate the oxidation states, oxidation state of iron here will be +2. When you calculate the oxidation state of carbon, it will be +3. This iron is in +3 oxidation state. This carbon is in +4 oxidation state. Now, +2 to +3 increase. +3 to +4 increase. Right? Oxidation state of both the elements is simultaneously increasing. So how do I check its n factor? Its n factor is simply going to be n1 plus n2. Now see, +2 to +3. +2 to +3. Final minus initial. The value is 1. 1 is the change for one iron. I have only 1. So 1 into 1 is nothing but 1 only. Right? Plus 3 to plus 4. What is the change? Final minus initial. The value is 1. 1 is the change for one atom. I have 2. So 1 into 2 is 2. Right? So its overall n factor is going to be n1 plus n2. That comes out to be 3. Correct? Understood? Let me take one more example. For example, I want to know the n factor of this particular species. First of all, let's calculate the oxidation states. Copper here will be plus 1 oxidation state, sulfur is in minus 2. This copper is in plus 2 and sulfur here is in plus 4. Now, plus 1 to plus 2, increase. Minus 2 to plus 4, again increase. I would say this is the compound in which oxidation state of more than one element is increasing simultaneously. Its n factor is going to be n1 plus n2 again. So, plus 1 to plus 2, plus 1 to plus 2, calculate the change. Final minus initial, the value is 1. 1 is the change for one atom, I have 2. So 1 into 2 is 2. Minus 2 to plus 4, minus 2 to plus 4, calculate the change. Final minus initial. So 4 minus minus 2, the value is 6. 6 is the change for 1 only. So n2 is 6. So overall, n1 plus n2. 6 plus 2 comes out to be 8. Its n factor over here is going to be 8. Right? Let me take one more example. With that, things will be more clear to you. Let me take one more example. Talk about this one. Calculate the oxidation state of iron. It's plus 3. Sulfur here is in minus 2. Iron plus 2. Sulfur plus 4. Now check it out. Plus 3 to plus 2. Decrease. Minus 2 to plus 4. Increase. Oxidation state of one element is increasing, another one decreasing. So its n factor is going to be n1 minus n2 come mod. Have a look. Plus 3 to plus 2. What is the change? Final minus initial. The value is 1. 1 is the change for 1. I have 2. So n1 value is 2. Minus 2 to plus 4. What is the change? Change is 6. Final minus initial. The change is 6. And 6 3s are 18. So n2 value is 18. Now, is it going to be n1 plus n2 or n1 minus n2? Minus. Subtraction. So the value comes out to be 16. Okay. Now, my dear students, there is one case which is left in n factor calculation. What is that? That is n factor of the substance which undergoes disproportionation. N factor of the substance which undergoes disproportionation. What is meant by disproportionation? For example, this is the reaction. Oxidation state of bromine here is 0. Here bromine is in plus 5 oxidation state. Here bromine is in minus 1 oxidation state. 0 to plus 5, increase. 0 to minus 1, decrease. 0 to plus 5, increase. 0 to minus 1, decrease. I would say oxidation state of same element is increasing as well as decreasing simultaneously. Oxidation state of same element is increasing as well as decreasing simultaneously. Whenever you see oxidation state of same element increasing as well as decreasing simultaneously, we say that species undergoes disproportionation. Whenever oxidation state of same element increases as well as decreases simultaneously, remember, we say that species undergoes disproportionation. And my dear students, how do we calculate n factor of that substance which undergoes disproportionation? It's n1 multiplied by n2 divided by n1 plus n2. Now, what is n1 and what is n2? 0 to plus 5. The change is 5. 5 is the change for 1. I have 2, so 5 2s are 10. n1 value is 10. 0 to minus 1. The change is 1. 1 is the change for 1. I have 2. So n2 value is 2. So it's going to be 10 multiplied by 2 divided by 10 plus 2. The value is 20 divided by 12. It's going to be 4, 5, 4, 3. 5 by 3. So its n factor is 5 by 3 here. Okay. Similarly, I can give you a question like this. I'm giving you a reaction. H2O2. It gives H2O plus O2. H2O plus O2. Oxygen. Minus 1 oxidation state because it's hydrogen peroxide. Oxygen. Minus 2 oxidation state. Here. 0. So minus 1 to minus 2. Decrease. Minus 1 to 0. Increase. Oxidation state of same element is increasing as well as decreasing simultaneously. If I talk about its n factor, if oxidation state of same element is increasing as well as decreasing simultaneously, it's undergoing disproportionation. So its n factor has to be n1 n2 divided by n1 plus n2. Now again, you have to calculate n1, you have to calculate n2. Minus 1 to minus 2, change is 1. 1 into 2 is 2, so n1 value is 2. Minus 1 to 0, the change is 1. 1 is the change for 1, I have 2, so 1 into 2 is 2. Right? So n1 as well as n2. Both are 2. So 2 multiplied by 2 divided by 2 plus 2. The value comes out to be 1. The value comes out to be 1. So its n factor is 1. N factor of this H2O2 is 1. If n factor of H2O2 is 1, so its equivalent mass will be molar mass divided by 1. Right? I hope this is clear to everyone. Now, my dear students, there is one more topic here. What is that? That is, how do we balance the reactions? Well, you need not to know all the methods to balance the reactions. You just need to know the simplest method by means of which you can balance. Right? I'll show you the simplest method by means of which you can balance the reactions. So first of all, you mark the heading as balancing in acidic medium. Balancing in acidic medium. One method I'll show you, that is more than sufficient. Balancing in acidic medium. Okay? Now guys, have a look. There are some steps which I want you guys to remember here. The first step is calculate the n factor of reactants. Calculate the n factor of reactants. Second step is crisscross the n factors. Third step is balance all atoms except hydrogen and oxygen. Next, balance oxygen with the help of water. Next, balance hydrogen with the help of H positives. These are the set of the steps which you need to know. Now, for example, I'm giving the reaction like this. Understand properly. I'm giving the reaction. The reaction is, for example, MnO4 negative plus Fe di positive. It gives Mn di positive plus Fe tri positive. Right? I want you to balance this reaction in acidic medium. First of all, we need to calculate the n factor of the reactants. We need to calculate n factor of the reactants. Okay? We need to calculate n factor of the reactants first. If you talk about the n factor of this reactant, see, oxidation state of manganese here is +7, here it is +2, +7 to +2. Its n factor is 5. N factor of iron, +2 to +3, the change is 1, n factor is 1. So you got the n factors. You got the n factors. Now, my dear students, crisscross these n factors. This 1 will go here, this 5 will go here. Okay? Now, after crisscrossing, balance all the atoms except hydrogen oxygen. Balance all the atoms except hydrogen oxygen. So 1 manganese, this is going to be 1 manganese. 5 iron, and this is going to be 5 iron. Okay? Balance all the atoms except hydrogen oxygen. Now, balance oxygen with the help of water. How many oxygen do you see here? 4? 4 on this side. Is there any oxygen on this side? No. Which side is oxygen deficient? Right side. How many oxygen deficiencies? 4. So add 4 water molecules on this side. That side which is oxygen deficient. Okay? Now, talk about hydrogen. Do you have any hydrogen on this side? No. Do you have hydrogen on this side? Yes. How many? 8. Add 8 H positives here. Add 8 H positives here. Perfect. The reaction is balanced. You need not to check it now. Am I clear with this, guys? Just tell me once. Am I clear with this? Did you understand how to deal with such things? Balancing in acidic medium? Let me give you one more example. With that, things will be more clear to you. For example, I'm taking the reaction. The reaction is, let's say, like this. Cr2O7 di negative, Sn di positive, gives Cr tri positive, Sn plus 4. Now, people, oxidation state of chromium, when you calculate, it's +6. In here is in +2, +3, +4. So +6 to +3, +6 to +3. How is it? How much is that change? 3. 3 is the change for 1. I have 2. So 3 2s are 6. So its n factor here is 6. +2 to +4. N factor is 2. Crisscross the n factors. This 2 will go here. This 6 will come here. After crisscrossing the n factors, Balance all the atoms except hydrogen oxygen. So 4 chromium on this side. So 4 chromium on this side. 6 tin on this side. 6 tin on this side. Okay. Now, balance oxygen with the help of water. 7 2s are 14. 14 oxygen atoms on this side. No oxygen atom on this side. So, add 14 water molecules on that side which is oxygen deficient. Okay. Now talk about hydrogen. 28 hydrogen atoms. On this side, no hydrogen. So add 28 H positives on that side which is hydrogen deficient. So this is now the balanced chemical equation. Okay. So this was balancing in acidic medium. Now, there are some chains when it comes to balancing in basic medium. Balancing in basic medium. Again, there are similar rules. The first rule is calculate the N factor of the reactants. Number 2, crisscross the N factors. Number 3, balance all atoms except hydrogen and oxygen. Next is balance negative charge with the help of OH negatives. Next is balance oxygen with the help of water. You don't have to balance hydrogen here because hydrogen is automatically balanced. For example, let me give you one example, guys. Let me give you one example. Let's say I'm taking the reaction Cl2 plus IO3 negative. It gives Cl negative plus IO4 negative. Let's say this is the reaction. I need to balance this reaction in which medium? I need to balance this reaction in basic medium. Now see, 0 to -1. 0 to -1. What is the change? 1. 1 is the change for 1. I have 2, so its N factor is 2. Iodine here is in +5 oxidation state. So +5 to +7. +5 to +7. N factor 2. After getting the N factors, we need to crisscross. This 2 goes here, this 2 goes here, right? Now balance all the atoms except hydrogen, oxygen. So 4 chlorine atoms on this side, 4 chlorine atoms. 2 iodine on this side, 2 iodine on this side. Okay. Now after balancing all the atoms except hydrogen, oxygen, we have to balance the negative charge now with the help of OH negatives. Do you see any charge here? No. Do you see any charge here? Yes. On 1 IO3 molecule, charge is -1. On 2, it's going to be -2. 1 Cl carries -1. 4 Cl carries -4. 1 IO4 carries -1. 2 will carry -2. So -4 -2 comes out to be -6. So which side is negative charge deficient? Left side or right side? Left side is negative charge deficient. How many negative charge deficiency? 4. So add 4 OH negatives on this side. Which side is negative charge deficient? Okay. Now, balance oxygen. Balance oxygen. How many oxygen atoms do you see here? 4 plus 6, that is 10. 10 oxygen atoms. How many on this side? 4 2s are 8. 8 oxygen atoms on this side. So which side is oxygen deficient? Right side. How many oxygen deficiency? 2. So add 2 water molecules on that side, which is oxygen deficient. Now the reaction is balanced. The balanced chemical equation. Okay? It is a balanced chemical equation, people. Am I clear? Am I clear, people? One more example I'm taking. For example, you have got reaction like this, MnO4 negative plus Br negative. It gives MnO2 plus BrO3 negative. I want to balance this reaction in basic medium with the help of same method. So again, what I'll be doing? I'll be first of all calculating the N factors. N factor of this one. See, oxidation state is +7 here. Here the oxidation state is +4. +7 to +4. N factor is 3. -1 to +6. Minus 1, sorry, not plus 6, it's plus 5. Minus 1 to plus 5. Minus 1 to plus 5. What is the change? Final minus initial. The value is 6. Its n factor is 6. So I got the n factors of both the reactants. If we got the n factors of both the reactants, this 6 will come here, this 3 will come here. Right? Now, people, balance all the atoms except hydrogen oxygen. 6 manganese, 6 manganese. 3 bromine, 3 bromine. Okay? Now, after doing this, we are supposed to balance the negative charge with the help of OH negatives. Balance the negative charge with the help of OH negatives. 1 MnO4 carries minus 1, 6 will carry minus 6. Br carries minus 1, so 3 will carry minus 3. So minus 6 minus 3 comes out to be minus 9. 1 BrO3 molecule carries minus 1, 3 will carry minus 3. This does not carry any negative charge. So which side is negative charge deficient? Right side. How many negative charge deficiencies? How many negative charge deficiencies? 6. So I'll be adding 6 OH negatives on this particular side. Okay? 6 OH negatives on this particular side. Now, balance oxygen with the help of water. So how many oxygen on this side? 6 4s are 24. How many oxygen on this side? 6 2s are 12. Plus 3 3s are 9. Plus 6. So this comes out to be 27. 27, 24. So which side is oxygen deficient? Left side. How many oxygen deficiencies? 3. So add 3 water molecules on this side, which is oxygen deficient. So this is how your balancing is done. I believe I'm clear to everyone. Okay? I believe I'm clear to everyone. All right, people? I think we'll take a break here. And after the break, I'll meet you. We are left with one topic here in this particular chapter, that is redox titration. That will be after the break. That will be after the break. Okay? So I'll meet you. One topic is left here. Not till 7:30, no way. It is going to be slightly long break, but not till 7:30, that's too much. Just give me a second. I think we can continue for like 5-10 more minutes. After that, I'll give the break, okay? We can continue for like 5-10 minutes more. We can continue for some time, some more time. See, guys, one more thing. One more thing. Yes, I'm also fasting. One more time. One more thing, guys. What is that? That is concept of equivalence. Concept of equivalence. My dear students, the way we calculate moles of any substance, in the similar way we calculate gram equivalents of a substance. The way we calculate moles of any substance, in the similar way we calculate gram equivalents of any substance. How exactly? Remember, number of gram equivalents of a substance is always equal to given mass of the substance in grams divided by equivalent mass of the substance. Okay? Second formula. number of moles of the substance multiplied by n factor of the substance. Third formula, normality multiplied by volume of the solution in liters. These are the three results with the help of which we calculate gram equivalence of a substance. These are the three ways by means of which we calculate gram equivalence of a substance. Okay. Similarly, my dear students, there is one more term, number of milliequivalents. How do we calculate milliequivalence of the substance? It is equal to given mass of the substance in grams divided by equivalent mass of the substance multiplied by 1000. Similarly, second result, normality multiplied by volume of solution in ml. Okay. Normality multiplied by volume of solution in ml. And at the same time, one more thing, remember, number of milliequivalents is always equal to number of gram equivalents multiplied by 1000. Number of gram equivalents multiplied by 1000. Okay, number of gram equivalents multiplied by 1000. Perfect. Remember these results directly, guys. And if you remember these results directly, then there is a term called as normality. There is a term called as normality, a simple term. How do we define normality? Normality is simply defined as the number of gram equivalents of solute present in 1 liter of the solution. Number of gram equivalents of solute present in 1 liter of the solution. If you remember, how do we define molarity? Number of moles of solute present in 1 liter solution. In the similar way, number of gram equivalents of solute present in 1 liter of solution. That gives you normality. So, what are its formulas basically? Normality is number of gram equivalents of solute divided by volume of solution in liter. This is the first result with the help of which you can calculate normality. Second one, mass of solute multiplied by 1000 divided by equivalent mass of solute multiplied by volume of solution in ml. This is the second result. And third and direct result, remember, normality is equal to molarity multiplied by n factor of solute. Multiplied by n factor of solute. Remember these three results. And one more thing. What are the units of normality? It's going to be gram equivalent per liter. Or you can call it as normal as well. You can call it as normal as well. Okay. For example, if I say normality of the solution is 2, what does it mean? It means that 2 gram equivalents of solute are present in 1 liter of solution. Okay, 2 gram equivalents of solute are present in 1 liter of solution. Okay. Now, guys, similarly, there are something important. I would say important reactions of KMnO4 in acidic medium, which you are going to remember. Some very, very, very important reactions of KMnO4 in acidic medium. First of all, your KMnO4 in acidic medium, it gets converted into Mn dipositive. This is something all of you would be knowing now. In acidic medium, KMnO4 gets converted into Mn dipositive. Now, my dear students, KMnO4, since it's a strong oxidizing agent, so the first thing, this KMnO4, it can convert Fe dipositive into Fe tripositive. Whenever KMnO4 comes in contact with Fe dipositive, this KMnO4 converts Fe dipositive into Fe tripositive. In which medium? In acidic medium. Similarly, the same KMnO4 converts Sn dipositive into what? Into Sn plus 4. The same KMnO4 converts I negative into what? Into I2. In which medium? Acidic medium. The same KMnO4 converts oxalate ion into carbon dioxide. The same KMnO4 converts H2S into sulfur. The same KMnO4, it converts H2O2 into O2. In which medium? In acidic medium. Okay. Perfect. Now you can easily write the reactions. How exactly? Understand. For example, if you talk about the first one, I told you KMNO4 converts what? Fe dye positive. In which medium? Acidic medium. Converts Fe dye positive in acidic medium into what? Into Fe tri positive. And itself gets converted into Mn dye positive. We know that. And just add water here. The reaction is complete. You don't have to remember the reaction. You can make the reaction now. For example, I have to make this reaction. I'm talking about KMNO4. KMNO4 converts what? It converts C2O4 dinegative. In which medium? Acidic medium. Into what? Into carbon dioxide. Itself gets converted into Mn dye positive. And with that, you can write water as well. Similarly, you can write all these reactions. And my dear students, same stuff is shown by K2Cr2O7 as well. It is just one thing you have to remember. When you talk about K2Cr2O7, that's again a strong oxidizing agent. And in acidic medium, it gets converted into Cr tri positive. Now, whatever reactions I showed for KMNO4, all those reactions K2Cr2O7 also shows. So what are they? K2Cr2O7. It converts Fe dye positive into Fe tri positive. It converts Sn dye positive into Sn plus 4. Sn dye positive into Sn plus 4. It converts oxalate ion C2O4 dye negative plus carbon dioxide. It converts I negative into I2. It converts H2S into sulfur. Okay. It converts H2O2 into O2. Now you can write the reaction as well. For example, I have to write this reaction. K2Cr2O7. K2Cr2O7 converts Fe dye positive. In which medium? Acidic medium. Into what? Into Fe tri positive. Okay. Itself gets converted into what? Cr tri positive. Just add water as well. That's all. Take any reaction. For example, you have to make this reaction. K2Cr2O7 converts I negative in acidic medium into what? Into I2. Itself gets converted into Cr tri positive. And with that, we have got water as well. Perfect. So you can make all these reactions here on your own. And these are the reactions of what? K2Cr2O7. For example, I have to make this reaction. K2Cr2O7. It converts H2O2 in which medium? Acidic medium. Into what? Into O2. Itself gets converted into chromium tri positive. And with that, we have got water as well. Okay. Done. So here we are taking a break. I'll see you after the break. And this break will be comparatively lengthy. So we have got a break time till 7 p.m. Okay. Break till 7 p.m. I would want every one of you to be back exactly at 7 p.m. Okay. Okay, let's make it as 10 p.m. is very less. Make it as 10. Now, okay. I'll see you all back at 7:10. Yes, I'm going to open my fast. I was fasting. Yeah, I might take a bit of. You also have your food or something, right? 7:10 is perfect. I'll see you exactly at 7. See you. But be back, okay? Be back. Complete. Guys, can you hear me? Can you all hear me? Yes? Okay. So is everyone back? Is everyone back? Perfect. Let's start then, no? Which chapter is currently going on? Currently, redox reactions is going on. And we are left with one very important topic of redox, that is your titration. That is your titration. So, my dear students, first of all, I hope like all the n factor calculation, every single thing is clear till here. Now, you mark the heading as law of equivalence. Or you can say law of chemical equivalence. What this law of equivalence says exactly? What kind of things we have to conclude from this law of equivalence? Where do we use this law of equivalence? That is important. So first of all, for example, you have got the reaction A plus B, it gives C plus D. Imagine this is the reaction. In short, law of equivalence says just one thing. Law of equivalence says whatever gram equivalence of A will be reacting, same gram equivalence of B would be also reacting, same gram equivalence of C would get formed, and same gram equivalence of D would get formed. Whenever you will have a reaction A plus B gives C plus D, gram equivalence of A reacted will be always equal to gram equivalence of B reacted, will be always equal to gram equivalence of C formed, will be always equal to gram equivalence of D formed. Okay? You can write the same statement in terms of milli-equivalence as well. You can say milli-equivalence of A reacted will be always equal to milli-equivalence of B reacted, will be equal to milli-equivalence of C formed, will be equal to milli-equivalence of D formed. Okay? Point number one. Now, point number two. For example, you have got a scenario like this. Let's say you have got a scenario like this. Like what? For example, you have got a container. In this container, for example, there are some three substances, A, B, and C. Imagine in this particular container, there are some three substances, A, B, and C. My dear students, for example, if you are adding some fourth substance, D, in the same container, and I'm assuming that D reacts with all. D reacts with A, B, as well as C. Let's say this substance D which you are adding. I'm assuming this D reacts with A as well as B as well as C. Then remember, law of equivalence says that gram equivalence of A reacted plus gram equivalence of B reacted plus gram equivalence of C reacted will be equal to the gram equivalence of D reacted. Okay? Now, what if D reacts only with A and B? If D reacts only with A and B, what happens at that time? For example, the substance D, if it only reacts with A and B, then law of equivalence says that gram equivalence of A reacted plus gram equivalence of B reacted will be directly equal to gram equivalence of D reacted. Then you have got nothing to do with C. I hope this is clear to everyone. My dear students, all the questions which comes from your titration part, when it comes to the NEET examination, they can be solved from these three statements only. All your questions, whatever question can be asked. Like how exactly? Well, In order to solve the questions, there are some n factors which I want you to remember. In order to solve the questions, there are some n factors which I want you guys to remember. And what are those n factors? Remember n factor of KMnO4 in acidic medium. That is 5. That all of you would be already knowing. N factor of KMnO4 in acidic medium, that's equal to 5. Okay, that is equal to 5 in acidic medium. We have discussed this already. Now, whatever n factors we have already discussed, I want you to remember few. Now, similarly, for example, you have got KMnO4. You are making KMnO4 to react with FeSO4. For example, in acidic medium, what is going to happen? Since this is iron di positive, and you know in acidic medium, KMnO4 converts Fe di positive into what? Into Fe tri positive. KMnO4 converts Fe di positive into Fe tri positive, due to which change in the oxidation state, final minus initial, the value is 1. 1 is the change for one atom, 1 only. So its n factor is 1. So remember, whenever you see a scenario in which KMnO4 is going to react with FeSO4, it is not only KMnO4, it can be K2Cr2O7 also. If K2Cr2O7 reacts with FeSO4 in acidic medium, remember, you are going to take the n factor of FeSO4 as 1. Similarly, for example, you have got sodium oxalate, Na2C2O4. For example, this sodium oxalate you are making to react with KMnO4 or K2Cr2O7 in acidic medium. Remember, KMnO4, K2Cr2O7 converts oxalate into carbon dioxide. We know that already, due to which its n factor will come out to be 3. Sorry, its n factor will come out to be 2. In case of potassium oxalate, remember its n factor as well. Potassium oxalate, its n factor is also 2. Okay. FeC2O4, ferrous oxalate, its n factor is 3. Cu2S, in reaction with KMnO4, K2Cr2O7 in acidic medium, its n factor is going to be 8. CuS, its n factor is going to be 6. Even more salt, its n factor is going to be 1. Remember these basic few n factors, you can solve the questions easily. For example, let me show you a few questions so that you can understand where do I use all of this. And guys, I think I have to take part 2 of today's session as well, okay? There will be one more part because we won't be able to complete the entire thing. Look at this question, for example. The question says, what volume of 0.1 molar KMnO4? What volume of 0.1 molar KMnO4 is required to oxidize? 100 ml of 0.3 molar FeC2O4 in acidic medium. So as per the question is concerned, KMnO4 is going to react with FeC2O4 in which medium? In acidic medium. KMnO4 is going to react with FeC2O4 in which medium? In acidic medium, right? Now the question says, what volume of 0.1 molar KMnO4? Molarity of KMnO4 is 0.1. Its volume we are supposed to calculate. Molarity of FeC2O4 is 0.3. Its volume is how much? Its volume is 100 ml. Right? Its volume is 100 ml. Now, first of all, do we remember the n factor of KMnO4 in acidic medium? Yes, that's 5. N factor of FeC2O4 in acidic medium, that's 3. Right? Now, my dear students, molarity multiplied by n factor, that gives me what? That gives me normality. So, normality will be 5 into 0.1, that is 0.5. Similarly, morality into n factor, that is normality. That will be this into this, 0.9. Right? Now, since these two are reacting, if these two are reacting, so I can say gram equivalence of KMnO4 reacted will be equal to gram equivalence of FeC2O4. As I told you a few minutes back, whenever you have got the reaction, A plus B gives C plus D. So, law of equivalence says that gram equivalence of A reacted will be equal to gram equivalence of B reacted. Similarly, I can say gram equivalence of KMnO4 reacted has to be equal to gram equivalence of FeC2O4 reacted. Correct? Or I can use the statement in terms of milliequivalence as well. Right? I can use a statement in terms of milliequivalence as well. Since volume right now is ml, volume is in ml, so I'll use the statement in terms of milliequivalence. I'll write milliequivalence of 1 reacted has to be equal to milliequivalence of 2 reacted. Why did I use the statement in terms of milliequivalence? Because volume is in ml. If volume was in liters, then I would have written the statement in terms of gram equivalence. So I can say milliequivalence of 1 will be normality of 1 multiplied by volume of 1 in ml is equal to normality of 2 multiplied by volume of 2 in ml. Tell me, what is normality of 1? That is 0.5. Volume of 1 to be calculated. Normality of 2, 0.9. Volume of 2, that's 100. So V1 value, after solving this, will come out to be 180 ml. So I'll say 180 ml. I'll say 180 ml. 180 ml of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar FeC2O4 in acidic medium. Understood? Understood, people? Let's try to solve one more question based on the same so that you will properly understand this. Look at this question. What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.2 molar FeSO4 in acidic medium? So as far as the question is concerned, your KMnO4 is going to react with what? It is going to react with FeSO4. Okay. Now, molarity of KMnO4 is given to me as 0.1. Volume of KMnO4 needs to be calculated. Molarity of FeSO4 is 0.2. Volume of FeSO4 is 100 ml. Now tell me one thing. What is the N factor of KMnO4 in acidic medium? That's 5. N factor of FeSO4. That's going to be 1. Few minutes back only I told you. Now what statement I'll be using? Since volume is in ml, I'll be using the statement in terms of milliequivalence. I'll write milliequivalence of 1 reacted has to be equal to milliequivalence of 2 reacted. Okay. Now, my dear students, if I ask you molarity into N factor gives me normality. So normality of 1 is equal to 5 into 0.1, that's 0.5. Molarity into N factor, that's normality. So normality of 2 is equal to 0.1 into 2, that is 0.2. Now milliequivalence of 1 will be normality of 1 multiplied by volume of 1 in ml. Okay. Similarly, milliequivalence of 2 will be normality of 2 multiplied by volume of 2 in ml. Now, because you know, I've already given you the formulas to calculate milliequivalence. There are 3 formulas to calculate gram equivalence, 2 formulas to calculate milliequivalence. Already given you the formulas. Now, my dear students, N1 value is given to me in the question 0.5. V1 value to be calculated. N2 value 0.2. V2 value, that's 100. So V1 will come out to be 40 ml. So I would say 40 ml of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.2 molar FeSO4. In which medium? In acidic medium. I believe this is also clear to everyone. Right? Now similarly, let's try to solve one more question. Let's try to solve one more question. Look at this question, guys. How many moles of KMnO4? How many moles of KMnO4, right? How many moles of KMnO4 will be required to react completely with 1 mole of potassium oxalate? So basically, you are making KMnO4 to react with what? To react with potassium oxalate. Now, first of all, do we know their N factors? N factor of KMnO4 in acidic medium is 5. N factor of potassium oxalate is 2. Now, how many moles of KMnO4? Moles of KMnO4 needs to be calculated. How many moles of KMnO4 will be required to react completely with 1 mole of potassium oxalate, right? 1 mole of potassium oxalate. So N2 value is equal to what? 1 mole of potassium oxalate, right? So how many moles of KMnO4 are required to react with 1 mole of potassium oxalate in acidic medium? Now, my dear students, since the data is given in terms of moles, so let me use the statement in terms of gram equivalence. I'll write gram equivalence of 1 reacted has to be equal to gram equivalence of 2 reacted. That means gram equivalence of KMnO4 reacted will be equal to gram equivalence of potassium oxalate reacted. Now, is there any formula to calculate gram equivalence in terms of moles? Yes. Gram equivalence is equal to number of moles multiplied by N factor. So I'll say gram equivalence of 1 will be number of moles of 1 multiplied by N factor of 1. Similarly, number of moles of 2 multiplied by N factor of 2. Number of moles of 1 needs to be calculated. N factor 1 is equal to 5. N2, that's 1. And this is 2. So I would say N1 is equal to 2 divided by 5. That means 0.4. So I would say 0.4 moles of KMnO4 are required to react with 1 mole of potassium oxalate. In which medium? In acidic medium. Am I clear with this? Am I clear with this? Am I clear with this, people? Everyone? Yes? Perfect. Let me show you one more question of the same manner, which you should be in a position to solve on your own. Look at this question. How many moles of K2Cr2O7 are required to react completely with 2.5 moles of Cu2S? So these two have to react in acidic medium. So first of all, N factor of K2Cr2O7 is 6. N factor of Cu2S, already I've told you that's 8. How many moles of K2Cr2O7 are required to react completely with 2.5 moles of Cu2s in acidic medium. So I can directly say gram equivalence of K2Cr2S1 reacted has to be equal to gram equivalence of Cu2s reacted. So gram equivalence of 1 means number of moles of 1 multiplied by n factor 1. Gram equivalence of 2 means number of moles of 2 multiplied by n factor 2. N1 needs to be calculated. N factor 1 is 6. N2 is 2.5 multiplied by 8. So N1 value will be equal to how much? How much this will be? How much this will be? 2.5. This is 2, 3. This is 2, 4. Right? 4 into 2.5 is 10. 10 by 3 is 3.3. So N1 value came out to be 3.3. So I would say 3.3 moles of K2Cr2S1 are required to react with 2.5 moles of Cu2s in acidic medium. Okay? I hope I'm clear with this. Perfect? All right? Okay, can you give this question a try on your own now? Wait. Similar sort of question. Can you give it a try? Okay, guys. So you can solve the same question like this. We have got FeC2O4 and you are making it to react with what? KMnO4 in acidic medium. So first of all, how many moles of FeC2O4? Its n factor, we already know that's 3. N2 value is 2. And n factor 2. KMnO4, its n factor in acidic medium is 5. Again, you are going to use the same concept. N1 into n factor 1 is equal to N2 multiplied by n factor 2. So N1, we have to calculate. N factor 1 is 3. N2 is 2. And this is 5. So N1 is equal to 10 by 3. That means 3.33. Perfect. So these sort of questions can be asked in your NEET examination when it comes to the titration part. Okay. Similarly, there is one more type of the question which you need to know here. Let me show that to you. Okay, this is the question. 6 moles solution of AN positive. 6 moles solution of AN positive requires 2 moles of Cr2O7 dinegative. Requires 2 moles of Cr2O7 dinegative. 6 moles of AN positive requires 2 moles of Cr2O7 dinegative for the oxidation of AN positive to AO3 negative. For the oxidation of AN positive to AO3 negative. So basically, Cr2O7 dinegative is oxidizing AN positive to AO3 negative. In which medium? In acidic medium. And you know, Cr2O7 dinegative in acidic medium itself gets converted into what? Cr tripositive. What do we have to calculate? The value of N, the charge present on this A, we have to calculate, right? So what do we do here? If I talk about, this is first of all N1, call this as N2. If I talk about N factor 1, it is equal. See, the oxidation of A is +1, plus N here. Here it is +5. So initial is plus n, final is 5. So final minus initial. Final minus initial. This is the n factor of this, right? What is the n factor of Cr2O7 dinegative? Oxidation state here is plus 6. Here the oxidation state is plus 3. Right? Plus 6 to plus 3. Final minus initial. The value is 3. 3 is the change for 1. I have 2. So 3 2s are 6. So again, I'll use the equivalent concept. I'll say gram equivalence of this reacted will be equal to gram equivalence of this. So which means n1 into n factor 1 has to be equal to n2 multiplied by n factor 2. What is n1? That is 6. N factor 1, 5 minus n. N2 value 2. N factor 2, 6. 6 gets cancelled. N value comes out to be 3. This sort of a question can be also asked. Okay? Okay, so with this, your redox reaction chapter is also done and dusted. Perfect. So guys, I think with this, we'll take a leave today. Okay, we'll have the part 2 of this marathon. Okay, part 2 of this marathon I'll take in 2 to 3 days, wherein we'll be discussing thermodynamics and equilibrium in one session. All right. Okay, and it's very, very, very tough while you are fasting to teach for this long. In 2 to 3 days, I'll be taking one more part 2 marathon of your thermodynamics and equilibrium. All right. Perfect. I hope whatever things I discussed with you today, I hope every single thing is clear. I hope every single thing is clear. All right. Do let me know in the comment section, guys, if you like the session. Okay. And in 2 to 3 days, you will have one more marathon with me of equilibrium and thermodynamics combinedly. All right. Chalo, take care. I hope these chapters, whatever chapters I took today, I hope all these are like super clear to everyone. Huh?